Έχω δοκιμάσει διάφορες επιλογές. Αν ακούγομαι καλά, να μην προσπαθήσω άλλο. Αν ακούγομαι δηλαδή υποφερτά.
Είστε
μια χαρά, πολύ καλά. Καλά.
Τώρα ακόμα καλύτερα.
Μια χαρά.
Είσαι μια χαρά.
Ωραία, ευχαριστώ.
Τι λέτε?
Να ξεκινήσουμε.
Ξεκινήσουμε.
Ναι, νομίζω να ξεκινήσουμε βέβαια.
Στα αγγλικά όπως είπαμε.
Ναι, να κάνουμε switch to English.
Okay. So, good afternoon and happy New Year to everybody and best wishes for good health, joy and progress towards your goals. I'm delighted to introduce this event, which started about 4 years ago as a more focused series of talks on machine learning and artificial intelligence. And it evolved through the years to a more wide event. Last year it was co-organized by 2 labs, and now it is organized jointly by the Computer Science Division of the School of Electrical and Computer Engineering of NTUA and the Data Science and Machine Learning graduate program of NTUA. This year's event reflects, we believe, the excellence of research and educational activities going on in the labs and of the division and within the DSML program as well. We are proud to have among our collaborators of our research groups and also many of them alumni of our labs, either from the ranks of MSc students or even from those that completed their doctoral studies in NTUA. And we are very happy about this. We thank them cordially, and we are certain that you will enjoy a great event. So at this point, I would like to ask our rector, Professor Boudouvis, to officially open the event.
Hello, everybody. It is so good that this particular seminar has become a tradition for the beginning of the new calendar year and brings together distinguished people from state-of-the-art of computer science areas. And most importantly, it attracts the interest of our students. When in person, it used to be a sold-out event. I thank the school, the dean, the heads, the lab directors, the organizers of this event for setting it up. It is such a good seminar, and of course, the speakers for their participation and their offer to our community. And acknowledge the fact that some of the speakers are alumni of this university. I wish you all a healthy and prosperous new year, and to our students who are online, all the best for the upcoming examinations. Thank you.
Thank you very much, Mr. Rector. I would now like to invite Professor Sapountzakis, who is Vice Rector of Finance, Planning and Development, to address the event.
Thank you very much, Professor Pagoudis. Dear colleagues, it's a great pleasure and honor for me to extend a warm welcome to all the participants of the Research Challenges in Computer Science 2022 event, organized by the Division of Computer Science of the School of Electrical and Computer Engineering at the NTUA and the MSc program on Data Science and Machine Learning. I am sure that this series of talks will facilitate the exchange of ideas scientific knowledge and experience. The aim is to present and discuss a wide variety of topics related to recent research advances and challenges in computer science, the boundaries of which continue to expand. The ongoing revolution in the underlying electronics technology continues to create new opportunities for innovation. I take this opportunity to thank all the panelists for attending this event and bringing their expertise to your gathering. You leading experts from academia have the vision, the knowledge, the wherewithal, and the experience to help us pave our way into the future. Thank you very much.
Thank you, Mr. Vice Rector, for your kind words. I would also like to ask Professor Kalantidis, Vice Rector of Administrative, Academic and Student Affairs, to say a few words.
Dear Rector, dear colleagues, dear students, I would like to begin by wishing you all the best for the new year. We are very happy for this series of talks about research challenges in computer science 2022, organized by the Division of Computer Science and the Master of Science, Data Science and Machine Learning from the School of Electrical and Computer Engineering at NTUA. The Division of Computer Science and the School of Electrical and Computer Engineering at the National Technical University of Athens are very strong research entities with world-leading research. I had the opportunity to know this during the recent accreditation procedure, which resulted in 2 outstanding feedback. The collaboration with the master's program in organizing the workshop is an excellent idea to link teaching and research activity in this area. From today's talks, I'm very happy to see that the topics selected are cutting edge and modern within the state of the art of the subject. From my personal view, being a mathematician with research interest in the area of inverse problems, big data often coming from sensors and observations are of utmost importance in model calibration. The mathematics community has strong interest in this area, also at large, especially in the intersection of data, mathematical foundation of machine learning, and optimization. Finally, I would like to thank the organizers and, of course, all the speakers for today's talks. Thank you.
Thank you also, Professor Kalantidis, for your nice words. And let me thank all the Rectors' Council for their presence here and for being so supportive in our activities and events. We function within the NTUA and nothing would be possible without their support. And the same holds for our school, which is the place where all these things develop and are cultivated. So I would like to take the opportunity to ask our Dean, Nektarios, to address the event.
Thank you, Aris. I'm really delighted that we managed to bring together the people, collaborators, our alumni, despite the difficulties that we had with the pandemic. I recall that we started a few years ago as an opportunity to bring together past students, collaborators, professors from our collaborations together after the Christmas vacations. And it happened that the event was sold out, as our rector said before. So we had the strength to continue this event and organize it this year virtually. I hope next year we will be all together in the big auditorium and have more than 500 or 400 people attending. I'm really thankful to our guests, to the speakers that have accepted our invitation. The program is full of people that they are esteemed and very at the top of the science and advances in the fields of computer architecture, machine learning, big data, algorithms. So the program is really full. And I think that all the people attending the event will like all the talks. I think that we can hope next year things will happen at the big auditorium of NTUA. Thank you very much, all the speakers for their availability. We are really thankful for them.
Thank you very much, Mr. Dean. And I would now like to ask Georgios Stamou, who is director of the Data Science and Machine Learning graduate program, to say a few words.
Thank you very much, Aris, and everybody, the rector, vice rectors of NTUA, the dean of the School of Electrical and Computer Engineering, our students, researchers, collaborators, and friends. Thank you, all of you, for being here. I hope you'll enjoy this event. I would like to say that I'm delighted and honored for all these distinguished invited speakers that we have on board, and I'm confident that as every year this event will motivate everybody that is doing research and is now here. As mentioned before, this year this event is co-organized by the new MSc program of NTUA, the Data Science and Machine Learning program. And as I am honored to be the director of this program, I will take this opportunity to say a few words about it. So this graduate program is a result of close collaboration of 4 schools of NTUA, the School of Electrical and Computer Engineering that is leading the program, the School of Applied Mathematical and Physical Sciences, the School of Civil Engineering, and the School of Rural Surveying and Geoinformatics Engineering. It has been started the academic year 2018-19. The duration of the studies is 1.5 years with 12 courses and diploma thesis. The courses introduce students to advances in the theory and applications of artificial intelligence and machine learning and data analytics. And our main goal is to provide students with the necessary mathematical background, but at the same time with hands-on experience, laboratory experience, to deal with big data in real applications. We know that the program is challenging for the students. However, we think that all their efforts are worthy, and the result is at the level of the reputation of National Technical University of Athens. Every year we get not around 40 students, and as we noticed the last years, the application process is very competitive with more than 300 very good applications every year. So it is well known that NTUA attracts the very best of the excellence graduates of high schools around Greece. Now we know that this MSc attracts also the excellent graduates of the Greek universities. We get students that graduate in the top 5% from departments of mathematics, physics, engineering, computer science, economics, etc. More than 20 different departments every year. So for all these reasons, the reputation of the MSc program is already very high. So our graduates start impressive careers in the industry or continue with PhD studies in prestigious universities in US and Europe, and we expect them, of course, to be top-class researchers. So I close this brief introduction with a promise next year to invite graduates from of the MSc program as speakers in the events. Thank you very much.
Thank you, George, and also for your help in organizing this event. And now I would like to ask Dimitrios Fotakis, who has been the soul of this event, and actually for some years now. Many of his students have talked in previous events, and now he has carried the most of the organizational effort very successfully, as you can already see. And I thank him very much, and I would like to give him the speech for a few minutes.
Ari, can I make a brief comment before Dimitri starts?
Of course.
Besides the distinguished speakers of this series of seminars, there is a distinguished attendee, and I'm talking about Stathis Zachos. And I'm so glad that he noticed his participation for the last many years in this particular seminar. And I really enjoy his presence, and I wish him to be with us forever.
Thank you very much. Thank you. I want to say something also. I'm very proud that 25 years ago, I insisted that whoever names the new division computer science, then he will have me also as a member of that division, because there were several other names back then, and that's when I joined the division there. And also I'm very proud that I see not only our graduates here, but also many of graduates, many people who are affiliated with my alma mater, which is ETH in Zurich. Thank you.
Thank you both for these comments. Very, very thoughtful indeed, Mr. Rector. This comment about Stathis. He's always been with us and inspired all of us, many of us, in doing whatever we are doing. So thank you, Stathis, very much for all this. Whatever you have given so far.
Thanks.
And let's hope that you will give for many more years. Now I would like to give the speech to Dimitris.
Yeah, thank you, Ari. Thank you all, especially our rectors, the dean of the school, and of course Stathis, for being here, for attending this event. I'm also delighted to see this event becoming sort of a tradition. So we started 4 years ago with more emphasis on theory, but now today we have a diverse and scientifically very strong program, which I believe, as you also said, reflects the research excellence of our labs in the division of computer science. And, I'm very delighted. I'm really delighted about it. I wish to thank our distinguished speakers for accepting the invitation, and of course my colleagues in the Division of Computer Science for suggesting them and inviting them. Thank you all, and I believe that we're looking forward to the first talk. So Thank you. Let's move.
Thank you very much, Dimitris. And as you said, it's time for the first talk. We can't wait to hear what our distinguished guest has to say. So I would like to ask George Goumas to introduce our speaker. We thank you very much, Onur, for this talk. George, please.
Okay, I will do. So, Aris,
Okay.
So, hi everybody. Thank you for being here. It is my great honor and pleasure to introduce Onur Mutlu. Onur is a professor at computer science at ETH Zurich and also a faculty member at Carnegie Mellon University. I'll try to be brief, but his bio is huge, so I just want to highlight what I find most important here. So he's also an ACM and IEEE fellow and an elected member for the Academy of Europe. His broader interests are in computer architecture, obviously, systems, hardware security, and bioinformatics. And his work has influenced not only researchers, other researchers, but also industry. And some of his ideas have been actually implemented in commercial microprocessors and memory systems and so on. So he received 2 bachelor degrees in computer engineering psychology from University of Ann Arbor, and then he moved to University of Texas, Austin to get his master's and PhD. Sorry about that. In addition to his academic positions, he also started the computer architecture research group at Microsoft Research in the second half of 2000. And he held various product and research positions in companies such as Intel, Advanced Micro Devices, VMware, and Google. So Onur is extremely prolific researcher, and his work has led to several best paper, top picks, and test of time recognitions in all the top computer systems and architecture conferences. So as a numbering result, he is in the Hall of Fame for all the flagship computer architecture conferences, ISCA, Micro, ASPLOS, and HPCA. Besides leading the Hall of Fame for ISCA by a huge margin, he is also in the top 2 in every other computer architecture conference. So his excellent research has, for his excellent research, he has received the prestigious Computer Architecture Technical Awards, both from IEEE and ACM, the Edward McCluskey Technical Achievement Award from IEEE, and the Sigurd Maurice Wilkes Award from ACM. So with that, I'll pass the floor to Onur to talk to us about memory-centric computing. Onur, thank you for being here.
Thank you very much, Dionysius, for the kind introduction, and thank you very much, Nektarios, and everyone for the invitation to deliver this talk. I would, of course, very much have preferred to be in person in Athens, which I wanted to visit for many, many years, but unfortunately, due to the pandemic, we couldn't come there for 2 years, even though Micro was supposed to be in Athens for 2 years. And hopefully we will change that this year and going forward. I will share my screen right now. Can you see it?
Yes.
Okay, thank you. So I will start the talk then. So as Dionysius mentioned, I'm going to talk about memory-centric computing. This is actually a quite long talk. I tried to shorten it to 30, 40 minutes. Let's see how it goes. But feel free to ask questions at any time. It's supposed to be an overview of how computing should be going, in my opinion. And also, I will give you some recent results in terms of processing in memory. And also, I will delve into issues like hardware security and memory technology scaling that's pushing us to do something different in our computing systems. So even though it's titled memory-centric computing, I'm going to talk a lot about issues in computing in general. But the major problem that we have today in our systems is computing is bottlenecked by data. And data is really key for many, many applications, especially important applications like machine learning, genomics. These workloads are all data intensive. They require rapid and efficient processing of large amounts of data and we're doing increasingly sophisticated things on data. And on top of this, data is increasing. We can generate much more data than we can process. And here are some example applications that we have been dealing with. They're growing. And as a result, the demands on memory and storage systems is growing, and data is becoming much more of a performance energy bottleneck. Here are some other applications that we're actually exercising, or at least similar applications that we're actually exercising in this call right now: web browsing, inference engines, training engines, video playback and capturing engines. And they're also bottlenecked by data in terms of performance and energy. And here are some other applications that we may not be thinking of on a daily basis, but genomics is a system or workload that's growing significantly because the cost of genome sequencing is reducing greatly, much faster than the cost of a transistor has been reducing for more than a decade right now. As a result, we're able to sequence many, many genomes. And clearly, this has been very important for the understanding of pandemics, but there are many, many other use cases clearly. Unfortunately, even though sequencing technologies have been very successful in generating a lot more data, our sequencing computational analysis techniques have not been as successful in terms of scaling. So the bottleneck in genome analysis today is how fast we can process, move, and perform on the data. As a result, data becomes a big performance energy bottleneck. I don't have a lot of time to talk about genome analysis, but we do a lot of work in this area actually, and I'm quite interested in pushing the technology forward with better computing architectures. And if you look at devices today, devices are very small today. These are like what you would call IoT devices. You can move these devices to anywhere. In fact, these were some of the devices that were shipped to China first in the pandemic. They're being used a lot right now to understand many, many things related to genomes, including the viral genomes. But the problem is these devices are great at sequencing, but they're not good at analyzing data. Imagine if you could actually give these devices to people, and people could sequence genomes and understand, ask intelligent questions like, what do I need actually right now to become better? Or if you give this device to a doctor who can use it at a critical point to understand what kind of drug they should deliver to a patient within a minute or so, wouldn't that be great? So we can actually have a lot of interesting applications if you can enable computation capability where the data is generated. And that requires, I think, a rethinking of how we design computing systems today. So today, what is happening with these devices, they generate data in the field, and that data gets moved to data centers, for example, far away. If you generate data in Africa, you have to move the data to Europe or United States and process the data over there. So data actually causes a huge performance energy bottleneck. And as a result, you cannot make real-time decisions. It takes days and days to actually get intelligent decisions out of these devices' data. So if you're interested, I think this is fascinating, and we do a lot of work in this area. This is an overview paper that we wrote last year on this topic. And we actually do a lot of data-centric designs, for example, to accelerate approximate string matching, for example. This is one example over here. But I think the future is very interesting in applications like this because the devices are scaling. Unfortunately, our computational capability is not scaling very well. And this talk is about why our computational capability is not scaling very well. And if you're interested in further, we have a lot of lectures on this topic that I will also mention toward the end of this talk. But clearly, data is today overwhelming modern machines. It's overwhelming the storage and memory capability, the communication capability, and in the end, the computation capability. Even though you may have a great computation engine, because you're bottlenecked by storage and memory and communication, computation is actually getting wasted. And data also greatly impacts robustness, energy, performance, and cost, and also as well as security. And I will mention that in the initial parts of my talk to actually motivate why we should be doing more intelligent computation near data. So if you look at a computing system, fundamentally, it consists of three key components: computation, communication, storage, and memory. And if you look at the grand overview of computing, we've heavily optimized the computing unit, and we mostly ignored communication and memory and storage units. I believe that needs to change, and we need to take a much more holistic approach to how we design computing systems. So if you look at a processor-centric design today, it kind of looks like this. This is an old picture that I drew actually from my first National Science Foundation proposal when I was at CMU. But if you look at this picture, computation is limited on a chip. Even though we know how to design computation units really well today, most of the system is dedicated to caches, interconnect, other caches, other interconnect, memory controllers, other caches, main memories, other interconnect, storage systems. So if most of the system, more than 90% of the real estate of a single node today is dedicated to storing and moving data. Computation is a very little part of it. But the system is still bottlenecked by memory. This should, I think, immediately raise some concerns about how we're designing our systems and where the bottleneck is. And even though we're dedicating a lot of resources to this bottleneck, that resource is still a bottleneck. And as a result, data becomes a performance energy bottleneck in our systems. Here, to give you a data point, this is a study that we did with Google a few years ago. We spent about 1.5 years, 2 years actually on this project. And we analyzed a lot of workloads that I will mention later on also. On mobile workloads, more than 60% of the total system energy is spent on data movement, just moving the data from the processor and the memory system. So my axiom going forward and the rest of this talk will be that an intelligent architecture, if you want to design intelligent architectures, and we would like to, I think, because these architectures will be making decisions for ourselves, they will have intelligence in themselves, but are they designed to be intelligent? If you want them to be intelligent, I think they need to handle data well. The question, of course, is how do you handle data well? And I think there are 3 directions over here. One is we should ensure that data does not overwhelm the components, the system we design essentially, via intelligent algorithms that operate on little amounts of data potentially, or that reduce the data very quickly, via intelligent architectures that do not move the data a lot, and via whole system designs, more importantly, algorithm architecture devices co-designed together so that data does not become a bottleneck. This is for the first direction. We're going to spend a lot of time in this direction the rest of this talk. But let me give you the 2 other directions also. I think we also need to design systems that are fundamentally intelligent. What does this mean? Fundamentally intelligent systems basically make their decisions based on data. If the data is flowing through the system and metadata is also generated or flowing through the system, we can use this so that we can improve our decision making. But if you look at the architectures today that we design, fundamentally, they don't really improve, they don't really learn from the data. So let's take an example of a memory controller. The memory controller on the cell phone, for example, has been working for 6 years. And it's using exactly the same policy it was dictated to use by a hardware designer. And that hardware designer clearly didn't know exactly what was going on in the system and what applications I would be using in my system, for example. What would a self-optimizing system be? A memory controller would actually observe its decisions and its actions based on the interaction with the environment, and it would change its policy based on the interaction with the environment. It would learn basically based on its actions. This I would call fundamentally intelligent. And humans are like this. For example, we interact with the environment. We learn based on our actions. If I put my hand on a hot stove, I will learn that I shouldn't put my hand on a hot stove again. But the memory controller today is not doing that. So I believe we need to redesign the entire system stack today to actually make it fundamentally intelligent. I'm not going to talk about this going forward in this talk because we don't have time, but I think this is very important. And the third direction is I think we need to understand and exploit properties of different data. If you look at data today, data is actually very various. It has many, many characteristics. It has privacy characteristics, security characteristics, compressibility characteristics, locality characteristics, approximability characteristics, bandwidth and latency sensitivity characteristics, or performance characteristics as well. But these characteristics are actually not communicated to the underlying hardware as well as the system. And the system, as a result, doesn't know what decision to make and how it should focus its policies based on the characteristics of the data. All data is mostly treated exactly the same. But if we actually communicate these semantic characteristics of the data into the underlying system, we can actually make much better system level decisions, both at the hardware, the software levels, and we can actually improve our systems a lot. I call this data-driven or data-aware architectures. And again, I don't have time to talk about this in detail, but I will mention that. So basically, if you look at corollaries based on what I discussed, architectures today are not good at dealing with data. They're basically processor-centric as opposed to data-centric. As a result, they're moving a lot of data across the system. And we're going to talk about that a lot in this talk. Second, architectures are not taking advantage of vast amounts of data and metadata that's flowing through the system. They're designed to make simple decisions, human-driven decisions, as opposed to data-driven decisions. Fundamentally, they're not learning from data. Architectures today also don't know and exploit different properties of different data. They're designed to treat all data as mostly the same. As a result, they make component-aware decisions based on, for example, the banks in the memory system or some other characteristics of the memory system or the interconnect, as opposed to the criticality of the data. For example, is this security critical? Should I be protecting this much more than some other data? Those are the data-aware decisions that we would like to get to. So again, as I mentioned, I'm going to focus especially on the data-centric or memory-centric part of it. But I believe data-driven and data-aware architectures are parts of the same puzzle, if you will. And memory-centric architectures also become better if they're data-driven and data-aware. So that's kind of the blueprint of fundamentally better architectures going into the future, in my opinion. But I think to be able to enable this, we really need to rethink the entire stack. And this will be also clear in the data-centric architecture that I will discuss. We really need to rethink not only just the architecture level, but algorithms, languages, system software, as well as underlying devices that we design our systems with. But I believe we can get there step by step. And hopefully in this talk, I will give you some examples of getting there step by step. So going forward, again, in this talk, my axiom will be that if we would like to achieve the highest energy efficiency and performance and other characteristics that we care about, like security, dependability, and reliability, we really must take an expanded view of architecture. Not just focus on a single layer, but cut across the layers, co-design across the hierarchy, algorithms to devices, and specialize our systems as much as possible within the design goals. And I have another view of thinking about this. This is, many of you may be familiar with Richard Feynman, who is a very famous physicist, American physicist, well, world physicist. But he actually coined the term of, I would say, nanotechnology early on, without naming it that way. But basically, he mentioned in this famous talk that there's plenty of room at the bottom in 1950s, late 1950s, meaning that if we could actually understand how individual atoms behave, we could design much more powerful computing systems, as well as much more powerful systems that can change our lives, like synthetic biology, etc. And later, nanotechnology advocates actually made this talk famous. And I still believe that we have plenty of room at the bottom. We just need to discover new devices that can enable us to understand the atomic interactions and do better at the lower level. And again, you can read Wikipedia. He actually talked about denser computing circuitry, like things like swallowing the doctor. These smaller devices can enable us to have significant advances in medicine, for example. But this is true today, I believe. It's getting harder with existing technologies, but there are some technologies that we need to look at going into the future, like future non-volatile technologies in memory, and some other technologies like potentially quantum, as well as carbon nanotubes, etc. We need to push the boundaries at the bottom. There's also some people that argue that there's plenty of room at the top, and this is also kind of obvious, I would say. Clearly, if technology scaling is becoming a problem, there should be more to be done in the software architecture, algorithms, etc., so that we can harness better performance, better efficiency out of a single transistor, for example. But I don't believe that it's just at the top. So I think there's still a lot of opportunity at the top and the bottom. We just need to do the research to understand what opportunities exist and how can we tap into them. But more importantly, in my opinion, if you actually communicate well between and optimize across the top and the bottom, top of the computing stack and the bottom of the computing stack, you can get to a much better place. And I think this talk is really about communicating better between the top and the bottom so that we can take advantage of the underlying technology with algorithms and software at the top so that we can get to a much better place. So that's why I have this expanded view that I mentioned earlier. Sorry, the slides are going a bit faster than I intended to be. That's why we need to think across the stack. And I think data-centric, data-driven, and data-aware architectures can all be enabled by thinking across the stack. Okay, now let me jump into the data-centric or memory-centric part of this one. And even if you look at the data-centric part, we want multiple properties. If you think about what should a data-centric architecture look like, clearly we want to process data where it resides. We don't want to move the data a lot in the system. We want to enable low latency and low energy access to data as much as possible because data is very important. We want to enable low-cost data storage and processing. And we want to intelligently manage data. We want to have intelligent controls handling different properties of data, robustness, security, cost, etc. I'm going to talk about this intelligent data management. I'm not going to touch into the second and third points, but there's a lot of research that's going on in the field on this topic as well. I'm going to talk about the first one especially, but I'm going to motivate it with the intelligent data management part a little bit. So let's jump into it. I call this processing data where it makes sense. Today, we're processing data only in the processor, in the computation units. It could be the CPU, GPU, FPGA. It doesn't matter. You have to move the data to there first. And that movement starts from the sensors or storage units or memory units or the interaction with the user. So right now, the data has to move to the processing unit. So why not actually? So the question is, does this make sense? And hopefully the answer will be, it doesn't make sense in today's systems. And can we do something better? And when I say where it makes sense, I say that we should really process data where it gets generated or where it resides, as much as it makes sense, of course. Sometimes it makes a lot of sense to move the data to a computing unit that has a lot of locality, or the data has a lot of locality that the computing unit can exploit. We should still keep that, of course. But we should enable other options so that we don't waste a lot of energy and performance in our systems, and the data gets processed in places where we could actually process it. Today, we don't have any option. We have to move the data to the processing unit. But this is an old idea, of course, right? This is not something we invented. Processing in or near memory is an old idea. These are some of the earlier papers. There are even earlier papers that look at analog computing that kind of mix memory and logic. But you can see some earlier papers that kind of clearly specify there's logic in memory, And this is a very famous paper for Harold Stone, for example, a logic and memory computer. And they advocated different reasons for doing this. For example, Harold Stone's argument was cost. If you want to make a less costly system, we should really merge logic and memory. And I think a lot of his predictions came true. But today we're in a different place. So clearly, this is an idea that has been advocated for more than 50 years, and it has not panned out. Why do we believe that it has to be revisited today? And why do we believe it can pan out today? So I'll give you a story from two directions. One is the push from technology at the bottom, let's say. At the bottom layers, we're having a lot of problems today. And there's a pull from applications and software at the top. So today we're having a lot of problems from the bottom as well as the top that is pushing us or kind of squeezing us to do in-memory computation, I would argue. So let me tell you the story of the technology side first. Why are we pushed from technology to have intelligent memory controllers that intelligently process the data? Why? Because our existing memory technologies are having a lot of difficulties today. DRAM, dynamic random access memory, is not scaling very well today. And I'm going to give you some examples of this. As a result, industry is finally examining controllers close to DRAM. And the industry is also open to new memory architectures. So these are some examples that were happening a few years ago. We have 3D stacked memories where logic layer has very high bandwidth and low latency access to memory layers. So we can take advantage of that for near memory computation. And there are other simple devices that people have put out where you can do processing in the row buffer, for example. And more recently, UpMem has produced a chip that can do processing, general purpose processing, near memory banks. And even more recently, Samsung has produced a more tailored processing in memory system where you can actually accelerate, multiply, and accumulate operations near memory banks as well. We're going to get back to these, but let me give you the story of why this is happening today. And the reason is memory scaling. Basically, we have a lot of issues with DRAM technology scaling. Memory scaling is not, well, at the bottom level at least. We have technology scaling is not going very well. And this is an old paper. If you're interested in some of the history of this, we have written this paper about 8 years ago or 9 years ago now that talks about why memory technology scaling is having problems today. So let me give you this reliability perspective. As the memory system scales, meaning as you increase the density of the memory chip, you reduce the size of the cell, and you put many more cells in a given millimeter square, for example. And because of this, memory is becoming much less reliable. This is data that we collected together with Facebook over the course of a year, more than a year actually. Basically, we looked at their data center. There are many data centers. There's a lot of data centers. So the confidence interval in this study is very high. And basically, the server failure rate correlates significantly with the chip density that's employed in the server. The denser chips lead to a higher server failure rate. Clearly, this is a correlational study. It's not causation. But we believe that there's a good link because the chips that are denser are having a lot more failures because there's a lot of noise that the smaller memory cells are subject to, and the memory cells are much closer to each other. So we're having a lot to actually solve these reliability problems. And let me motivate us a little bit more. Basically, we built these FPGA-based infrastructures to understand the reliability, latency, scaling issues related to memory. You can read some of these papers. I'm going to mention some of them. And this is some of the like mid-level infrastructure. And we open source this infrastructure. So if people are doing FPGA-based studies to understand memory reliability, latency, et cetera issues, we actually support them. And you can find this paper as well as our source code online. And many people are actually using it both in industry and academia. But I would like to point out one interesting study that's actually a hallmark, in my opinion, of technology scaling problems that we're having with the main memory that we have today. And this is called the Rowhammer problem. Essentially, today, at the software level, you can predictably induce errors in most DRAM memory chips. This is called the Rowhammer problem, as I said. And more than 80% of the tested DRAM chips were vulnerable when we did the study early on in 2012 or so together with Intel. And this is really the first example of how a simple hardware failure mechanism, device-level failure mechanism, can create a widespread system security vulnerability. And as a result, people who normally deal with software are writing articles like this. Forget software. Hackers are exploiting physics. And this is actually a very good characterization, in my opinion, of a problem that looks like this. So what's the problem? Basically, it's a disturbance error. Whenever you read a memory cell, you're disturbing adjacent cells that you should not disturb. But it's happening today because cells are too close to each other and cells are too small. So in DRAM, if you want to access a memory cell, you need to open an entire row, activate an entire row, which means that you need to apply high voltage to that row. And if you want to open some other row, then you need to apply low voltage to this row, meaning pre-charge the array. And as a result, you can read another row. Now, if you keep doing this repeatedly, apply high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, or activate pre-charge, activate pre-charge, activate pre-charge to the same row, which is a valid action, perfectly valid action that a memory controller can do. And real workloads actually do that, as we will discuss in a little bit. It turns out in physically adjacent rows, you get bit flips today. Clearly, this is not supposed to happen because whenever you read a row, you should not disturb any value. Basically, you get data corruption in adjacent physical rows. And we call this the hammered row, we call this the victim rows. And we basically showed that more than 80% of the DRAM chips that are manufactured by the 3 major manufacturers in the world today are actually vulnerable to this problem because it's a technology scaling problem that was not anticipated well, let's say. And these are some data. Basically, you can see that all of the chips that we tested that were manufactured between 2012 and 2013 were actually exhibited this row hammer problem. So let me quickly describe why this is happening. Essentially, there's electromagnetic coupling between the 2 rows. Whenever you activate one row, you also slightly activate adjacent rows. Clearly, there's a lot of low-level device-level explanation that I'm omitting over here. But at the abstraction level that I'm operating at, you're leaking data from some vulnerable adjacent cell little by little. And if you keep doing this hammering enough times, before the cells get refreshed, you leak enough charge from some vulnerable adjacent cells that you lose the data. So unfortunately, this is a reliability problem, but this is also a security problem, as we will discuss. Basically, a simple program can induce many errors. This is a program that we wrote and released at the time. A very simple, and it's a user-level program. What it does is it selects the addresses X and Y, and if the DRAM chip is, and it hammers them. And if the DRAM chip is vulnerable, you get errors. And we show that you could do this in Intel and AMD systems. Later works actually show that you could do this on any system with a reasonable memory controller. And this is a real reliability and security issue. It's a security issue because some malicious program can exploit these bit flips for malicious reasons. So basically, when we wrote the paper, we said that memory isolation is a key property of a reliable and secure computing system. And access to one memory address should not have unintended side effects on data stored in other addresses. I still believe that this is very fundamental. And we said that someone can take advantage of these bit flips that you're causing to take over your system. And later, Google Project Zero folks piggybacked on our paper, and they basically showed that problem. I'm not going to go over the details of this. This is actually very fascinating, in my opinion. This slide is copied and pasted from their blog post and Black Hat presentation that basically showed that they can gain kernel privileges with a user-led process by circumventing virtual memory protection. Basically, they do beautiful security engineering, and they induce these row hammer bit flips. As a result, they were able to write to the page table of a user-level process, and they were able to modify the page table at the user level without actually causing any, let's say, detection by the system. So you can actually gain kernel-level privileges. Later research actually showed that you could actually do a lot of other things. This is work by Tues that show that they can gain unrestricted access to systems of website visitors by inducing these through the JavaScript. This is actually a very interesting work that showed that they could gain control of a smartphone deterministically by inducing these row hammer bit flips in an Android phone. Other folks show that you could actually do this through a GPU in a much faster way. And you could actually do this through the remote direct memory access interface in a data center potentially, and take over a remote server. And I'm not going to go through this in detail. There are actually a lot of interesting attacks that people have developed. I will mention these recent attacks that talk about neural networks. So you may actually have very good neural networks. These neural networks may provide very good accuracy. But if someone actually takes advantage of bit flips, like row hammer, their accuracy can go down significantly, as you can see in this particular slide that I borrow from this paper. So basically, I think this sort of technology scaling issues are getting to the heart of what we really want to have from our systems. We want to have our systems intelligent, and we've built this machine learning infrastructure that are actually reasonably accurate, let's say, but can we trust them in the presence of these technology scaling problems that lead to bit flips? And these are clearly row hammer bit flips, but there are other bit flips that may be happening due to retention errors, read errors, write errors, etc. I think we need to solve these problems related to these errors. Basically, memory scaling issues are real, and they're affecting our applications, in reliability of our applications, as well as security of our systems. The question is, what do we do about this? So clearly, I can talk more and more about row hammer. This is actually a really interesting area. We wrote an invited retrospective paper on this. If you're interested, it covers a lot of issues from the entire system stack. But the solution to this, I believe, requires more intelligent controllers. Intelligence has to be added to the memory chips or the memory controllers. It doesn't matter where. And I think there are many, many proposals that are floating around right now. But we need to provide some security to fix these issues in a fundamental way. And that, I don't believe there's another solution to this, at least low-cost solution to this, without providing intelligent controllers. And this is one intelligent controller that we have designed and put out recently in the last HPCA. If you're interested, you can take a look at it. Rowhammer has not gone away. So since it's a technology scaling problem, it's going to become worse and worse. And we have done a lot of analysis related to this. Basically, it's becoming much worse today. Number of hammers that you need to do to induce these bit flips is reduced, and existing mitigation mechanisms are not effective. Unfortunately, the intelligence that is being put into the DRAM chips is not enough. Basically, DRAM manufacturers said, we solved the problem, trust us. But they didn't disclose how they solved the problem. As a result, we took up the challenge, and in this paper, we demonstrated that you can reverse engineer what the DRAM manufacturers put into their chips, and it can basically induce Rowhammer bit flips, even though the DRAM manufacturers claim their chips are Rowhammer free. Basically, to solve this sort of issues, we will need to be, let's say, rigorous, and we cannot rely on security by obscurity. We will need to be open, and we really need to rely on security by proof, let's say. Basically, we've been doing a lot of studies on Rowhammer more recently as well. The question is, can you actually identify chips that are vulnerable to Rowhammer with good enough testing methodologies? Unfortunately, the jury is still out there, and we don't know how to do this yet. And there are a lot of papers that are being written on this topic that I'm not going to talk about. The most recent papers, as far as I know, are in Micro 2021. They go a little bit deeper into the analysis of Rowhammer, into the sensitivities of Rowhammer, for example, and they go a little bit deeper into what the manufacturers do today and why it's not working. I believe there's more to come. I find this fascinating, and there's a lot of research in this area for those of you who are interested in doing research. And this is a good time to actually look into these sort of technology scaling issues. And I will finish this Rowhammer part with detailed lectures. You can take a look at a lot of lectures. There's a lot of information out there that you can take a look. Let me actually give a high-level perspective on this, like intelligent memory controllers and Rowhammer. We think of infrastructure as, we think of bridges as infrastructure, and humanity has been building bridges for thousands and thousands of years, right? Bridges are clearly critical infrastructures, and this is one example. This was the Galloping Gertie, which actually got destroyed like this because of a bit flip, let's say. You can read about it. And that's clearly a problem with infrastructure. Today, computing is a much bigger infrastructure than this, and we need to take computing much more seriously than we have been taking bridges so far, because computing is everywhere. Bridges are still small number compared to computing devices that we're going to rely our lives on. And this is another example of a bridge, let's say. If these people have a bit flip on this bridge, in the next second, they may not be very happy. So I believe security is about preventing unforeseen consequences going into the future. And we really need to develop techniques in our computing systems so that our computing systems are fundamentally secure, safe, and reliable. This example from Mr. Bean driving a self-driving car much before self-driving cars were popular is an example. Maybe this is a litmus test, right? Can we trust our computing system so much that we could drive it like Mr. Bean over here? So I think the part of the answer goes from intelligent memory. It's basically, memory will have a lot of issues going into the future, but we need to design it to be intelligent. We need to design it to have controllers that can avoid these problems. And I think for this, we really need intelligent controllers. So that was an example from the push from technology. Basically, the technology is pushing us to have intelligent controllers that can basically understand what's going on in memory in the applications and to fix these reliability and security issues. I can give you another example from refresh, but we don't have time on this. Data retention is becoming much worse, for example. And all of the memory technologies that are interesting today are having these problems, not just DRAM. Clearly, DRAM is a huge market today. Almost all of the main memory in computing systems is DRAM. But even emerging technologies have this sort of issues. So that was a push from technology. Technology is pushing us to do something intelligent in our systems, such that memory control should not be dumb anymore. It should be intelligent. It should be fixing these problems proactively. Let's take a look at the top of the computing stack. Systems and applications are telling us the same thing, perhaps even more strongly, let's say. Data access today is a major bottleneck. Energy consumption is a key limiter, and data moment energy dominates computation energy. I'm going to give you examples on each of these. But before that, the question, in my view, is actually much more pressing than what we have today with technology scaling. Do we want a world that looks like this, that we can live in, that we can actually leave it to future generations in a sustainable manner? Or do we actually want to pollute this world with the way we make our design decisions in our computing systems? Yes, computing system is not the only reason why we are having climate issues, but it's going to be a much bigger portion of the energy consumers in the world going into the future. So I would say that we would like all of them, meaning we would like high performance, energy efficiency, and sustainable at the same time. We cannot give up on high performance because we have a lot of problems to solve, but we want to get high performance with energy efficiency and sustainability. But the problem is we have a design decisions at the fundamental part of our computing systems that makes us go against all of these, basically. Our current design principles cause great energy waste because we're moving data all over the system. Data access is very costly today from memory or storage, or sensors to the computation units, but we're exercising it continuously, basically. We have to move the data before we can process it. Clearly, this is causing great energy waste. It's causing great performance loss also, because we know that data access is costly and we're moving the data in the first place. Okay, fine. We're designing our systems to actually avoid this performance loss. We're actually adding a lot of multi-threading capability, a lot of prefetching capability in software and hardware levels, a lot of auto-order execution capability, a lot of caching, many levels of caching at many levels. Unfortunately, these are adding to the energy waste. So we're in a vicious cycle right now. Data access is causing energy waste. To overcome the performance loss, we're adding even more energy waste because this infrastructure, this hardware and software infrastructure that we built to tolerate memory accesses is actually not working today in many applications. Today, if you really want to overcome the energy cost of data movement, you need to have a lot of locality in applications. And in many applications, we're not having that locality. In fact, many applications are increasingly random access, irregular. As a result, the locality is not being exploited. So all of that infrastructure that we have put in our systems is they're adding complexity and wasting energy. And if you want to solve this vicious cycle, we need to find the problem at the heart of the problem. Today, processing of data is performed far away from the data. And I think that's the main reason, main thing we need to tackle. Basically, if you look at a computing system, I showed you this picture before, computing unit is heavily optimized, but everything else is not that optimized if you think about it. Well, clearly there's work in this area. I'm not saying that there's not work in this area, but the amount of effort that we have put into the computing unit and the computing centricity of the systems is really hurting the overall system today. So yet we know that actually this is a problem. This is actually a person who has dedicated his life into designing compute-centric systems, Dick Seitz. Right now he's working on data centers, which is actually a different story. But Dick Seitz was the chief architect of alpha processors. His team designed the fastest alpha processor of its time, fastest processor of its time, actually. And after they designed this, he wrote a one-page article at Microprocessor Report, whose title is "It's the Memory Stupid." Basically, he said that we designed this processor. It's able to finish 4 instructions per cycle, but in real workloads, it's finishing 1 instruction every 4.7 cycles. Basically, it's operating at 5% of its efficiency. And he finishes the article by saying this: I expect that over the coming decades, memory subsystem design will be the only important design issue for microprocessors. And I agree with him. Fast forward 10 years, this is data from my own PhD thesis. We worked together with Intel, analyzed many applications. Basically, a state-of-the-art processor at the time was waiting for data most of its time. These are cache misses. If you're interested, you can read that paper also. Fast forward 10 years later, if you don't believe me or believe Dick Seitz, since everybody believes Google today, for good or bad, Google actually published a very nice paper in 2015 that shows that all of their interesting workloads, you can see some workloads that people may be using, search, Gmail, indexing, video, etc. They're all memory bound, basically. The processor is doing useful work only 10 to 20% of the time. Most of the time, the processor is waiting for data. And there's more analysis. So basically, we have a problem with processor-centric design today. We have grossly imbalanced systems. Processing is done only in one place, and everything else stores and moves data. As a result, data moves a lot. This is energy inefficient, low performance, and complex. And also, we have an overly complex and bloated processor, as well as accelerators. When I say processor, I would also mention that accelerators are very similar. So if you think about FPGAs, GPUs, or machine learning accelerators, they also need to get the data from processor and from the memory system. And they also have these complex hierarchies and mechanisms, which are energy inefficient, low performance, and complex. So as a result, we have this picture that I showed you earlier. Most of the system is dedicated to storing and moving data, yet still a system is bottlenecked by memory. Let me give you the energy perspective quickly. This is data that I borrow from Bill Daly. It's old data, but I think the conclusion is the same today. If you look at an arithmetic operation, is 20 picojoules in terms of energy. A memory read or write is 800x more costly. So if you look at the system design today, basically a memory access consumes 2 to 3 orders of magnitude the energy of a complex addition. The question is, of course, does it really make sense to bring the data and pay the energy cost of 2 to 3 orders of magnitude to do a very simple, energy simple operation? So I would argue that this is actually a great thing that enabled that has been enabled for us by technology scaling. If you look at this picture 70 or 80 years ago, when von Neumann was designing his architecture, for example, memory access was more costly than computation. Over the course of 70, 80 years, the same technology scaling that has been causing problems right now in terms of DRAM that we discussed has made computation a lot cheaper, but the interconnects and the memory did not scale. As a result, the picture has reversed significantly. So the design decisions that we made in 1940s, for example, when we were designing the first computers, don't hold because the energy cost of interconnect and memory system is much higher than energy cost of computation. So I believe we need to rethink. And if you actually do the calculations, to overcome the energy cost of this data access, you really need to have a whole lot of locality in your caches. And many workloads today do not have that sort of locality. Okay, so if there's a lot of other papers that are written that I'm not going to talk about over here. As a result, we have system level issues, like more than 60% of the total system energy is spent on data movement today. So I would argue that we do not want to move data. We want to be judicious in moving the data. We need a paradigm shift to enable computation with as much as possible minimal data movement. We want to be able to have the option to compute where the data resides. We don't want to do it all the time, perhaps, but we want to have the option to be able to compute everywhere. And we want to make the computing architectures more data-centric. So we need to have a paradigm shift. And memory is a good place to actually enable this paradigm shift. There's, of course, storage, which people are looking at. We're also looking at. I don't have time to talk about it. We need to process data inside the network, maybe inside the tape in other devices, inside the caches as well. Basically, we want to enable computation capability anywhere in the system as opposed to just the processor. Let's take a look at memory. Memory is very special, in my opinion, because today we have a lot of workloads that are designed for in-memory systems. For example, we have in-memory databases that fit the memory. You don't go to storage as much. We have in-memory graph processing engines. We have in-memory media processing engines, in-memory machine learning engines. These workloads are designed to avoid storage as much as possible. You don't always do it, of course, and you have sometimes one-time cost from the storage to memory, which is also important. I'm not going to ignore. I'm going to ignore that for now. But memory is special because we have these workloads that are in memory most of the time, but we cannot compute in memory. Basically, we would like to enable the processor to say, memory, can you do this computation for me? And the memory says, yes, and here's the result. And then the processor can do other things. We want to have memory as equals to the processor, if you will. We don't want to get rid of the processor. Processor-centric paradigm still has its benefits, but we want to partition the computation such that you can do the computation where it makes sense. Clearly, this opens up a lot of questions. I'm going to talk about several of these questions in the rest of the talk, but there are a lot of interesting questions, interesting research questions as well. How do you design the compute cable and the memory and the controllers? How do you design the processor core and in-memory units? How do you design the software and hardware interfaces? Today, we don't have a lot of those. How do you design the system software compilers and languages to enable a computation paradigm like this? And how do you design the algorithms to fit the memory devices? As well as how do you revisit the theoretical foundations of computing? Basically, we need to revisit the entire stack of computing today. I say theoretical foundations, and I must actually mention this because we're talking about computer science here. Computer science is based on analysis of algorithms that actually count operations. So if you look at the big O notation, big theta notation, analysis of algorithms is really looking at operation counts, which really is processor-centric, compute-centric. There's the data-centric part of the paradigm is not there. So if you think about, if you want to design much more data-centric systems, maybe we should really look at algorithm design and algorithm theory of algorithms in terms of how much data movement they cause, how much memory space they lead to. So this sort of information is not there in the design of our algorithms. That's why I think this is a paradigm shift. We really need to rethink everything we're doing with computing today if you want to do processing inside memory in the best ways. Okay, in the rest of the talk, I'm going to give you some examples of this. But I'm not going to be able to go into a lot of detail. If you're interested in a lot of detail on this, we have written this long article that talks about an overview of processing in memory that gives you a historical perspective as well as the current perspective. And this talks about, you can see that we will talk about processing using memory, processing near memory, and we'll talk about adoption issues, which are also important, but we will not have time to go through everything in detail. But I will argue that today we need to think differently from the past approaches. I think thinking differently leads to two different new approaches. One is processing using memory, the other is processing near memory. And these are two fundamentally different approaches. Processing using memory takes advantage of the underlying memory circuits and basically uses the operational characteristics of memory circuits to do computation. How can we think about the memory circuit and how can you take advantage of it to actually do computation and not just storage of data? And I think this is fascinating because all memory devices that we know of are capable of doing some amount of computation, the way we design them today. In fact, even off-the-shelf DRAM chips, you can take them and you can violate them some timing parameters, and you can actually mimic some of the operations that I'm going to describe to you in a little bit. You can do data copying, you can do data initialization, you can do simple bitwise AND and OR. This is fascinating because these memory chips are not designed for that purpose. They're designed for storage, but they can actually do computation. Now imagine what we can do if we actually go and design them specifically for both computation and storage. And I think that's going to change the paradigm. Processing near memory is more conventional, in my opinion. Today, memory is here, processor is here, they're far away from each other. And processing near memory says, okay, can we put the computation units closer and closer, 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 take advantage of some interesting technologies, if you will, such that at some point, memory and processing gets merged together, but they're different units still. And I think we need to look at both approaches. Now, let me give you the first approach in a little bit. First approach actually is significantly different because it will actually have significant impact on programming and algorithm design as well. The second approach, I think we can adapt our existing programming and algorithm design into the processing near memory paradigm. So there's more detail in the paper. Now let's jump into the first approach. So the idea of the processing using memory approach is, can we take advantage of the operational principles of memory to perform block data movement and computation in memory? We can exploit internal connectivity in the memory chips today to move data. We can exploit analog computation capability of the memory cells and the bit lines, etc. I'm going to give you examples of both. And I'm going to start simple, kind of cheat a little bit. Even data copy and initialization. These are actually important workloads. We do a lot of copying and initialization of our systems. Imagine you have a 1 terabyte database and you're initializing the memory. It takes a lot of time, actually. Imagine you fork a process, you initialize memory. Even if you do copy on write, it takes a lot of time, actually. And Google actually showed that in their data center workloads, data copy and initialization, these two function calls, only these two function calls occupy 5% of the cycles. So how do we do data copy today? Initialization is actually a special case of copy, so I'm not going to go into the details of initialization. But if you want to copy a simple small page, 4 kilobyte page in memory from here to here, today you have to go through the processor. You have no other option. You have to at least go through the memory controller. And this is the low, sorry, somehow I skipped. Basically, today you have to go through the processor. It's high latency, high bandwidth consumption, high energy consumption. But future systems should do better. Basically, in-memory copy in future systems should basically tell the memory do the copy internally and don't disturb anything else in the system. This way, we can have low latency because we're exploiting internal connectivity in the memory, and we're not exercising the long buses over here. No bandwidth utilization, no data bus utilization in the most important system resource that we have, the memory bus. No cache pollution, but you can eliminate that today with memory controller optimizations, DMA optimizations, for example, and no unwanted data movement. And I will show you that with a very simple modification to the DRAM system, you can get rid of a lot of latency and a lot of energy. You can reduce the latency by more than 10x, and you can reduce the energy by, let's say, close to two orders of magnitude today. And the idea is very simple. I'm not going to go into the details significantly, but any memory technology can actually enable this. In DRAM today, off-the-shelf DRAM chips can enable this by doing what I described, by violating the timing parameters. But basically, if you want to do in DRAM row copy between two rows that share sense amplifiers in DRAM, you first activate the first row, which brings the data into the sense amplifiers. These already exist today. And then you first activate the destination row, which deactivates the source row and brings the data from the sense amplifiers to the destination row. So by using existing circuitry inside DRAM, the row buffer, the bit lines, sense amplifiers, you can do copy from one row to another row with minimal modifications if you want to do it completely reliable to the DRAM chip. So the idea is very simple, negligible hardware cost. And this leads to more than 10x reduction in latency and more than close to, let's say, 2 orders of magnitude if you optimize it, reduction in energy in terms of data copy. And ignore these bars over here because these bars actually enable data movement across different banks, across different subarrays, etc. I'm not going to go into the details, but these bars have reduced since this paper was published. They're close to the red bar. Basically, you can design the memory system such that it can do the data copy internally very efficiently with support from the memory chip. And I'm not going to go into the details, but this is one of the papers. And clearly, there are a lot of extensions that have happened, follow-up work. You can basically move data at smaller granularities. You can do faster inter-subarray copy, better interbank copy, etc. And I'm just going to show you some of the papers on this topic. And if you're interested, there are clearly lectures on this topic also. But let me talk about the mindset. Basically, this mindset says memory is actually good at doing data copy and initialization internally. So why don't we design it to do it really well? Have the specialized computation capability inside memory. And memory is an accelerator. We were used to building a lot of accelerators. They all have an Achilles heel. And that Achilles heel is the memory bus. Basically, the memory bus is limiting all of these accelerators. Why don't we design an accelerator over here that actually doesn't have that Achilles heel over here, which has low latency and high bandwidth access to memory, low energy access to memory. And memory can be actually programmed similar to a conventional accelerator this way also. Okay, maybe I cheated, if you will. That was data copy initialization, but we can actually do truly in-memory computation as well. We can support in DRAM bitwise and or not and majority functions at low cost. And the idea is to use analog computation capability of DRAM. activating multiple rows actually performs computation. I'm going to give you a little bit more detail in this. And you get, as a result, 30 to 60x performance energy improvement in bulk bitwise operations. And this paper details it significantly. And emerging memory technologies actually enable even more opportunities. They can do what we discuss in this paper, but they can do even more. They can, for example, do matrix vector multiplication in a crossbar array structure. And because they're not destructive, reads are not destructive, you can operate on data with minimal data moment in these technologies. Let me talk about DRAM. And this is, again, applicable to emerging memory technologies also. But if you look at 3 DRAM rows, 3 DRAM cells over here, you can do some fundamental operations by concurrently activating those 3 rows. And imagine that these are just 3 rows, each can be 8 kilobyte wide, and you may actually have thousands of subarrays. So you may actually be doing this operation on more than 8 million, 10 million bits in a single DRAM chip. So the operation is triple row activation. You concurrently activate rows A, B, C. I'm showing 1 bit over here, and this is the bit line, which means that you connect the bit lines, the cells to the bit line, which means that based on fundamental circuit principles, if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. This is a bitwise majority function. And you can actually design your algorithms to operate using bitwise majority. Now, this is not enough. If you actually want an inversion function also. If you have bitwise majority plus an inverter, that's functionally complete. But you can also rewrite this Boolean equation. Set C to 1, you get the OR of A and B. Set C to 0, you get the AND of A and B. So basically, you can have a functionally complete Boolean bulk bitwise execution engine inside DRAM. And if you have a functionally complete engine, then the question becomes, how do you redesign your algorithms such that you can operate, you can express them in terms of these bulk bitwise operations? And that's essentially what we did in this work. Some of the algorithms, of course, are more amenable, or at least our thinking is more amenable today, because we have a lot of bitmap indices, bitweaving, database queries are doing, some of the databases are designed using these bulk bitwise operations. Web search similarly is designed using bulk bitwise operations, DNA sequence mapping, etc. But some of the algorithms we need to rethink so that we can take advantage of it. But let me give you an example from databases. If a database is designed to maximize bulk bitwise operations, and you map it to a substrate like Ambit, like we discussed earlier, you get more than 4 to 12x performance improvement in many queries. And performance improvements actually increase with the data set sizes that you have. I find this fascinating. Then the question becomes, how do you rewrite your algorithms, or how do you ease the programmer's job to enable a substrate like this such that the programmer can actually take advantage of this massive bitwise parallelism that exists in your DRAM device? I'm going to talk about that in a little bit. But we've written papers on this topic. Clearly, you can take a look at them. This is one of the recent papers where we tried to tackle the question, how do you ease the programmer's job? This was published in ASPLOS. I'm not going to go into details. I'll give you some high-level ideas. Basically, it's an end-to-end processing using DRAM framework that provides a programming interface, ISA, and the hardware support so that you can efficiently compute any complex operations. So you can imagine any complex operation, let's say convolution, and this convolution gets implemented by a design automation process that I will describe quickly in the next section. And the memory controller provides a convolution function internally using DRAM commands. And whenever the programmer uses a convolution function in the ISA, for example, it could be added, then this function gets invoked in the memory controller that basically sequences through a DRAM command, like triple row activation, like O-clone operations that we discussed, so that that convolution function is actually efficiently implemented in memory. That's the idea. And arbitrary operations can be computed this way. And basically, we have minimal changes to the DRAM architecture that I just discussed earlier. And this is a process, basically. User input, user has a desired operation. It can be expressed as a functionally Boolean complete circuit. And then we actually generate majority logic, majority and not. And this gets expressed in terms of DRAM commands. And now you have a microprogram that is part of the DRAM controller. And that microprogram gets called from the program using a special instruction that's added to the ISA. And that's the idea. Now, if you do this, actually clear some of the burden is reduced from the programmer now. The system has the burden, but the results are quite good as far as what we're still working on, of course, to make it even better. But you can see that we can achieve more than the throughput of a CPU and a high-end GPU, as well as energy efficiency. And I think there's more work to be done to actually generalize this to many, many, many programs going into the future. So similar to this, actually, you can have physical unclonable functions. I don't have time to talk about this, but physical unclonable functions in DRAM. You can have a security infrastructure in the DRAM side, basically. You can have true random number generators on the DRAM side. And I don't have time to talk about this, but this is exploiting, again, the operational characteristics of memory to actually generate true random numbers. And if you want to execute, for example, a security critical application, you should really generate true random numbers on the DRAM side. And this is a paper that's coming up related to this topic. Okay, Now, with the given time, I will quickly talk about processing near memory and then talk about adoption issues. As I said, processing near memory is fundamentally different from processing using memory. It's similar to how we design systems today. So today we actually have graph processing workloads, and I'm going to talk about this from an application perspective. Graph processing is clearly very, very important in our lives. Many machine learning frameworks have it, many bioinformatics frameworks have it. Clearly, many social media and Wikipedia, for example, that many people are using is based on graph processing. Unfortunately, scalable graph processing is challenging. It's really a memory-bound problem. You can throw cores at the problem, but it's extremely inefficient to improve performance. Why? Because you have frequent random memory accesses and little amount of computation. So this is a great fit for processing near memory. Put the processors closer to memory, at some point immerse them with memory, and these processors do not move the data as much, but they move the instructions to the data. So we're talking about essentially a message passing system that I will describe. So a technology that enables this sort of approach is 3D stacking. You have a logic layer underneath memory layers, and logic layer can have many processors that can potentially be specialized for graph processing or machine learning or something else. So since this is actually a whole system design, I don't have time to go over the details of it. But basically in the logic layer, you can have a distributed system, which is programmed using message passing. And it can basically lay out your graph nodes on top of it. And basically you don't move the graph nodes. Whenever you want to do an operation on a graph node, you send a message to the processor that hosts the graph node. You can see that these are all in order, simple in order cores. And these are programmed using message passing. It's essentially a distributed system in the logic layer. And then if you want to scale up the system clearly, you have many more of these cubes, if you will, logic plus memory chips interconnected with each other. And you can think of this as a primitive GPU today. If GPUs were like primitive in 20 years ago, this is a primitive GPU. It's a message passing based system, physically addressed. You offload your graph processing computation, and hopefully data doesn't move a lot in this system. And we actually ensure that data doesn't move a lot. I don't have time to go over this in detail, but proximity to data of the logic is what enables this system. Okay, and as a result, you get a lot of bandwidth. Basically, because your processors are tightly integrated with the memory, you get 8 terabytes per second bandwidth compared to all of the existing systems that we had at the time. Let me give you some promising results. So as a result, on 5 graph processing algorithms, you get more than 10x performance improvement. And again, this is data from 2015. Later works actually improved on our work. They did better load balancing in the system. They did better data mapping. They did better scheduling. They did better interrupt handling, etc. And as a result, today, actually, you can get close to 100x improvement on these 5 graph processing algorithms with the research that was done since then. I think this is significant. And energy reduction is also significant. We demonstrated more than 8x, but today we're at actually close to 2 orders of magnitude if you specialize your system for graph processing. And if you're interested, this is the paper that originally introduced the idea. Now, let me quickly talk about more general purpose. So clearly, this is a specialized system, but can we actually do this in a general purpose manner? That's what we tried to do with Google in the work that I mentioned briefly. We wanted to look at consumer devices that are actually critical in terms of energy. And we wanted to look at these 4 popular consumer workloads in these devices. They're clearly Google workloads, but you have equivalents of these workloads from other companies. And we quantified the data energy cost of data movement. I mentioned that earlier. More than 60% of the entire system energy is spent on data movement. And we actually wanted to use processing in memory to reduce the data movement. But we want to do the function offloading. Basically, the programmer says this function should execute in memory. And we have the system infrastructure to support this. And how do you do this? Basically, if you want to be able to do this, the second observation helps a lot. A significant fraction of the data movement often comes from very simple functions in applications. And we design lightweight logic to implement these simple functions in memory. They can be implemented in small embedded low power cores or small fixed function accelerators or some FPGA-based reconfigurable logic. I believe actually a heterogeneous system design is useful for this. And as a result, we found out that you get significant performance energy improvements. It's not as impressive as 100x. It's more than 2x though. But the programming effort for this is much less, if you will. So if you're interested, there's a lot of workload analysis in the paper that I don't have time to go over. But for example, with TensorFlow Inference Engine, more than 50% of the inference energy is spent on data moment. And more than 50% of that data moment is coming from 2 simple functions that prepare data across layers, for example. And the paper has a lot more detail. So I can give you a lot of examples, but since we don't have time, I'm going to get toward the conclusion over here. But there's a lot of evidence that shows that if you do processing inside memory and near memory, you get a much more efficient system. And this is an example from GPUs. There are other examples from pointer chasing workloads that are actually difficult to do. The dependent cache misses, prefetching mechanisms, climate modeling. We can actually use FPGAs today to actually do better climate modeling near memory, approximate string matching, time series analysis, neural network inference. This is a recent paper that we did with Google, but I don't have time to again go over this, but you can see that if you design data-centric accelerators for neural network inference, your performance energy can improve by more than 3x. And this is a heterogeneous accelerator that contains 3 accelerators. One is compute-centric, 2 of them are data-centric. Okay. As I mentioned, FPGAs are actually quite interesting to do near memory acceleration today as well. So these are all examples of revisiting the entire stack, but I believe these are also examples of getting there step by step with simple changes as opposed to changing everything that we have in our systems. And I think there are other simple changes that can happen with simple processing in memory, with PIM-enabled instructions that I don't have time to go over. And this paper talks a lot more about them. Okay, let me give you some hope in terms of the industry. So when I was giving this talk, let's say 5 years ago, or 6 years ago, or 7 years ago, this system didn't exist, for example. But now this system exists. This is a system that's designed by the UpMem startup in France, in Grenoble, that we're collaborating with. These folks, what they did was they basically took a DRAM chip, and each DRAM bank, they put a processor. And this processor is programmable. It's a general purpose processor. Now you can actually do a lot of offload a lot of applications to this processor. And these are real systems that we're working with. You can see a picture of a system that has more than 2,500 of these processors inside DRAM. And you can see that this is a simple processor over here that uses fine-grained multi-threading. You can actually run 16 threads inside this processor, etc. That I don't have details, that I don't have time to talk about the details. But we've written papers about this, and we actually released benchmark suites about this. If you're interested, you can find the benchmark suite, contribute to it, and these are some of the papers that talk about this system. So what we find is that these systems are very good at some workloads, but they're not very good at some other workloads, because some other workloads are extremely computation heavy, and we cannot put a lot of computation near the memory. Over time, this will evolve, of course. We can put more computation near memory, and these systems will become much more powerful. But today, these systems are not that powerful. So you need to make a decision as to what to offload to this system. And there are a lot of work that we have published that describes what you should offload and what you should not offload. Again, I'm going through this relatively quickly. And we have actually other work that talks about what you should offload and what you should not offload to the near data processing engines. We have characterized many applications for many distinct domains in this work, for example. And we categorize the memory bottlenecks in terms of whether you have the bottleneck in terms of bandwidth, latency, cache capacity, or your compute bound. You can use these tools to actually identify the bottlenecks in your application. And this can actually aid you to partition your application between the CPU, for example, and a near data processing engine like UpMem, for example. And this is all open source. Again, you can find information about it. There's a lot of research that can be done on top of it, in my opinion. And I'd encourage the people to think about these research directions if they're interested. And one last thing that I will mention is Samsung, the biggest DRAM manufacturer, is finally pushing with processing in memory as well. Recently, they have announced in 2021 that they're putting functions inside each bank or next to each bank that can do computation, specifically machine learning type of computation. But over time, they have plans to generalize it. So this system basically has a small pipeline near. You can see the instruction set architecture over here, small pipeline that can execute this instruction set architecture, which is really tailored for multiply and accumulate and multiply and add operations, as you can see over here. But the important thing is this system exists, and people are actually doing experiments on it, and they're writing papers about it. So these systems are becoming real today, which is actually important. There are also other systems that I don't have time to talk about. These are some module-based processing systems. So I can go on and on about PIM, but I know we're already out of time. I will just mention that there are lectures. You can find information about it, and there are also tutorials on PIM that we have given that you can find online. So this concludes, I think, the major part of my talk. How do we design fundamentally energy-efficient architectures? I think the answer is data-centric. How do you design fundamentally high-performance architectures? I think the answer is, again, data-centric. And we really need to minimize the data moment in our systems. So clearly, these systems require a lot of adoption issues, and this slide lists a lot of the adoption issues. A lot of them are related to software. You can see it's about functionality and applications. It's about programming. It's about system and security support. It's about runtime and compilation systems to enable more effective integration with the system, as well as programmers, as well as system designers. It's about infrastructures to assess benefits and feasibility. I believe there's a lot to be done. We need to revisit the entire stack, but all can be solved with a change of mindset. And we need to change our mindset from processor-centric. We should not think about processor-centric. We should think about data-centric going into the future. And I think if we actually think that way, we can enable much more intelligent platforms, new medical and health platforms that can take advantage of systems that I showed earlier, and that can maybe revolutionize our lives. So as I expected, we won't have time for the next two parts. Data-driven, self-optimizing computing architectures are also important. They're part of the equation. Data-aware expressive computing architecture is also part of the equation, but we do not have time for that. But if you're interested, there's a lot more information on those in this tutorial that I gave in the International Electron Devices meeting a couple of years ago. Let me conclude. As I promised, I was going to talk about data-centric systems, but data-driven and data-aware are also important. But I believe it's time to design principled system architectures to solve the data handling problem. And we have a huge problem with data handling today. We want to design complete systems to be truly balanced, high performance, and energy efficient. And I think that requires us to think our systems and design our systems to be much more intelligent. And if you want intelligent systems, I believe they need to be data-centric, data-driven, and data-aware. And this requires us to enable computation capability inside and close to memory, as well as other parts of the system. I believe this can lead to orders of magnitude improvements, and I've given you some examples of this. Some of the examples were 2 orders of magnitude, for example, in terms of both performance and energy. It can enable new application and computing platforms. It can enable a better understanding of nature, because I think fundamentally nature is data-centric, data-driven, and data-aware. It's not processor-centric, and who knows what else. And I think to be able to do this, we need to have, in my opinion, better mindset about architectures, and maybe better questioning about what are we doing in our architectures? Are we really designing architectures that are truly intelligent? Or are we violating some fundamental principles that we're observing in nature that are enabling intelligence in humans? I'm not claiming humans are the most intelligent beings or anything, but clearly we're doing some things that are much better than computing today. But maybe not everything better than computing today, of course. But I think to get there, we need to revisit the entire stack. And we need to exploit good principles. There are many principles that I touched upon in this lecture. I didn't mention many of them. But more than anything else, I think we need open minds, meaning change our mindset such that we have a memory-centric mindset or data-centric mindset. And if you're interested in this, there's a short paper that I wrote, invited paper again in Date, that talk about these principles in a much more compact fashion. And I mentioned that there are a lot of things that we put out, but I think at this point, I'm going to acknowledge people who have supported this research. These slides will be available. I'm happy to send them to the organizers. But I'll acknowledge people who funded this research. This research would not have been possible with these people who fund the research. And I'll acknowledge more than anything else my research group and collaborators, some of which are actually at NTUA right now, for enabling a lot of this research. And if you're more interested in our research, you can find some newsletters that we put out. And these are some interviews, etc., that you can find. And all of the things that we have put out that I mentioned are actually online. If you need something that's not online for some reason, please email us and we'll try to get to it as much as possible, as much as we can, actually. So thank you very much. And we're a big believer in open source. I must mention that before we conclude, actually. We put out a lot of things online, open source. So hopefully people in the world can do the research and can basically enable us to build much better, much more intelligent systems going into the future. So thank you very much. I'm a little bit over time. I understand that. I apologize, but I'm happy to take any questions, either online or offline at this point. Thank you.
Thank you, Onur. I do have time for a couple of questions, Harry?
Sure, yes.
Okay. Anybody in the audience? Let me ask one question. So, Onur, I know the computation parts of this work. I follow it, obviously. A lot of acceleration is happening on the physical domain, actual memory, and all the rest of computer science is moving as far away from the hardware as possible with things like, starting from operating system and virtual memory, all the way to languages that are very, very, very high level. So how do you bridge the gap? How do we train people to do all these nice things they want to do in the high level, but also keep an eye on the efficiency of the low level?
Yeah, that's a great question, Yannis, and it's probably a question that the real answer would lead to billions of dollars, let's say. but I think maybe there are multiple ways of thinking about this. One is, yes, it's true that a lot of computer science is moving away from the low level. And we have these very high-level frameworks, and that's good, I think. We would like to keep them as much as possible, but it's leading to a lot of inefficiency also. How do we get the efficiency? So also a lot of computer science is looking into these, I think, merging of hardware and software today. So if you look at companies like traditional companies like Google, Microsoft, Amazon, etc., they're all building their own chips. They're all building their own accelerators. So it's true that there's a push towards more efficient programmability in parts of them, but even the very traditional computer science powerhouses, let's say, they're also moving to this hardware-software co-design paradigm internally. Yes, maybe not all of their programmers are aware of this, but a good chunk of their programmers are actually trying to understand what's going on in hardware. I believe that this will continue. Maybe a bigger fraction actually will do hardware-software co-design, and people will actually figure out how to have many people looking at hardware and software. But I agree that we cannot expect this from the everyday programmer, like more than 90% of the programmers. The way I believe things will work out is for those, a good fraction of people, while I was at Microsoft, we used to call these people, let's say, Einsteins, geniuses. These are genius programmers. And there are some Elvises also who are quite good at programming, but the general programmers are not the best, let's say. These Einsteins and Elvises will actually provide the infrastructure that's extremely efficient and will enable these higher level programmers to actually take advantage of these hooks at the hardware level with the right interfaces. I don't believe we found the right interface. For example, I don't believe Python is the right interface to do efficient computation for machine learning, right? Everybody's moving away from Python. If you want to do extremely efficient training of data, you need to actually move it to lower levels and optimize it with the hardware-software co-design. So as long as we find the efficient interfaces to call from Python, for example, or some other language, I'm not taking sides in languages over here, we can still maintain the programmability advantages at the high level, while also having a good base of, let's say, engineers and researchers who really understand what's going on. And again, I don't think we expect everyone to be able to do low-level optimizations. I think the answer is really from the interfaces side. People who know how programming, they should know what to express, but not necessarily how to take advantage of things underneath. Does that make sense?
Okay, yeah, thank you. Any other question? Let me check the chat here. I don't see something. Okay, then, Onur, many thanks.
May I ask something? Sorry, I had the mic closed.
Yes,
I'm not very familiar with this area. I'm mostly in the top, let's say, part of the algorithms, but I appreciate that work very much, and thank you for this stream of information. Great talk. I saw many improvements in the times X factors in several points of your work. Impressive improvements. I was wondering how well do these scale? Do they scale? Oh.
Thanks, Aris, for the question. So when you say scale with the data set sizes? Yes. So yes, basically they do scale. Of course, the limitation is, so what I have presented to you is mostly within a memory chip. And you can scale it by techniques that we currently use, like replication and having many memory chips, many processing units. So all of the understanding that we have developed in distributed systems, distributed algorithms can enable us to scale to many dimensions. Clearly, I don't believe that they will scale with a single memory chip. No question about that. A single memory chip is not enough for very large data set sizes. But I think we have a good idea of like distributed systems theory and algorithms today that can take advantage of the substrates that we discussed and amplify it to the higher levels. There's still some research that to be done in this area, I think. For example, scalability is limited by data movement across the chips and synchronization that you do across the chips. And I think there needs to be research in those, let's say, I call these pain points, synchronization and data movement across these massively parallel chips. But I believe those scalability issues can be solved over time as well.
Thank you very much once again.
Thank you.
Okay, then let's thank again Onur. Onur, I hope we see you in person soon in another one of these events.
Yeah, thank you very much, Yannis. I hope in Samos as soon as possible.
Yes, yes.
Yeah, take care. Thank you.
Thank you. Back to you.
So, yeah, thanks once again for this great talk. It was great to have you here, Onur. And let's move to the next talk. And by Yannis Kalantidis, I will ask Stefanos Kolias, I see he's around, to present next speaker.
Thank you, Aris. Thank you also for the organization of this excellent event where we're trying to investigate new challenges dealing with our research and the research we're performing in the computer science in our division. And it's my great pleasure today to be able to introduce Yannis. Yannis has been one of our not only undergraduate, but also PhD students who finished their PhD here in Greece in our lab in 2014. And we had a great collaboration in the lab with Yannis and the whole team we had at that time. Maybe I just give you just to put the framework of what we have been doing. From my personal experience, I have been involved in about 45 PhD studies implemented in our lab in the school. About 15 of these young scientists now are our colleagues, our academics in universities and in research centers, and maybe a bit more in Europe and US. Some of them have been working with big companies well known in our field, and they have done it either in US or in Europe and so on. And the rest have been working in companies or organizations in Greece. So we were very happy to see this evolution of our graduate student. Yannis specifically is one of the persons that have been involved with really big companies and working in the state of technology the last few years. Yannis completed his PhD about in 2014 with us. And then I think just after that, he left for the States, where he was involved and he participated as a research scientist in Yahoo Research for 2 years, I think 2015 to 17. Then he moved to Facebook AI, again in the US, for 2 years more, 2017 to 19. And I think by that time, you know, this evolution is very interesting because Yannis has finished his PhD mainly in computer vision applications where we're trying to provide efficient implementations of analysis of formation, sets of information, and so on. In this way, I think by 2019 in Facebook AI, he got more involved with video understanding, with deep neural networks, deep learning. And this is, it shows that he was really involved in this high expansion of technology in this field in the last few years. I think in 2020, Yannis moved to NAVER labs in Europe. So we have the whole scene of his evolution after he left us. And I think Yannis has done a great job. He has published papers in all top level conferences like CVPR, ICCV, NIPS. He has also papers in the major IEEE journals like PAMI and so on. So I think we have, it is a great pleasure that we have him with us today. And as you see, his talk will be in this new field that we are dealing the last few years. That means representation learning, self-supervised learning, and generalization. It's my great honor that I have that Yannis is with us today. I'm very glad to introduce him and have his talk, to hear his talk now. Thank you.
Thank you. I hope everybody can hear me. Thank you, Professor. It's an honor, really, to talk at the TUA and to have you introduce me. Yeah, I didn't expect that. Thank you so much for this very, very kind introduction. It's true. I did my PhD at NTUA with Professor Collas, and then I left. But yeah, now I'm going to talk to you about more recent research around self-supervised learning and generalization. It's research that I'm doing at NAVER Labs Europe. And although all the years that I've been at corporate research labs, publications and open research has been my focus. So I will mostly focus on computer vision. And this is a very difficult and central task for AI, which means understanding what is in images and videos, right? This could be used for a wide range of tasks like scene understanding, Earth observation, climate change, monitoring, or for assisting medical diagnosis, for example. So together with AI at large, artificial intelligence in the field, a central factor for the recent accelerated progress has been data. And the data sets that we were using back 15 years ago were small and had a few thousand images. And then about a decade ago, data sets like ImageNet appeared. Now they have thousands of classes and labels and millions of images. And in fact, Professor Fei-Fei Li from Stanford had this idea of crowdsourcing labeling images, right? They used Amazon Mechanical Turk to get millions of class annotations of images, and then this enabled AI systems to learn what objects appear in an image, for example. And the size, the sheer scale of these data sets provide us with the data we needed to train huge models with millions of parameters like convolutional neural networks. And not only that, it enabled us to benchmark and measure our progress much, much better at a much nicer scale. So the ImageNet challenge started in 2010, and it's still 2022, very widely used, one of the central benchmarks for AI in general and measuring progress in AI. So let's briefly look at an image classification pipeline, assuming that one has access to a large set of annotated images, for example, ImageNet, and here are some classes, some images of cats and some images of dogs. We have two classes, cats and dogs. One can use these images to learn the parameters of a model, right? You use machine learning to learn the parameters of a model, and this is what we call supervised learning because the learning is guided by the labels, a cat or a dog. And I don't really have time to talk about how this type of learning happens, but in short, it follows the steps that you get part of the data set, a batch of the data set, as much as you can fit in your GPU memory, and you pass them through your model that initially is random, and then you calculate some gradients with respect to a loss function that essentially penalizes picking the wrong class for its image. And then we use backpropagation to update the parameters stochastically, and this is the gist of stochastic gradient descent. This is how supervised learning and self-supervised learning proceeds, as we will soon see. So the idea is that you learn the parameters of this model using the data you have, and then when a new image comes, we can use this model to get the probability of whether this new image now depicts a cat or a dog. Okay, and now the question is, do we need this large annotated set of images for every class and every data set that we want to classify, or could we learn visual representations on one data set like ImageNet that costed millions of dollars to collect, and then adapt them to new ones that might be much, much smaller? So this is what transfer learning is. My talk today is going to revolve around this idea of transfer learning, which is the machine learning method where a model is developed for one task and trained on one task and then reused as a starting point for a second task. And for example, we can use supervised learning, as I showed before. We have the images and the labels, and we learn the model parameters for image classification. And then we generalize or transfer this knowledge to other downstream tasks and datasets. And this is a very, very successful recipe, especially when downstream datasets are small. Now, the question that I'm mostly interested in is, can we learn such representations that transferable representations, but without requiring those labels, those annotations for training, right? Can we do it by only looking at images? And this is what self-supervised learning is all about. And the idea is that you learn your model parameters, like before, with some sort of learning, but without labels, from an unlabeled data set, without annotations. And you transfer the model to downstream tasks. And the learning happens again with stochastic gradient descent, as I mentioned before, like cats and dogs, but now we don't have the label cat and dog. So we need to find some different loss function to guide our are learning. And we evaluate self-supervised learning in this way. We measure how good our transfer learning performance is. We care about generalization. We basically train on one set and mention how good this helps us solve other tasks, right? And it turns out that it helps a lot. So self-supervised learning has deeply impacted the field of AI the last few years. I mean, the last 4 or 5 years. Although the ideas come from before, it has revolutionized fields like natural language processing. You probably all have heard of models like BERT or GPT-3. And it's now becoming a core component of computer vision state-of-the-art, and essentially it's transforming the whole field. Stanford recently even started a whole research center on foundation models that are models like this that are trained usually with self-supervised learning. And of course, there's been prominent figures that have been talking about self-supervised learning for a while, like Jan LeCun or Alios Aethros. So in self-supervised learning, there are no annotations, right? So we learn a proxy task that is self-supervised, which means that it's defined on the input data alone. And the idea is that we're learning some sort of aspects of the input, different aspects of the input space that are generally useful, perhaps in downstream tasks. So the best part is that no human annotation are required. We can utilize unlabeled data. This means that we can practically use any available image for training, while we also have this flexibility to find the best data that fits our downstream tasks that we want to solve, right? Because this has shown that it's better. So now one might think, does this mean that I don't need to care about what data I use anymore? And that's very, very wrong. Yes, you need to care even more, because things like this tend to happen where for self-supervised learning, there are no labels to get what we learn, right? So what we're essentially learning and encoding is whatever biases exist in our training datasets. So the subsets of labels might make you look at data even less. So always make sure, though, even for self-supervised learning, especially for self-supervised learning, inspect and understand the data that you use for your downstream tasks, to learn for your downstream tasks. So, yeah, so the proxy tasks that we're about to solve can be predictive or generative and formulated as synthesis or classification, or they can be contrastive, where we're learning some sort of variance to a pretext task. And what has proven to be a very successful proxy task for visual representation learning, that means for learning image representations, is learning invariance to image transformations. So as you see here, you take an image, you perform 2 independent data augmentations or data transformations, right? We change the color, we change a little bit the contrast. And then what you're trying to do is to maximize the similarity of the representation of these 2 versions of the same image. And although this might sound very simplistic, this is the task behind most of the most successful methods of the last couple of years. Yeah, and however, this is a task that is only useful for visual representations, right? When one can handcraft these image transformations, we know that the input is pixel intensity, so we can handcraft, color jittering and use it as a way of creating 2 versions of the same image. To go beyond pixel inputs, one can consider a more generic task that is of learning a lower dimensional space that preserves some sort of the topology of an already meaningful input space. And this is what we usually call dimensionality reduction or manifold learning simplistically. So with all this in mind, here is an overview of the talk that I will give today. It's a shorter version of a little bit longer talk. I hope I'll be on time. So first, we will talk about how to improve the transfer learning performance of state-of-the-art contrastive self-supervised learning. Then we will go beyond computer vision for a while and present how one can utilize all these amazing frameworks that work so well for visual representation learning, but now for a more generic task, that of dimensionality reduction. And finally, and since generalization is what we care about for self-supervised learning, we will talk about how one can measure a specific type of generalization, which is concept generalization in a principled way. Okay, and these are works that we published the last couple of years or on archive. So let's start with ways of improving self-supervised learning, contrastive self-supervised learning to be precise. And here our proxy task is the one that I mentioned before, which is that we're learning invariance to image transformations. So for contrastive learning in general, we need to define positive and possibly negative pairs, but now it's self-supervised learning, right? So we need to define them in a self-supervised way. So what we do is we take as a positive pair two transform versions of the same image, and then as negatives, any other image, okay? So starting from a given image, for example, this image of the cat, we first perform two image transformations and get two images, right? And these transformations, also known as data augmentation in in recent machine learning and deep learning, can be simple things like cropping or jittering the colors or changing the brightness, contrast of the image, right? So we take these images and then we pass them through the model, and this is the model whose parameters we want to learn. And we get two feature vectors in this high dimensional output space that we see here. These two green crosses are the features in this high dimensional space. So what we also do is we do the same thing for the negatives. We pass the negative images through the same model and get the red crosses, and these are the negative features. And we do contrastive learning. What does this mean? We're bringing the representations of the positive pair, the two green crosses, close to each other, and then we're pushing them, for example, one of them far away from the negative features, okay? So to do that, we're gonna use the influence loss, and this is a simple loss where, as you see in the denominator, you simply have the dot product, the similarity between the positive pair, and on the denominator, you have the similarities between one of the positives and all the negatives, and we're essentially minimizing the minus of this. So we're maximizing the similarity of the positive pair and downgrading the similarity versus the similarity of the negatives. This is a very successful loss that has been used in many, many papers. So famous papers like SimCLR and MoCo use this approach, and they basically differ on how do you get the negatives, right? So SimCLR is a simple framework. That's how it's called. That's why it's called SimCLR. It's a simple contrastive learning framework. The idea is that for every image in your mini batch, you get two augmentations to have the positive pair, and then every other image from the same batch are the negatives, okay? And MoCo is a little bit more advanced and essentially uses a memory with images from the last K batches as negatives in order to get more challenging negatives, right? More negatives to contrast. And this is a key observation, right? That led MoCo to have a larger set of negatives. We want to get more challenging pairs, more challenging positives and negatives to drive the learning, right? Because this has shown that leads to representations that generalize better. So how to get more challenging negatives? For SimCLR, the negatives come from the batch, so the only thing we can do is increase the batch size. While for MoCo, we have a memory, right? We can start increasing the memory, and this works pretty well, but after a while, we see that we're mostly adding non-challenging negatives. We're adding negatives that are not helping us learn faster. Yet, what we observed is that some hard negatives do exist already in the queue, and not only that, they have a strong influence on the learning and are influencing loss. So what we propose is as simple as this. We're taking some of the hardest negatives that we have for each query, and then we're synthesizing, we're generating a new set of synthetic negatives and adding them to the negative queue. So we're doing this directly in the feature space, as you see here, and on the fly for each query. So we're getting its query and we're randomly sampling some of the closest negatives, and then we're using linear interpolation to get a new point that is somewhere between the two hard negatives. Excuse me. I have my tea, but it doesn't help much. So yeah, we can go as far as mixing the query with one of the negatives, for example, to get even harder negatives, and we repeat. And what we have is a new set of red crosses, a new set of negative logits that are added to the denominator of the influence loss we saw earlier. And this is what we call mochi, or mixing of contrastive hard negatives. And I'm not going to go into details, but we implemented it on top of a state-of-the-art method. It fits really well with very, very small computational overheads in recent contrastive self-supervised learning state-of-the-art. And we're able to synthesize hard negatives, and as we'll see, increase the transfer learning performance. Excuse me. So to evaluate our models that are trained with Mochi, we use the common protocol that self-supervised learning methods use, which is we pre-train on ImageNet without the labels, right? Only using the images, and evaluate on a number of downstream tasks and data sets. And I'm going to refer you to the paper for details, but the highlights are the following: that for transfer learning to object detection and instance segmentation, synthesizing those hard negatives help the model learn faster. So you get strong performance with even few epochs of pre-training, and you can match the performance of the very strong baseline in only a fraction of the time needed, and these gains persist even after training longer. Right? So, as I said, further analysis is in the paper. We're analyzing the methods during the labels, and we see that also Mochi results to a feature space that is kind of more nicely utilized according to some metrics, and we have models publicly available. So the take-home message from this work is that you can synthesize hard negatives and you get faster learning and higher transfer learning performance. And it's a work we presented last year at NeurIPS. Okay, now, excuse me for this. Now, contrastive self-supervised learning has shown really impressive results for visual representation learning. Okay, but let's look at the more generic task. What happens if we want to go beyond computer vision and beyond this proxy task of learning augmentation invariance? So now, unlike representation learning, where the encoder function has to learn to transform a structured input like pixel intensities to a vector space through, for example, a convolutional neural network, for dimensionality reduction, we assume that we have a vector space and it's meaningful. We have a meaningful vector space, and maybe this vector space is high dimensional, right? And our task now is to compress the space and learn a space of fewer dimensions that preserves some properties, for example, the topology of the higher dimensional input space. And this is what is known as dimensionality reduction. And dimensionality reduction is a very important method that is used for a large number of tasks in practice. Why do we use dimensionality reduction? Well, because that if we compress the representations, any computation we do on top of that is more memory and compute efficient, right? Everything is faster after that. Also, we see that a lot of those dimensions might be even redundant, and you can reduce the memory and compute without losing any accuracy. And also, maybe we're doing dimensionality reduction because although there's this trend for learning things end-to-end in our field lately, so everybody says you can learn your representation together with the peculiarities of the task that we want to solve. This is something that in practice could be prohibitive for a number of researchers, especially outside the core AI field, because one might lack the know-how of training these huge encoders, or they might not have the compute to train these huge encoders that need many, many GPU hours. Or, for example, we're just having this representation that could even be a visual representation, right? But we get it directly from a sensor, and it's impossible to handcraft priors like the ones we did with pixels. So even in the case of NLP, for example, handcrafting priors is really, really hard. That's why all the successful self-supervised learning models in NLP are using simple masking, for example, predicting with context. So for all these reasons, dimensionality reduction is still ubiquitous in many, many fields beyond core AI, like computational biology and remote sensing and climate and finance and drug discovery, for example. So here's a figure. Let's assume we have an input space of dimensionality capital D. And what we want is to learn this encoder, which is the dimensionality reduction function, that would take us to a lower dimensional space for dimension lowercase d. So when this output lowercase d dimension is 2 or 3, we have a very specific case, a very popular case that is visualization. And for this, there exist a number of amazing methods that specialize, like TSNE and UMAP. And these are great, but they're made for visualization, and they really don't scale well when you want the output dimension to be more than 2 or 3. So what do we do when we have output dimensions that is more than 3, for example, is one thing you can do is this manifold learning approaches, where the idea is that you're trying to preserve the topology of the input space. You assume that the data in the input space are lying in a lower dimensional manifold, and usually you assume that it's locally linear, and then you're trying to find this lower dimensional manifold. The problem with these methods is that they really don't scale well with respect to the dataset size and use complex optimization many times or require a lot of compute. So what do people do in practice? Like when you have even a few millions of data points and we want to do simple dimensionality reduction? Well, in practice, what everybody is doing, and this is true even in production systems right now, is use linear dimensionality reduction. And this is like variants of principal component analysis, for example. And yeah, as I said, it's used in practice for large scale systems, especially retrieval systems where compute is very, very important. And it's used everywhere just because it's like really, really hard to beat. In large output dimensional spaces, a linear dimensionality reduction seems to be very, very strong baseline. Okay, so this is why PCA is in many cases the method people use, and in fields like biology, again, assisted medical diagnosis or medical image analysis. But let's take one step back, right? And we said that these manifold learning methods are really cool, but are not scalable. Why aren't they scalable? Well, this is usually because many of them require propagations on, for example, KNN graphs, or use complex optimization solvers, or use eigendecomposition Laplacians in these graphs. But all these things weren't really an issue for the simple things that I was presenting before, right? This contrastive learning, you have stochastic gradient descent, you take a few minutes at a time, you have a simple contrastive loss where you're just bringing two things together. So the question that we asked is, can we borrow from these approaches that have worked very well for visual representation learning to design dimensionality reduction approaches? And to do that, we needed to find, first of all, a simple and a scalable loss function. And for that, we chose a loss that is more recent than the influences, this Barlow-Twins loss. So this is a loss that was used in the original paper for the task of learning invariants to image transformations, as I described in the first part. So it is made to work with positive pairs, right? So unlike InfoNCD, however, it does not have any negatives. We will see the loss function and how it looks. But what is important is that this loss function fits really well for dimensionality reduction because it's focusing on decorrelating the output dimensions, and it has a very, very elegant way of avoiding collapsing representations, despite it only has positive pairs. So it brings things together, nothing to contrast. It still doesn't collapse. So let's look at the loss function. Assume that we have a pair of matching representations from the positive pair, ZA as a B. The loss first requires to compute this empirical cross-correlation matrix that is computing across the feature dimension. So it's if the output dimension is D, this is a D by D matrix that is essentially the outer product of some more normalized version of every positive pair that is averaged over the minibus that we have, okay? So given this matrix, the Barlow-Twins loss has two terms. And the first one is trying to push the elements of the diagonal to be close to 1, while the second term is pushing the off-diagonal elements to 0. So what does this mean? The first term that we're maximizing, we're trying to essentially maximize the dot product of every positive pair. Pretty similar to InfoNC earlier, right? While the second term is essentially saying that every two dimensions have to be decorrelated. I'm saying again, this matrix is a D by D matrix, so the rows and columns correspond to dimensions in the output space, in the space where you compute the Barlow-Twins loss. And that's it. So what is missing? Well, the Barlow-Twins requires positive pairs. How do we define positive pairs? Now that we don't have, for example, we cannot define image transformations well. For that, we follow the recipe of many manifold learning methods, and essentially are saying that we want to preserve neighborhoods of the input space that we assume meaningful in the output. So what we're saying is that we're going to create pairs by getting nearest neighbors in the high dimensional input space and use those and the Barlow-Twins loss to learn this dimensionality reduction function. Okay, and then to put it all together, we have our encoder, which is the encoder that we want to learn, the parameters, the model that we want to learn, and a batch P of uppercase D dimensional vectors. And let's get positive pairs via nearest neighbors in the input space. This is the high dimensional input space. We split the pair, we pass it through the same encoder, and we get two lower dimensional representations. Then the only thing we have to do is to add the Barlow-Twins loss on top, okay? And this is what we called twin learning for dimensionality reduction, twin because you're using twin encoders, or TLDR for short. And once again, I'm not going to stay in the details. There's some important notes. There's this projector that I didn't even discuss about, but there exists this projector that takes you to a different space where you compute the laws in practice, and yeah, a much larger dimensional space, and this is important to make this work. And the cool thing here is that we're saying that the encoder can be anything, right? So it could even be linear, for example. So the TLDR algorithm is very simple. You have the input points, you're getting nearest neighbors, you sample pairs, and then you learn the parameters of the encoder by optimizing the Barlow-Twins laws. And to evaluate this, we use a task where dimensionality reduction is still rules, and it's a part of even the state-of-the-art pipelines, and that is large-scale retrieval. And since TLDR is input agnostic, we experimented with like image retrieval, but also with document retrieval. And note that this is a case where the output dimensions are, for example, usually close to 128. This is what we care when we want to compress, you know, a huge data set and store it into memory for example, approximate nearest neighbor search. So what is used in practice here, even state-of-the-art methods, right? There's a baseline, but a very strong baseline is PCA with widening because of its effectiveness and scalability. Excuse me. So to directly compare to PCA, we choose to have a TLDR with a linear encoder. So our encoder is essentially a matrix multiplication, a linear function that we're learning. So I'm once again only going to summarize the highlights of the evaluation. So we're replacing PCA with linear TLDR at the state-of-the-art retrieval pipeline like GEMAP, and we test on common datasets that like the Oxford and Paris buildings datasets, and we see that we either get an increase in performance, or we can match the performance of the baseline with far fewer dimensions, right? And we got also very good results for text retrieval and for a task that's called argument retrieval, actually. So the idea is that you get recent features from a BERT model, and you want to retrieve, again, the closest argument to solve this question, for example. And this is argue on a data set. What we see is, again, that we usually outperform a state-of-the-art baseline in most dimensions, or we can match the performance of the full representation, usually a small percentage of them. So to summarize, TLDR has a number of advantages. First of all, it's general. It can compress any meaningful vector space with no further assumptions. And you can use many types of encoders. We mostly focus on linear, but you can also use MLP or factorized linear. It's relatively simple to train. The Barlow-Twins laws is very, very robust. It's easy to optimize, and the hyperparameters really transfer across tasks. It's trivially scalable, right? It's learned through minibus stochastic gradient descent. It's very GPU friendly, and it has very high resilience to approximate nearest neighbors. We have a lot of ablations in the paper, but what's most important is that we think that TLDR is a tool that we hope a lot of people are soon going to start using. So we released very easy to use code with an interface more or less like scikit-learn. So you have a fit and a transform function. Everything is abstracted, and a few lines you can use this. And in many cases, just try it. If you're using PCA, definitely try it. You can probably do better with TLDR. Yeah. So yes, to sum up, TLDR is a scalable dimensionality reduction method based on recent algorithms, but also very old ideas. And it exhibits strong performance in many tasks, and we have really easy to use code publicly available. It's not suitable for visualizations or representation learning, which that means like if you can hand graph priors, please do, it's going to be much better. But if you cannot, and you just want to do dimensionality reduction, you can use TLDR successfully. Okay, that was TLDR, and let me see how we're doing on time. I think okay. Let's talk about how we can measure generalization better. As I said, for self-supervised learning, this is what we care about. We don't really care about how well we're solving, the proxy task, the augmentation invariance task, for example. We care about how well we're doing in the case where we transfer this knowledge to a new data set. So let me define concept generalization. Is the extent to which models trained on a set of seen or training visual concepts can be used to recognize a set of unseen target concepts, right? In other words, we're asking the question, is a model that recognizes cats, let's say we learn a model that recognizes cats, is this a good starting point for learning to recognize dogs? And how about corals? And in general, does it even matter what are the classes that we use during training when we want to transfer this knowledge? And so our hypothesis is that, of course, it matters. Like semantic distance between the training and scene concepts and target concepts impact generalization performance. And our goal is to design a better benchmark for measuring exactly this, concept generalization in a more principled way. So let's first see how we measure concept generalization right now, right? As I said, we're learning the model parameters for ImageNet-1K. Either self-supervised way or supervised way, it doesn't matter. Right now, we're just trying to measure how well models generalize to other concepts. But what is happening usually is that you usually evaluate your model on many downstream models, for example, like food or cars or aircrafts, and you expect that on average it will show that your new algorithm is better, right? The problem is that it's really unclear how the concepts in these datasets relate to the concepts that were seen during training, okay? So what we wanted is to have a benchmark that is better in the sense that it has a large set of concepts, right? And a very controlled setup where there is a disjoint set of training and testing or unseen concepts. And also, we want to have a way of measuring the distance between concepts, right? There's some sort of semantic distance, for example. So what are the ingredients to create this benchmark? Step 0, we need a large data set. So for that, we use ImageNet-21K, which is a very extended version of the ImageNet. When everybody says ImageNet, they usually mean ImageNet-1K, which is a data set of approximately 1 million images. So ImageNet-21K is a superset of this, and it has 21,000 concepts. Each concept is corresponding to a scene set from a handcrafted ontology called WordNet that we're going to use later to define semantic similarities. And most importantly, it has this very popular training set as a subset, the ImageNet dataset. So everybody is using ImageNet to train their self-supervised learning algorithms, for example. This means that this is what we will define as the set of scene concepts, right? So the next thing we need to do is to split the classes in disjoint sets of seen and unseen concepts. And this is a very easy choice, as I said. We have ImageNet-1K being a subset of our data set. So the seen concepts will be ImageNet-1K. And now for the unseen concepts, we're going to do a selection of the rest of the concepts. We're going to filter out some pathological concepts or concepts with few images. And what we end up with after filtering is 5,000 concepts that are eligible to be our unseen concepts for transfer learning, for measuring how well we transfer. And now remember that we need to define some sort of semantic distance between concepts. And for that, again, we're not doing something special. We're using an LTK metric called lint similarity that takes into account the graph that underlines this concept. In practice, the choice of a metric was not crucial, and we showed that one can use things like word2vec to also define similarity between concepts. But with this metric, we have a way of defining a distance or a similarity between two concepts that is based on a handcrafted human-created ontology, right, of semantics. So the first thing we do is we extend lint similarity to a set to concept metric by simply taking the max. Why? Because we want to measure how far we are from the ImageNet 1K dataset as a set, okay? We want to see how its unseen concepts relates to all of the seen concepts together as a set. So this is what we do. For every unseen concept, we calculate the lint similarity versus the set of seen concepts, these 1,000 classes from ImageNet, and then we rank. We rank all these 5,000 unseen concept candidates with respect to their semantic distance to all the scene, okay? And then we take this ranked list and we split it in 5 levels or 5 data sets. And now what happens is that each one of these levels contains concepts that are on average semantically further and further from the scene ones, okay? So concepts in L1 are on average closer to the scene concepts, to the training concepts than L5, okay? again, I'm not gonna stay with the details. This is a benchmark that we named ImageNet COG, and COG is for concept generalization. ImageNet is because we use ImageNet. And the benchmark consists of 5 levels, which is a sequence of 5 data sets of unseen concepts, each one with increasing semantic distance to the training ones. And the evaluation protocol for this benchmark is that you have a model, you treat it as a black box. As a feature extractor, you take, you extract features from a model that is trained on the seen concepts on ImageNet 1K. And then you only learn linear classifiers on top for ImageNet 1K and each one of the generalization levels. And the cool thing about this benchmark is that we can therefore evaluate any public pre-trained model out of the box. All the new architecture, all the new computer vision, fancy architecture papers are usually releasing their models publicly. Well, that's it. We can take them and out of the box evaluate them on our benchmark. And that's what we did in our paper. We have a detailed study on like 30 very recent models, like visual transformers or neural architecture search models, or a lot of self-supervised learning-based models. And we evaluated them on our benchmark. So I'm only gonna present highlights. First of all, at this very complex plot of 31 lines, we see that we're verifying our hypothesis, right? So what do we see here? We see top 1 accuracy versus on the y-axis versus the generalization levels on the x-axis. And on the leftmost, we have ImageNet 1K, which is how well these models perform on the seen concepts. And then we see that as we go to further and further semantic concepts, it's harder to generalize, okay? So this verified our hypothesis, right? Now, to make this a little bit more readable, it's like very chaotic graph. We did 2 things. First of all, we took this black line, which is this baseline ResNet 50, which is a classic CNN out of the box that a lot of people use from PyTorch, and we flattened it. And then we're showing performance relative to this, just to clarify things. And the second thing we did is that we split the graph into methods along different axes. And some highlights are simply that, like, first of all, self-supervised learning models really excel at concept generalization. Things like visual transformers over fit, that neural architecture search and distillation methods really help improve concept generalization performance. Additional, even noisy data help. We also show that recent works that are proposing label-based augmentations, like CatMix or Mixup, like that help a lot for ImageNet 1K. They deteriorate the performance for COG, for our benchmark, and for generalization in general. So again, I refer the interested readers to the paper for details and for way more results. So the take-home message is that here's a new benchmark that enables measuring concept generalization in a controlled way. And it's really easy to test your ImageNet 1K pre-trained model. We have code available, and we have a large study in our paper with many recent methods out of the box. And this is work that we presented recently at ICCV. So this was it. This was a very quick overview of recent works that I've done around, I've participated in, around self-supervised learning and generalization. We talked about how hard negative mixing can help contrastive self-supervised learning. We talked about how can we use recent visual self-supervised learning frameworks for dimensionality reduction, and then how can we measure concept generalization in a more principled way. And of course, this is work with a number of colleagues and students at NAVER Labs Europe. All the works that I presented are with Diane Larlous, and then some with our student Bulent that we co-supervise together with Kartika Lahari from INRIA. And then Carlos and John and Noe and Philippe are also co-creators of some of the works that I presented. So I'm presenting this on behalf of all these people. This is not just my work. And all this work was done at NAVER Labs Europe. And maybe, I mean, I didn't know what NAVER was before I joined NAVER Labs Europe, but NAVER is a company that still has the search, the larger search market than Google in Korea. So it's a very big Korean company that has a very extensive research team. And we have teams focusing on computer vision and 3D vision. We have more than 30, that's even more now, I think. We have many top tier publications. We have collaborations with many top tier universities. And we have research, internships, and positions open. So check out our website if any of this was interesting, and to see way more things that we do around 3D. So just to finish, and like again, thank professors for inviting me. I feel like it's an honor to be invited to talk to NTUA, and at this scale, like seeing the previous speaker and all the amazing thing he has done career, it's like a real honor. I just want to mention here that it's been like I spent almost 12 years of my life at NTUA as an undergrad at ECE at CIMI, and then my PhD under Professor Kollias and Yannis Avritis. And then I went to the US, and here I wanted to mention my research interest in case somebody is also interested and they want to talk more about this. You can find more at my Scholar profile and personal webpage. And to advertise a little bit more, NAVER Labs Europe. NAVER Labs Europe is really, these are our offices. They're under the Alps in Grenoble in France, and it's a very beautiful place. We have 3 buildings. This is one of them. Yeah, and thank you so much. And any questions? And I hope, I think I'm on time. I didn't leave a lot of time for questions, but yeah. I can also not see people, just note. Ah, no, okay. I can see some people. I can see Yannis, hello, and Professor Kollias, and other Professor Zachos, that, yeah, it's so nice. So thank you. I mean, any questions are more than welcome.
Thank you very much. Stefano, will you guide the questions? We don't hear you, sorry. The mic is closed.
Sorry, yeah. Yanni, thank you very much for this presentation, which included very recent developments from your side the last couple of years. And I think all this show how what we expect at this direction of research with respect to self-supervised learning, with trying to show how deep learning, data-driven knowledge links with semantics representation and so on. I think so it shows really interesting views that we think will be also present in the next few years. Could you give us a prospect of your research based on what you have decided? I think it's interesting because we're speaking of challenges here. What do you think will be the continuation of these things in the next couple of 3 years, for example? Yeah.
Yeah, thank you. Thank you again. I just remember that even back in 2010, before this, you were always, you know, about neural network here, and you've been teaching for 30 years, like many other people. But I remember at some point, like 2010, you came and said, "Yeah, it's neural network will rise again," or something like this, and they did very shortly after. So these are all very recent things, right? So one of the works is on arXiv, like a couple of months ago, is works that we're doing now. The longer trend for me is we see that if you have better representations, other things become easy. So if you are doing good representation learning, even for NLP, then other tasks that were solved with like handcrafted ways can be simplified and solved with simpler methods. I think this trend will continue, and I personally really like learning with like limited annotations and learning models that adapt and they change, and they can be used in many tasks, for example. And that means that it's really interesting to probably go towards more structured intermediate representations. So right now we're talking about representations that are like a vector, and you transfer this vector to a million tasks. Can we learn more expressive ways of understanding an image that is not just a vector, for example, like not going back to local features, but something in between, something like more expressive mid-level representations? Or how can we learn these models in ways that encode a multitude of these priors that we have, and then try at test time understanding what is the best thing to use for a new task? This is not just me saying that it's like a big directions from like Google and Facebook. They're all working on the same things. And yeah, I don't know if that answers your question.
Yeah, thank you very much. I mean, this is a continuation. We will continuously face problems, and the one will build on the other, and so on. We know how this works. And thank you, Yannis, very much. I think I wish you the best for the continuation.
Thanks
We'll
so
be in
much.
touch. Thank you.
Of course.
I see there is a question by Thanos Volodymos.
Thank you very much. Hi, Yanni. Just to reiterate, I mean, it's your work has been impressive. Thank you very much for this interesting presentation. All three parts, the three bodies of work that you presented, they were all interesting in different ways. So way to go about that. Just, I mean, I do have several questions. Just maybe I missed something. One of them maybe has to do with the first part of your work. I think I missed. Excuse me if you did say it or if when it isn't totally clear to me how one can be sure what the limits of the hard negative space, or to put it differently, when you produce when you generate something, how do you know if it is certainly within the hard negative space?
This is an excellent question. First of all, you didn't miss everything. I had to butcher this talk to make to make it fit in time.
It was already too dense. Let me say. I mean, it was. Because
what you're saying is excellent point, and in fact is how we started this this line of research. So to take you one step further, we're saying that this way of learning helps you do image classification, yet for this specific cat image that I showed, the little cat, every other cat image is a negative that you push away in feature space. So even without mining hard negatives or synthesizing hard negatives with what we do, you simply you're pushing this cat image further away from every other cat image. Yet what you learn through this process still helps you understand what a cat is. It's fascinating, and we wanted to understand how far can we push this. By synthesizing hard negatives, we might be exaggerating this problem, as you said, right? You don't know the limits of when a hard negative starts and or a good positive is. So yeah, it's amazing that this works. There's a study in the paper. I didn't have time to go through this, which it says, okay, we're doing self-supervised learning, but all this is on ImageNet, so we have labels. So let's look, we can understand, when do we get to cats to contrast one synthetic cat with a cat? And we have studies on that, and it shows that on average, it's not that much. It's not very often that you synthesize something like 2%. When you synthesize one, for sure, a hard negative from the same class. But this is already an issue that exists, right? So it's an open question. Why is this working so well is unclear, but it's at the heart of this. Very good question.
Okay, I see. Thanks again. Great work.
Thank you for this question.
I'd be happy to chat more about
of course
this. Yep.
Yannis, I think there's a related question in the chat.
I cannot see chat. Let me see. I've never used WebEx before. Okay, chat. I found it. Okay. That's very first minute, yeah. It's a question about Mochi. Shouldn't using synthetic hard negatives introduce noise in learning? Yes, so this is very, very good. Another very good question that is very related to what Thanos just asked. So we measure exactly how many these 4 negatives are. And the best part is that I hid through this presentation is that when we're learning classifiers on ImageNet, synthesizing hard negatives doesn't help increase the performance when you're testing at the same data set as training on top of MocoV2, right? So we're not increasing the performance when we're doing when we're learning on ImageNet without labels and then transferring it to learning classifiers on the same data set. Where we gain is when we use this model for other tasks, right? So so it does help downstream tasks, but it doesn't help when you're testing on the same training set because exactly of what you said, because it's more noisy. I hope that answers the question.
Thank you from our side. Thank you very much. Aris, it's up to you now.
Thank you. Don't want to take up
Okay.
time from the next speaker.
Okay, I think we are on time. Thanks to Yannis, he kept time very well. And let's thank all the speakers of this session, Onur and Yannis, very much for being with us and presenting excellent talks. And also thanks to the chairs, Dionysis Pneumaticatos and Stefanos Kolias. Thank you all. We'll have a small break now and we can resume on time, 4:30 p.m. with the talks of Leonidas, Lampropoulos and Thanassis Avgerinos. Okay, see you all.
Thank you again for the invite, everybody. Thank you. You're going to invite. Yes, yes.
Thanks, Yannis. It was very nice to see you again after.
It's nice to see so many of my professors in one place.
Thank you, ευχαριστούμε Γιάννη.
Ευχαριστώ εγώ πολύ. Τιμή μου. Γεια σας. Καλό μεσημέρι.
Γεια χαρά.
Γεια σου, Γιάννη.
Okay. So I think it's just about time to start the next session, right? So we have two excellent speakers, Leonidas Lampropoulos and Thanassis Avgerinos. Who would like to introduce the first speaker? Is it Kostis or Nikos?
I can do that, if you want me to.
Okay. So Nikos will introduce, and I think he's the most appropriate.
So good afternoon.
The next one. Thanks, Nikos.
Good afternoon, and thank you very much, Ari and Dimitri and the other Aris and everybody who helped in making this day of presentations possible. It's a wonderful event. I am very happy to introduce Leonidas Lampropoulos, who's going to be the next speaker today. Leonidas was a former student of our school at the National Technical University of Athens. He finished his first degree in 2012, and then he moved to the University of Pennsylvania, where he got his PhD in 2018. His advisor was Benjamin Pierce. During this time, he also had a short internship at Microsoft Research in Cambridge, in the UK. After his PhD until 2020, Leonidas was a postdoc at the University of Maryland, and I think it was a joint postdoc with the University of Pennsylvania. He worked there with Michael Hicks and Benjamin Pierce. And since the July of 2020, he has been an assistant professor at the University of Maryland at College Park. Leonidas's interests are in the area of programming languages, and especially in the field of software correction. Software correctness. He does that both using verification techniques and random testing. And his talk today is going to be about mostly about the second of the two that I mentioned. He's going to talk to us about property-based testing. Leonidas is the author of the fourth volume in the series of software foundations, and he has also published his research results in the most prestigious and well-known venues in the field of programming languages, such as conferences like POPL, ICFP, ESOP, UPSLA, etc. I'm very proud to present Leonidas, and Leonidas, if you're here, you can give us your talk. Thank you very much. Dimitri, Leonidas says he cannot unmute himself, so let's do that. He's probably in the attendees and not in the panelists.
I fixed it.
Okay. Leonidas, can you do that now?
Can you hear me now?
Yes, we can hear you.
Perfect. Okay, let me share a screen, see if that works.
We can hear and we can see.
Perfect. Let's see. Can you see the screen?
Yep.
Okay, perfect. Let me that. Okay, so thanks for that introduction, Nick. As Nico said, I'm going to talk to you about work that we have been doing in the University of Maryland in property-based testing. Yeah, so let's see if that works. Yeah, okay. So as always, I'm going to start my talk talking about how bugs are everywhere, right? The bugs are everywhere. They can have devastating implications, financial implications, security implications, and most of my work has been dealing with either how to find these bugs or how to make sure that they don't exist. In this talk, I'm going to mostly focus on the question, how do we find bugs? How do we test software effectively? And my favorite answer to this question, going back to when I was doing my undergrad with Kostis, is property-based testing. Property-based testing is a technique invented by these two folk on the right, Kuhn and John, where programmers write properties, they write specifications of a system under test, and a tool generates many random inputs and tries to find counterexamples to those properties. So as a running example, I'm going to use a simple specification of sortedness. So a very simple specification would say that for all lists of integers, if we sort a list L, then the result is sorted, right? And the question that we'll be asking throughout this entire talk is, how do we test this property? In property-based testing, we start with a generator for random inputs, here, random lists of integers. So you would generate a list, run through the property, and you'd get back the result. Is the result after sorting sorted or not? And as long as it's true, you're going to try this again and again and again until at some point you generate some list for which the result is false. And then you report that to the user. Now, this is a very high level overview. And of course, the way you're generating your inputs matters. And in this case, you can just use type information and say that I'm generating lists of integers. And therefore, if we take an even more abstract view of things, we're literally just talking about universally quantified properties of the form, for all x of some type t, p of x holds, where p is some property that you can decide, like, is the result of sorting this list sorted? And the approach is we generate x based on type information and test whether p holds. Seems simple and straightforward, but it works in a surprising amount of cases. Today, I'm going to talk about two problems that arise in this setting, in this situation. And the first one is when properties have a particular form of having preconditions, right? So if you have properties with preconditions of the form for all x of some type t, p of x implies q of x, the approach I just described of generating x based on type information would mean that we are checking whether p holds, and if it holds, only then do we test the conclusion. If not, we have to start over. And of course, if p is sufficiently sparse, if it's hard to satisfy, this will not work, right? So for example, if we were testing a compiler, then a property could be that if we have a C program that doesn't exhibit undefined behavior, then it should behave the same before and after optimizations. But of course, generating C programs that don't exhibit undefined behavior is a research paper on its own right. It was like a PLDI paper 10 years ago. So this can be arbitrarily hard. And to make things more concrete, let's spice up our running example a bit with a precondition. So instead of talking about sorting lists altogether, let's talk about inserting elements in sorted lists. So this property says that if for all integers x and for all lists of integers L, if the list is sorted, then inserting an element into the list preserves this sortedness. And the question I'm going to ask once again is, how do we test this property? Well, the first way we can test this property is do what I described before, generate and test. We generate an integer x and a list L, check if the list is sorted, and then and only then test if the insertion works. But just like I hinted before, even for this very, very simple example, this doesn't work. Generating sorted lists of integers of length more than like 4 and 5 is almost guaranteed to fail. So the solution that the property-based testing community has sort of arrived at is to write custom generators, to write a generator, a program that produces sorted lists directly with some distribution. And in this case, it's surprisingly easy. You can just generate an arbitrary list and sort it. And if your sortedness does not actually rely on insert, so you're not using insertion sort, then this is actually a pretty good way of generating a sorted list. However, we've sort of just punted on the problem, right? So we've turned the problem from how do we generate integers to how do we write a good generator for sorted lists. And here by good, I mean it produces only sorted lists, it produces all possible sorted lists, and the distribution is somehow appropriate for testing. And as I hinted at before, this is a particularly hard problem. It can in fact be a research contribution in its own right. The precondition I talked about before, the generating C programs without undefined behavior, was a PLDI paper. Generating lambda terms that are well typed was an AST paper. Testing non-interference, which is a thing I will come back to later that we did, was an ICFP paper. This is a very hard problem. So let's take a step back and put different flavors of how you can achieve this generation in a slightly not that formal axis, right? So we have, on the one hand, we have user effort, on the other hand, we have bug finding efficiency. So at the bottom left, we have naive generate and test random testing, right? With minimal user effort, you just use automatic tools that exploit type information, you have minimal bug finding efficiency. You're not gonna get far by just generating random C programs and hoping that they don't have undefined behavior. On the other hand, on the top right, you have handwritten generators, maximum user effort, but also maximum bug finding efficiency. You can find bugs, hundreds of bugs in C compilers like GCC or LLVM, but it will take you a PLDI paper to do this. Ideally, we would be on the bottom right. So we would have minimal user effort and maximum efficiency. But of course, we're not there yet. And whenever I see a graph like this, I'm going to have to ask what's in the middle. And this talk, the first part of this talk is going to be about how we can take this automatic methods of minimal user effort and trying to make them better. How can we extract every ounce of information that from what we know, from the structure of the properties and so forth? Now, there are mainly two approaches. You can cluster these kinds of techniques in two approaches. One is white box techniques, where you know the code of the precondition, and you can inspect it, analyze it, do some static analysis, do symbolic execution, whatever, to generate inputs that satisfy this precondition. Or you can have some more lightweight techniques that only use some runtime information to guide the exploration of the search space in the style of fuzzing. I've done work in both, and many people have done work in both, but this talk is about the latter. It's about some work that we did a couple of years ago on combining fuzzing with property-based testing. So with that, welcome to Fuzzing 101. In fuzzing, it's traditional software engineering fuzzing. You have a binary executable, and you have some generator for random bits of integers. You're generating those inputs, you run the executable, and then as long as you don't find a crash, you keep doing this whole thing. Does this look familiar? Well, it should, because the key realization that fuels this line of work was that fuzzing is just an instance of property-based testing, where the property is that for all binary inputs, the program doesn't crash. Great. So let's recreate the original graph that we had for property-based testing and see what's here. On the bottom left, we have completely naive random fuzzing, where the bits are generated randomly. No user effort, but also not great bug finding efficiency. On the top right, we have fuzzing with custom grammars in the style of libfuzzer or IMF. Those can be extremely effective at finding bugs, but writing a custom grammar for binary inputs is extremely hard as well. However, in the middle, there is a particularly interesting design point, which is covered guided fuzzing in the style of AFL. And I'm saying particularly interesting because it has revealed a plethora of bugs that are extremely important, from Firefox to PHP to iOS itself to whatever. It has been used by the security community to find bugs everywhere and vulnerabilities. So let's take a closer look, because if fuzzing is just an instance of property-based testing, can we use ideas from a successful point in the design space to make property-based testing better as well? So here's how coverage-guided fuzzing works. You start with the same binary executable you had before, but you add some lightweight instrumentation, and the instrumentation allows you to keep track of which branches you take throughout the execution. you start with an initial seed again, random number, random bits, run the binary executable, ask if it crashes. Now, however, if it crashes, you report to the user as before, but if it doesn't crash, you don't throw it away, but rather you ask the coverage information to tell you whether you uncovered any new paths, if this particular input led you to explore a new path in your program. If not, then you throw it away, fine. But if it did, then maybe, just maybe, if you remember this SID, and then you mutated a tiny bit, like changing those ones to zeros, then if you run it again, you're going to uncover a new path and keep exploring your program, eventually leading to a crash. That's it. That's coverage guided fuzzing in a nutshell. And what we call a fuzzer is this idea at the top. You have to have a way of figuring out if an input led you down a new execution path. You have a way of remembering and picking which seed to work on next. And you need a way to mutate those seeds in order to create new ones. And the key insight behind this line of work is that just like AFL uses coverage information to mutate bit strings, we can use coverage information to mutate complex structured data in the style of QuickSet, in the kind of structured data that property-based testing works on, lists of integers, programs, whatever. And this is what we're going to call a semantic mutation. So coverage-guided property-based testing is basically the same thing you saw before, but with a few key differences that I'm going to point out. First of all, instead of starting with a seed, a particular bit sequence, you can start with a random generator. So you had those random generators, type-based random generators before that generate lists of integers or C programs or whatever, and you can generate those in order to feed your system under test. And then when you run your system under test in your property, you have your instrumentation, you can figure out which branches you took, but the end result is not a simple, did this program crash or not? You get the result of the property. You have a lot more information like, did it satisfy your precondition? How close was it to satisfying your precondition? And all of those things are various forms of feedback which you can use to make generation better. Then, just like before, you look at if there were any new paths and you have a seed pool. And then when you go to mutate your inputs that you've remembered, you mutate them at the semantic level. You're not longer flipping bits. You work with algebraic data types. You work with typed structured data, and you need to preserve the structure in order for running your property to be even possible. And finally, you have this choice point where you're no longer roped into only doing mutation. You can choose when you're going to do random generation and when you're going to do mutation. And it would make a lot of sense to sort of keep doing mutation as long as you're exploring new paths. And when you're finally hitting some a limit in your how much you can explore, try to reseed the entire process with new random seeds from your generator. So there are a lot of things you can do in this regard, and a lot of the bits that you see here circled are very important to how well this thing works. But arguably the most important part is the semantic mutation itself. And that's what I'm going to focus on for a bit. So semantic mutators are basically functions that take structured data to a probability distribution over things that are nearby. And here I'm just going to be showing the support of that distribution, the things that are the elements of that distribution, because what the correct probability is frankly open future work. So all the semantic mutators that we created are inspired by their AFL counterparts. So AFL can do modifications, right? We said we have a series of bits and we can flip one of them or a sequence of them. When you go to a structured setting, that means you can just mutate elements of your data structure. So if I have a list of 4 numbers, I can change that 4 into a 5 or that 1 into a 0. Then the second kind of mutation that AFL does is it can delete bits. And it can delete a single bit or a series of bits or something like that. Of course, if I were to delete bits from the underlying representation of a list, that would just leave garbage. You wouldn't even be able to type the resulting artifact. But we have structure. And since we have structure, we can focus on particular substructures of our input and delete those. So we can delete something from the middle of the list, delete the tail, delete the head, whatever. And finally, another line of mutations that AFL does is basically to result in adding bits. And usually that happens by duplicating sequences of bits from the input. Here, however, since we have random generation, we can do a lot more than that. We can just use the random generator to create nodes that were not there before, but that still respect the structure of our input. So we could create a 42 and put it at the front of the list, or we create a 0 and put it somewhere in the middle. And all of those things are a lot more powerful mutations compared to what AFL does at the bit level. Precisely because we have this structure. Now, we can also describe these kinds of mutations more formally. So, for example, if we have an inductive type, we have a data type with a number of constructors, then a mutation is really just either we're picking one subterm of the arguments of a constructor to recursively mutate, or we are mutating to a different constructor by keeping some of the subterms that have appropriate types and generating new ones from thin air. It's not really important what the particular formalization of this process does, but what is important is that having done this formalization, we can now prove once and for all that mutations are complete, in the sense that you can go from any instance of an inductive type to any other instance of an inductive type in a reasonable number of steps using these kinds of mutations. Okay, so I gave you a brief idea of how this coverage guided fuzzing works, but let's talk about how well it works. And the case study I'm going to talk about is a case study that was one of those really hard preconditions that we wanted to tackle that I mentioned in the very beginning, which is non-interference. And non-interference is a security property that states that secrets don't get revealed. So a brief primer on what this is, you start with a machine, standard machine. It has a register file, it has a heap, RISC-like instructions for the setting, because that's what we were working on at the time. And the idea is that you tag every single piece of data in this machine, every single integer, you tag it with a security level that says whether inputs are public or secret. And the idea is that everything that is tagged public is public knowledge, anyone can see it, but everything that is tagged secret is should not be able to be accessed by a public observer. And the way you phrase that is that secret data never affects the value of public ones. How do we enforce this? Well, we enforce this with a security monitor. So what does the security monitor do? It looks at the thing you're trying to do. For example, you're trying to add 42 public to 1 secret, and it says, wait, you're trying to combine data that are secret and public. You shouldn't be able to do that. More likely than not, it's going to be a bit more permissive than that. And it's going to say, well, you're allowed to do that, but the result is now secret. So you've influenced something in using secret values, so the value of the result should also be secret. And the natural question here is, how do we know this is correct? But before we even ask that question, we should know what does correct even mean. And the answer to that second question is non-interference. Now, non-interference is the property that says that public data should not be influenced by secret values formally. How do we do that? We use the notion of indistinguishability. So we start with two machines that are identical. They are exactly the same for all intents and purposes. And we are allowing them to differ only on secret data. So to an observer that doesn't have access to those secrets, those machines are now indistinguishable from one another. And then we let the machine step, right? We start with two machines that are indistinguishable and take a step. And non-interference states that those new machines that we step to should still be indistinguishable. So differences in secrets in the original machines should not result in differences in public data after one or more steps. And the question is, how do we test this property? This is a perfect example of a very sparse precondition that we saw in the very beginning. And because you have to generate input machines, which have register files, heaps, and programs, evaluate indistinguishability on each one, and then discard the ones that are not distinguishable. And if you think about it, the naive generate and test is just not going to work. You're never going to be generating indistinguishable machines in the first place. So the existing approaches that we could compare against is the very naive one, which we expect to be horrible. And there was a handwritten generator way back almost 10 years ago now in ICFP that had a custom generator that created such indistinguishable machines that could step. And the hope is that this line of work that I described, coverage guided fuzzing, is going to be somewhere in the middle. And the question is, how far in the middle? How close to the good approach is it compared to the naive one? So for the evaluation, we systematically injected non-interference violations and measured the mean time to failure across multiple runs. And here are the results. Every bar in this graph denotes a buggy variant of information control flow enforcement, and they're sorted by how effective the fuzz check was. So at the top, you see that the purely naive random generator is basically horrible. It takes 4 hours and for almost all of the bugs and finds basically none of them. At the bottom with blue, you see the performance of the handwritten generators, which are amazing. They find all of the bugs in less than a second, but it took an ICFP paper to get to that point. On the other hand, you can see the property-based fuzzing, called FuzzCheck here, as the name of the tool, is solidly in the middle. It takes less than 2 minutes to find the majority of the bugs, and finds most of them in less than the 4 hours, which was the time limit, but it's still 1 or 2 orders of magnitude slower than the very expertly handwritten generators. On the other hand, the handwritten generators required an ICFP paper and 1,500 lines of code to actually be written, while the property-based fuzzing generators required nothing other than the tooling work that was done on the backside. The user-facing effort was literally zero. So there's a lot to be done here, and this shows that there's a lot of promise in this line of work, and we've been working on making this better ever since. But there's still a lot of room to catch up with what humans can do by hand. So that sort of concludes the first part of my talk, which was focusing on the question of what do you do when the property that you want to generate for has a precondition? And the problem was that preconditions are sometimes too sparse, and you want to be smarter about generating things while taking that precondition into account. But the main takeaway from that line of work for me is that you can use dynamic feedback. You can run your precondition and use feedback from that to make future generation efforts better. Okay, but even before going to properties with precondition, there are other issues that can arise when you're doing property-based testing, even in this simple setting without preconditions. And another problem that sometimes comes up is that you're often going to run too many unnecessary tests. And to show what I mean, here is the default result for one property-based testing framework, where you're running sort correct using type information. And it's going to run 10,000 tests, and you can grab statistics about the lengths of the lists generated. So it's generating roughly, generating lists that are uniform in the length as a default. But that means that we're generating 1,500 tests that are the empty list. That is insane. Running the empty list is important, but running it 1,400 times is not going to give you a different result. So the problem that we might want to tackle is running too many unnecessary tests. On the other hand, sometimes if you were to remember all the inputs you've run through, that is going to be extremely costly the most thirsty runs, right? So you want a way of quickly deciding if inputs are going to lead to already seen behavior or not. And one answer to that from the software engineering literature is combinatorial testing. So what is combinatorial testing? Combinatorial testing is a field of study that usually focuses on how to explore different behaviors in systems that have a lot of combinations of flags, usually. So imagine you want to test a property, a function that has that takes 4 booleans that describe its behavior. And which combinations of X, Y, Z, and W would you try? Well, one thing you could do is test all 2 to the 4 combinations, but that can be exhausting and it can scale really, really badly. And the idea behind combinatorial testing is, what if instead we just tested all pairwise interactions? So look at these 5 tests. If you try it out, no matter what combination of values for 2 variables like X and W you think of, it exists somewhere in there. So if you wanted to, for example, have X be false and W be true, well, you can just look at the 3rd test. Or if you wanted to say Y be false and Z be true, then you can only look at the 4th test. And in fact, these 5 tests cover all possible interactions between any pair of variables. And this is something that scales, right? So this is something that as you have bigger domains and more variables, you need the amount of tests that exhibit this behavior of covering all of your behaviors, all of your interactions, is exponentially smaller than just exhausting all of your inputs. And just for a little bit of terminology, we have tests, and we'll say that tests cover descriptions, whereas one description can describe a lot of tests. So for example, this test that we have above, where X is set to false, Y is to true, Z is to true, and W is to true, covers both the description that expects X to be false and W to be true, and one that expects both Y and Z to be true. While the descriptions below describe both these tests and a whole bunch of others. And the idea here, the main idea in combinatorial testing is that you can maximize the effect that a few tests have in finite domains if you choose them carefully, and it has empirically proven to be effective. So the question that we asked that led to this line of work was, can we make this work for functional programs where we have highly structured data like the ones we saw in the first part of the talk, and where the inputs can potentially be infinite, right? There's no real size bound on the lists or the programs that you can run, at least mathematically. So, and since I'm here, the answer is, of course, yes. And the second part is going to focus on what combinatorial coverage means for algebraic data types, how we can use it in practice to thin generators and avoid and guide our generation to behaviors that we haven't seen before, and a bit of evaluation. So first of all, we want to start with the same thing we had before, right? We have the same example we had before of the function that takes 4 booleans, and here I have them in the form of a list. And I want to ask, this test should cover some descriptions. Which ones are they? Well, the first thing that we need to do is look at the underlying notation. So a list is just a bunch of constructors, cons chained together with nil at the end. And the idea is that the coverage is going to be phrased in terms of interactions between constructors. So for example, this particular test will cover the description cons true and whatever, the list that starts with a true. It's going to cover elements that have lists that have at least 2 elements. It's going to cover the situation where there are at least 2 consoles, eventually one between the other, or where there is at least one element whose element is at least one element in the list that is false, and so forth. There are multiple things that multiple descriptions that it covers. To be more formal about what it does, we turn to the language of regular tree expressions. So regular tree expressions are basically regular expressions in tree form, where you have some element top, sum of two things, recursion, and constructors, like the constructors const, true, and false that we saw before. And the advantage is that they can encode algebraic data types. So any algebraic data type can be written as one of these regular tree expressions. So for example, lists of booleans is the type X for which, sorry, which is either a console with true and false as its head and a list of booleans as its tail, or the empty list. And you can make this construction for any algebraic data type you want, but regular tree expressions are more expressive than that. They can encode other sets of terms a lot more compactly. So for example, you could encode the lists of all, the set of all lists whose elements are true, which is exactly what we had above, but ignoring the false part. And the other thing you can do is encode the notion of eventuality that we saw before, like there is a console that is eventually going to be followed by a console, which we will denote with this diamond constructor. And what it says is that eventually there will be a console whose head is true and whose tail eventually will contain false. And you can use this kind of language of regular tree expression to express this, but it's a tiny bit involved and I won't get into the details. But this exact thing, this eventually is what we're going to want to cover. So for an example, I'm going to turn to the simply typed lambda calculus. And this is the type of lambda terms if you encode it as algebraic expressions. We have units, we have variables drawn from some variable type, abstractions where you have some type and then a lambda term, and application of two lambda terms. So for example, in the setting, the function that takes the identity function, taking a unit to a unit and then applying it to a unit, it can be described as application of an abstraction and so forth. Now, here, the kinds of interactions that we're going to care about are interactions between eventual constructors, right? So we have eventually an application node that eventually on its left has an abstraction, but we don't have an application inside another application. What is then combinatorial coverage in this regard? We take we calculate the set of all two-way descriptors for a data type, like the two that we saw before. We calculate the set of two-way descriptors that any particular expression covers, and then we just take the division between the two. Now, how do we use this? So we have this notion of combinatorial coverage. How can we use that to make property-based testing better? So we start with our specification, our property that we want to test, and the standard property-based testing workflow. But instead of generating one list and running it through the property, we generate many. And then we use combinatorial coverage to decide which one is best, which one has led us to behavior that we haven't seen before, interactions between constructors that we haven't seen before. And of course, there's a parameter here of how many things you generate and discard, because that cannot be too much. There are sort of two things that we wanted to evaluate to see how well this works. First, larger fanouts, no matter what, should lead to lower mean test to failure. If I generate a ton of things and grab the one that shows the biggest combinatorial gains, then that should lead to fewer tests. And then we want to see if this actually leads to faster testing, not just more effective tests themselves, because even if I can create one test that will reveal every bug, if that test takes ages to run, I'm not actually seeing any benefit. So for the first part, we turn to a fancier version of the lambda calculus, system F. We systematically injected bugs in the reduction of system F and calculated the mean test to failure for vanishing fanout. So in this graph, you see basically how many times fewer tests do we need on average for every particular test. And you see that the bigger the fanout becomes, the more that much fewer times, that much fewer tests we need on average to find a bug. So in terms of the first question, combinatorial coverage has a statistically significant signal of if you run more tests and pick the one that exhibits the most combinatorial gains, then you're definitely getting something out, some kind of value out. And the question then becomes, are you getting something that justifies the extra work that you're doing in order to generate this many things and throw most of them away? And in order for that to be justified, you need running your property to be slow. You need it to be much slower than just generating a bunch of tests and seeing what happens. And one case study that makes that very apparent is testing a compiler, right? So, sorry. So we replicate the very old case study of where they generated Lambda terms, convert them to Haskell programs, and found bugs in GHC strictness analyzer. And our results showed that we could achieve a 40% reduction in the number of mean tests to failure. So where before it took 21,000 tests, it took us 15,000 tests to find the similar bugs. And it led to a 30% speed up in mean time to failure. So whereas before it took over 3 minutes to find a bug, it takes around 2.5. So in cases where running your properties slow, doing some kind of pre-processing on your inputs like this is definitely worth the hassle. So just to take a step back and see what I talked about so far. Well, the first problem I dealt with was how do we deal with preconditions? And the idea was we can use branch coverage as feedback to guide the generation process. And the second part was how do we generate more diverse tests? And the idea was to use combinatorial coverage as feedback to guide the generation process. So the main line of work that has stemmed from this exploration and that we're working on at UMD, at Penn, and with others is what other coverage can we use as feedback to guide generation? What other notions, distance, other ways of using combinatorial coverage? Can we put them all together? There are a lot of questions here that are extremely interesting and that we're looking to evaluate in the near future. And with that, I want to thank the people that were my collaborators throughout this line of work, Benjamin, Mike, John, and Harry. And I'm here to take your questions.
Thank you very much, Leonidas. It was a very interesting talk. Let's see if we have questions from the audience. I don't think I see a question, so let me ask one. Leonidas, could you comment on how practical this approach is? So have you tested this on real systems? Is there any let's say industry experience about all this?
So the main things that I'm interested in is not really industry application, is widespread adoption when you're doing verification, right? So my idea of adoption is QuickCheck becoming a mainstay in people writing their COC programs and automatically having things tested in the background. In that regard, it's extremely practical compared to nothing that was before, obviously. But the more of this kind of work we put in, the more adoption I'm seeing in terms of people using it as much out of the box as possible to test their theorems and their lemmas and everything before they're proceeding to proofs. So on that respect, I'm very hopeful. On the other hand, to get industry adoption, you need industry to start writing properties and specifications. And one of the reasons fuzzing itself has been extremely popular is you don't need to do that. The specification comes for free. And until that point where we start teaching people and enough people know what specification means and abstract away from unit tests, the kind of free specifications that you get from things like fuzzing or differential testing are still going to be dominating the field compared to the more structural specification guided things that are now applicable usually to functional programming or proof systems.
Right. I suppose we still don't have any.
I can ask also a question. So,
yes, Kosti.
One of the issues I have with the coverage-based work is that property-based testing, at least in my mind, is fundamentally a black box technique. So you can take, a program written in some other language, write some properties, and then test that program using a property-based testing tool. And the program that the system under test can be a black box completely.
Yep.
So when you open the possibility to use some gray box techniques or even white box techniques, they are better. They're fundamentally better techniques for doing testing than property-based testing.
Property-based testing is the idea that you have specifications there, right? Like that's the main part is not you need some way of generating input data and you need an oracle to decide whether that data is good in some regard. Did it reveal something that is wrong or did it reveal something that is, did it reveal nothing, right? So in that sense, that being my view of property-based testing, the way you do generation is affected by how much you know from your property. If you view it as a black box, then property-based testing is, of course, black box generation. You can use types, maybe, something like that. If you have more lightweight information like coverage, then you should be able to use that to make your generation better. If you know the entirety of your structure of your precondition, you might be able to do some static analysis and create a generator that influences things. Or you might be able to use symbolic techniques. You might be able to use something like that. On the other hand, even in systems where we have all of those techniques available, where we have things like CLI and whatever, and I'm sure Thanassis is going to talk about a few of these things right after, fuzzing is surprisingly effective because of the sheer number of inputs you can throw at the problem while getting something back from the fact that you're not black box anymore. And I think that's the really, really cool stuff of fuzzing. It hit a very good sweet spot in we're generating inputs that are more interesting than random with very little in terms of overhead compared to techniques like symbolic execution. Because yes, you might be getting 100 times better tests with symbolic execution, but if it takes you 1,000 times more to generate them, your users are getting a worse experience.
So I think we are still in time. So let's thank Leonidas again. And like this as well. And I will ask Kostis to introduce the next speaker.
Okay, so the next speaker that we have with us is Thanassis Avgerinos, who also happens to be a graduate of the School of Electrical and Computer Engineering of NTUA. It also happens that he was my first diploma thesis student. He graduated in 2009, and then he joined the Electrical and Computer Engineering Department of Carnegie Mellon University in the USA, in Pittsburgh. He has done their work that is very well known and highly cited, together with his advisor and the team that participated in the CyberGuard Challenge competition. I'm sure Thanassis will tell us more about that. His research interests are in program analysis, in testing, in security, mainly using testing and analysis for finding security problems in programs, in software testing, yes, software security. So that's all I have to say. After he graduated, he has been involved in a company with a very cool name, making us all secure. So Thanassis, share your slides. Take it on.
Awesome. Thank you, Kosti. Thank you, Nico. Thank you, everyone, for the invitation. Very quickly, before I begin, I know the original invite said to do it, the talk in Greek. I can do it in English and Greek or whatever language we prefer. Is there a preference one way or another? I've seen all the previous ones were in English, just making sure we're continuing the trend knowingly. Thank you. All right.
Χρόνια πολλά, Θανάση. Και Θανάση Βουλώδημε. Έχουμε κι άλλο. We should check whether we have non-Greek speakers, and I think there are some among us.
All right.
I guess this is partly my fault, because both Leonidas and Thanassis asked me a long time ago whether the talk would be in English or in Greek. I said probably in Greek, because we expect there to be many undergraduate students as well. So Thanassi, χρόνια πολλά, and blame me for that.
That sounds good. No issue there. Fantastic. I'll just do it in English. It's going to make me confuse myself less, because the terms are going to be the same independently of the language. And also I want to apologize for my voice. I'm still recovering from an illness. So please bear with me as we get started with the talk. Let me see if I can share my screen real quick. All right. Can everyone see my screen? Cool. All right. Again, thanks for the invitation. And my name is Yannis Avgerinos. Today I'm going to be talking about the Mayhem cyber reasoning system. I know Kostis just gave a quick intro, but I thought, because I don't get the chance to meet all of you in the audience today, say just two things about me. I grew up in Greece, did my undergrad in NTUA. Kostis and Nikos were, on my thesis committee right before I graduated. This photo is from exactly that time, spending my last beautiful summer as an undergrad in Greece. And then I did my intermediate stop at Carnegie Mellon, and around 2014, I started a company focused on program analysis named ForAllSecure. For the past 13 years now, I've been living in Pittsburgh. Pittsburgh has a wonderful weather, as you can see on the right. This is similar to what it looks right now. We have -10 Celsius at the moment, I believe. And as you can see, I've always liked challenges, and you can see two of them standing by me in that picture. So most of the work that I have done really is around a single system called Mayhem. And at this point, I wouldn't call it just a single system. I would say it's a brand of work that has happened over the last decade. Probably one of the highest points that I can say about the work is that it was exhibited in the National Museum of American History in Washington, D.C. This was in recognition of how the system performed in a fully automated competition worldwide, where the goal was to demonstrate that we can find and fix vulnerabilities fully automatically. And so I'm going to circle my talk around the system, and I'm just going to tell a story. We're not going to go deep, and we'll try to stay on time. This is a partially cannibalized talk from a much longer talk. All right, so some of the things that I want to cover today are: one, what's the challenge? What is the problem we're trying to solve? Two, I'm going to talk about one of the techniques that you can use to solve this problem. We're going to talk about how you can use this technique to solve a particular set of problems. We're going to discuss a little bit one of the important techniques that we have identified in the process. We're going to briefly talk about the cyber grand challenge, and at the end, I'm hoping to get some time to show you where we are today and talk about today and the future. All right, so the challenge today really starts from one problem. We write programs, like humans write programs. Unfortunately, we're not flawless. We make mistakes. And at the same time, we're being pushed, if you're a developer, you may know, to write code faster and faster, and it needs to reach production as soon as possible. So you have faulty beings and deadlines that are looming even faster. This has only one result. On top of it, who cares about the quality of programs? One of those people is security engineers. And if you look at the latest trends, we are actually, we're outnumbering, developers are outnumbering security experts by almost 3 orders of magnitude, 570 times more. And this trend is not getting better. People are investing in, the software business, and they want to get visibility, but no one really cares about the quality. And so you have this pressing deadlines, and suddenly you don't have the resources, the people to look into it. On top of it, it gets even worse. Are we starting from a clean slate? No. The software we have today is so full of issues that you cannot even describe it. And some of them, are never going to be fixed. Ubuntu Linux has over 100,000 open bugs at the moment, and they haven't been slowing down. In fact, the only thing we see is how the trend just keeps going up. And if that was not enough, we have very determined people, sometimes we call them the bad guys, that are interested in taking control of your computers and using them for malicious reasons. This is what we typically call an exploit. You may have heard the term log4j recently. It is a vulnerability that was released and is currently exploited in the open, taking over various servers. If you want to have a mental model of what an exploit is, it's literally a string. So for instance, this is the toy example I always give. IWconfig, it's an old utility in Linux. If you give it the name of an access point, it sets up the configuration of that access point. If you give it that very particular string and you have that a very old version of IWconfig, and because IWconfig is a setuid binary, you get root access. So when I say exploit, really I mean the types of issues that allow an attacker to take full control of your computer, and the ones that would be very horrible in practice, especially as we're thinking about putting all that software in self-driving cars, airplanes, and everything else. So how can we, can we get to a place where we're fixing these issues? There is this constant battle where the bad guys are finding something, and the defenders are always reactive. So this probably paints a negative picture, but I would say, and I think the name of the series is Challenges Computer Science. These are some real challenges, and these are some problems that still haven't been solved. Some of the questions that we are asking at ForAllSecure are two. Effectively, which bugs are important? And is zero human interaction application security possible? Is it possible to find and fix all these issues fully automatically? And our vision, put it into a single sentence, is to automatically secure the world's software from exploitable bugs, where exploitability is the property I was describing earlier. So one of the techniques I'm going to present briefly today is symbolic execution. This is one of the many possible techniques you can use. And the easy way to think of it is as a box that takes in a program and then finds inputs, some of which may be bugs. And the program can be, can be anything really. Let's say it's a C, x86 assembly, and the bugs can be really any property that you can express. For instance, memory corruption is typically easy to express. So how does dynamic symbolic execution work? It's just like regular execution with one minor twist. Instead of using concrete inputs, you use symbols. So when you start executing the program, all inputs are assigned a variable. They're not a specific value, and they can be anything. And then symbolic execution systematically explores all possible paths that the program can take. So here, for instance, you can take the true branch, and you can take the false branch. And for each one of the branches that it takes, it captures the conditionals necessary to follow that branch. So for instance, here for the true branch, S needs to be 42, and for the false branch, S needs to be not 42. So we have a logical formula that describes each path. We call this the path predicate, and we use pi to symbolize it. And we can directly convert these into test cases. And one of the ways to do this is through SMT solvers who take these Boolean formulas and give you assignments to variables. So for instance, if we gave the one to the right to an SMT solver, the SMT solver would immediately reply with, yeah, just give S the value for 42, and you can trigger the bug. The technique is not new. It's actually been around since 1970. Some of the SMT solver technology evolved around 2005, and since then there have been numerous systems. Actually, this slide probably a couple more pages. There are papers that are published every other month, I would say, on a new symbolic executor. But this is still a very active field of research. One of the key issues that still remains open, mostly, is called state explosion. And this manifests simply from how the technique operates. For every branch that we see in the program, we have to consider both paths. And then for n paths, you need to consider 2 to the n paths. So the number of states, the number of predicates that you need to solve, each one of these, by the way, is a Boolean formula, so we're solving SAT under Mutlu, is exponential. And all of these need to be checked for exploitability. So overall, not a simple problem. So how can we use, so this is the fundamental tool, this is the basic technique. How can we use this to solve some of the problems that we're interested in? What I told you earlier is I would like to find a way to describe bugs that effectively let you have control of the other person's computer. In other words, exploitable bugs. So we need to have a way to express our security policy. And this type of attacks are typically called control flow hijacks. And the reason they're called control flow hijacks is because they're literally hijacking the control flow of the program. Control flow of the program is determined by the instruction pointer. So the easiest way in English to express the a control hijack is that the instruction pointer is pointing to attacker code. And so in the next step, we're going to execute the attacker code. So for instance, for that IWconfig example that I was talking about earlier, if you take a look at the code, it's a simple C program. There is a small chain of functions. It takes in the name of the argument, that is the name of the interface, passes it in down to functions, and at the end, in the end, it copies it into a local buffer. And so if you take a look at the definition of the local buffer, it is located in the stack. There's just 32 bytes. There is no bounds checking. So this string copy could have arbitrary effects. In C, it would be undefined behavior. But what can happen, on a compiled program? What happens when, we have inputs where whose length is longer than the buffer that the structure has defined? To see that, we need to look a little bit lower. We need to take a look at the activation records. For instance, for the getInfo function, it's going to look a little bit like this. You can have a return address, you're going to have some locals, and then the buffer on the bottom. When you have normal use of the program, your input is going to fill in and fit within that buffer. However, as we said, if we provide very long inputs, we can override arbitrary things and even the return address. And if you're familiar with activation record, the return address is really the future instruction pointer when the function returns. So to do a control flow hijack, all we need to do is put our attacker code in the beginning of our buffer, add some padding, and then in the end, add the address of our buffer. So when the function returns, the next instruction that will be executed is going to be attacker code. So how can we check exploitability? How can we put that in a logical statement? It's very simple. It's literally two conditionals joined by a conjunction. The first one is, let's make sure we write at least 68 bytes. This is the path predicate that ensures we can overwrite the return address. And then let's make sure that the instruction pointer is going to be pointing to shellcode. This is the exploitability condition. This is literally where the instruction pointer is pointing to. Make sure that is attacker code. And it's literally that simple. Once you have this, generating some of those very interesting inputs that you had, it's as simple as sending it to an SNP solver and getting satisfying answers. And you can even enumerate them. You can make them more interesting. We have written papers as follow-ups on this. So this is the exact technique that we took, and we wrote our first prototype. That was around 2010. I was built on top of CLI. It's one of the well-known symbolic executors, required source, and it checked exploitability the way I just mentioned. So we tried using this on known buggy applications, and it didn't really work. We did find that IWconfig example that I showed you that is really simple in about 5 minutes, but it really wasn't working. And we have had this experience several times in this line of research, where you try out something and it really doesn't work. So one of the things that we tried was to add a heuristic on top of it. I'm not going to go into the details of this, but applying this heuristic allowed us to go from 1 to 10 exploits. And one of them, the more interesting facts for us was that not only did we find, we reproduced the known exploits, we actually found new issues in those same programs that we tested. So that was the very first, that is us scratching the surface and trying out the technique to see if we can find issues. So this told us that checking for vulnerabilities with source code is possible. However, we're interested in coming up with solutions that are not tied to a specific language. So what if source was not available? We do this with binary code. And this was literally the next step that we took in our research. And at the fundamental level, you can think of it, we just took the C and we substituted it with binary code. This is the first time we're introducing the name Mayhem. It's actually in the system just turned 10 last year. And we tried the exact same thing. We built a binary-only symbolic executor, checked exploitability the same way. We found that a lot of the issues that we had with missing abstractions, like types, buffers, and so on, caused a number of scalability issues. We developed two new techniques. One is called hybrid symbolic execution, and the other one is called partial memory modeling. And thanks to those, we were able to actually produce issues. The only one we were able to find without this technique, I believe, was the IWconfig exploit. And the results look a little bit like this. So we had analyzed both Linux programs and Windows programs, and we found issues in all. And again, we found more new vulnerabilities. So at this point, I have a very quick demo. I actually had to dig this out and get it works. And excuse the resolution, because this is a really old video. But here I'm like on a benchmark on a VM. I'm opening the IWconfig program. You see here the buffer overflow we just talked about. That expects 32 bytes, and this is the user input. IWconfig is a very small program. It's roughly 1,400 lines. And here we have the binary program. As you can see, this is a stripped binary. So we have no symbols, no source code information. And now we're going to run a single command, a single program that takes in another program. And then after we give it some time, it says exploit generated. And then it gives you a little timing. And then as a result, you're going to see it emits a few files. one of these files looks a little bit like this. If you're familiar with shellcode, that last part is shellcode. And so now if we run iwconfig with this input, let's see what happens. Suddenly, we are the root user. So we took over the computer in a matter of seconds. So at this moment in this timeline, we know it is possible to check for vulnerabilities completely automatically. Are there any other roadblocks to scale? Can we go to bigger programs? What is holding us back? And the challenge I mentioned earlier is really one of the key ones. It's still open, but here I'm going to mention one of the ways where we try to mitigate parts of it. So this 7-line program is very simple for a human to analyze. If you read it, it is a loop with 100 iterations. On each iteration, it checks if each character in the input is the letter B, and if there are 75 Bs, it will trigger a bug. So this very simple program that any of you would probably be able to find a bug in probably less than a minute has 100 consecutive branches, which means has 2 to the 100 feasible paths. So if we wanted to check those states with symbolic execution, and assuming that we have some amazing technique that scales incredibly and can analyze one state per nanosecond, it would take us 10 to the 14 years to analyze it. To put this in perspective, the believed age of the universe today is 10 to the 12 years. So it would take a very long time. This felt very dissatisfying. And it raised the question for us, can we possibly check all states of this program in a reasonable amount of time? And what we found is the answer is yes, but really not if you check one state at a time. Like literally, this does not make sense for exercising programs that have a very high cyclomatic complexity. So for attacking this problem, we can look at a different technique that's called static symbolic execution. This is from the verification community. And static symbolic execution is similar to dynamic symbolic execution with a few twists. First, in terms of inputs, it takes the starting condition to execute the suit. You can call it a precondition, and a cyclic control flow graph. So no loops are allowed. And then at the end of the analysis, it emits one formula per control flow graph node. And this formula encompasses all paths reaching that node. So to visualize this, this is an example control flow graph, and this is static symbolic execution analyzing it. Starts with a starting condition, and it starts propagating and computing new path predicates. When two edges meet, we apply a merge operator that creates merged path predicates, and then at the end, you have one final path predicate for the final node. So if we wanted to obtain node coverage for a control flow graph like that, what we'd need to do is take an SMT solver, send each one of these nodes, each one of these formulas, and get a solution. What is interesting here is that the number of formulas is not exponential. We can obtain node coverage without incurring an exponential cost, at least at the state level. So the issues with the technique are really shown if you highlight some of the words in the previous slide. So first of all, it's static, which means features that cannot be recovered dynamically. How do we represent those? Or cannot be computed statically? I said the program needs to be acyclic. Unfortunately, we have programs with loops. What do we do there? And last but not least, this is a verification technique. It has known fundamental scalability problems, mostly related to formula solvability. This is going to be an issue for us. Specifically on that last one, we actually performed several experiments with dynamic symbolic execution, and looking at the data, it seemed that at least for dynamic symbolic execution, typically the formulas are not the issue. 99.9% of queries are solved in less than 1 second. And most of it, like I believe the median is, the mean is at 3 milliseconds, the median was slightly lower and a very small variance. And other systems report similar results. So it seemed worth to explore a trade-off in that area. And you can see that once you put the pros and cons of each technique in a single picture. So for dynamic symbolic execution, you have, the benefits of dynamic execution. You have loops unrolling as the code executes. You have formula solving that seems acceptable, but you have path exploration. For SSE, you have missing dynamic features. No, you don't know how many times to unroll loops. You know that formula solving can be really difficult, but you don't get path exploration. And this is where we proposed a new technique called very-testing that try to combine these two techniques into a single one. And the core idea is to use dynamic symbolic execution to dynamically unroll loops and have access to all the dynamic features, and use SSC to analyze multiple paths simultaneously. So I won't go into the nitty-gritty of it, but at a high level, what the way the two techniques work is very simple. For dynamic symbolic execution, once you reach a conditional, you split that path predicate into two, and then you have to reason about each one of them independently, and you never bring them back together. While with very-testing, when you reach that first branching point, the first step that you do is to recover a control flow graph so that you can perform your SSC. Then you switch to SSC mode, you compute all path predicates for all the nodes, and in the end, you perform a merge function. And after that merge function is performed, you can switch back to dynamic symbolic execution with the final predicate that you have at the end of the execution. And so here you can see that we have the capability to merge states again. Now, how you do this merge function is actually pretty critical for performance. We're not going into the details of this, but let's just say details do matter. We did several benchmarks to check our performance, over 1,000 programs. This summarizes the results. We saw strong improvements in code coverage. By the way, code coverage is a metric that is extremely hard to improve. For instance, since then, we have found that it is much better to measure speed up, because to get a 5% code coverage improvement, you may need a 3 orders of magnitude speed up. Anyways, we can talk about it in the end, but let's just say this is a counterintuitive metric, because you see 5% and you're thinking, oh, this is not a big number, but actually a 5% coverage improvement is very significant. We did this by computing fewer test cases, and we were able to find more than twice the number of bugs. We have several statistics from that set of experiments. I can tell you today, companies are using the system and they have billions of test cases on their instances. And you typically see this funnel operation where you have lots and lots of test cases, then fewer crashes, fewer defects, fewer exploitable defects. We have worked with open source to report some of these. I think we raised the bug count by a couple of thousand in a day. Some of them still haven't been fixed. We got stellar feedback back then, and I won't iterate through all of this, but then if you see that last line, we said, I would pay for a service like this. You guys should definitely commercialize it. And little did they know, this is exactly what we did. And then we switched from Carnegie Mellon to actually starting a company. All right, so far we've talked about how to find vulnerabilities in software, and we've shown that this is possible. The next question that you may want to ask yourselves is, can we fix them? Because we know, like as I said, some of the bugs we've reported a decade ago are still not fixed. Is there a chance for us to automatically fix issues? And this was the goal of the Cyber Grand Challenge. This was a program that was a worldwide competition. I believe 118 teams participated. Only the top 7 would advance in the finals. And the idea was to push the state of the art through competition. So the technical challenge, when it was stated, was as follows: automate exploit finding and bug fixing without any source code. So this required for you to have exploit generation tools and techniques. Check there, we're very good at that. Root cause analysis for identifying the bug. We had tooling, but not where it should be. Static analysis to generate the patch and ensure that the patched program passes correctness and performance. This is a complex problem. This is what we worked on while we worked on that challenge, and effectively do binary rewriting for automatic patching. So it's not just necessary to understand what the issue is. You also have to be able to express it in binary code, inject it inside, and make sure the new binary is no longer vulnerable. So I can safely say that the only path to success is to find smart people to work with and let them at it. So this is what we did. We got together a very good team made up of vulnerability researchers, academics, and so on. And it was a very good mix. And we put together our third prototype. So I remember it's called source binary. Now this is the third instantiation of Mayhem. This is at CGC. And this is a little bit what the system looked like. At the bottom, you have the binary analysis platform. This is how we translate binary code into an intermediate language that we understand. And then the system had two main modules. One was called Sword. This was the offense component. It was doing symbolic execution that we just mentioned, but it was also making heavy use of fuzzing. And this is an extremely effective technique as well. We could probably have another 3 talks talking about that. We had a triaging service, something that allows you to identify what is going wrong. An exploit generation service. So after you find something that's wrong, how do you convert that into something that is actually a problem? Something that allows us to explore crashes, to look further into what is going wrong. And then we had a defense component called Shield. Shield was effectively a static binary writing framework. It allowed you to perform hardening on binary code and apply crash specific or generic defenses. And it was doing a lot of data flow analysis to accomplish this. We have published a paper on this where we were detailing some of the techniques. And last but not least, at the very top, we had the thin layer that was doing the, let's just say, the strategy of the game. How do we allocate resources? How do we choose which patches to fill? What is the right strategy at any moment? And this is what we took. We took that software system, we put it in the hardware they gave us. It's a 2,500 core, 256 terabyte of RAM machine. All of these machines were completely air-gapped and put in a single network and asked to fight each other. Before we get into the actual competition, there was a qualification round. It ran for 24 hours. The systems had to find and fix issues in 131 stripped binaries of varying complexity. We verified along with 6 other teams. As you can see, we were way ahead of the competition in the qualification round. And we also had a very strong final round that was structured in the form of DEFCON. If you're familiar with DEFCON, it's a hacking competition where humans hack each other. And spoiler alert, we won. This was a fantastic PR event for the company. And so at that point in time, we know that we can check for vulnerabilities and we can even fix them at scale. Like this is something possible. How can we help the world with this technology? Is this also possible? This is what we have been working on. Today, like what I talked to you about, handled C and maybe C++. Most of the time it was not working. Today, we have support for over 20 languages. We have integrations with every single thing that enterprises may ask, including open source fuzzers. So not just our own Mayhem. We have support for any environment that you can think of, from x86 to MIPS and PowerPC. We have been extending them more recently with support for fuzzing, RESTful APIs, and even libraries. For the libraries one, we actually found time to write down the paper and send it to ISC. It's going to be presented later this year. It's called GraphFuzz. Hopefully, we can talk about it at some time in the future. And last but not least, we have integrations with every tool that developers use today for embedding these solutions into their SDLC. Oh yeah, and a shameless plug here. We are hiring. We actually have people in the United States, Canada, and Greece. So if you're interested, consider joining or forward this to your students. They may have interest in some of these categories, and remote work is possible. Last but not least, none of this work is just my work. It would have been impossible with all these amazing individuals working side by side with me. So how close are we today to our vision? Can we fully automatically secure the world's software from exploitable bugs? I would say we're closer, but we're not there yet. I could probably spend several minutes talking about each one of the things that the future holds for us, but I do want to mention something like the one that I had highlighted here. If you think a little bit about program analysis and the problem we're trying to solve, it's literally a search problem. We're taking a thing, a maze, and we're looking for an exit or some specific issue. It's the needle in the haystack problem. And symbolic execution or fuzzing or all these things are literally a translation step, something that takes you from the program to actually applying these techniques. We have well-known search techniques that I guess are very effective. The thing that seems to be missing, and I think ties back to I think what Leonidas said a few moments ago, is it's all about education, all about simplifying the problem, lowering the bar of entry, and also offering a framework for users to introduce these techniques in the workflow. Because this is really why today, for instance, we don't have this fully automated throughout the world. Like I think we have had the tools for a very long time. Really, the issue is more of a social one. How do we push the barrier? How do we introduce these tools in a way that are not in the way, not standing in our way, but they're enabling us. And at the same time, it's not too difficult. And with that, I would like to thank you and open it for questions. I also said I would have a demo, so I'm going to have it run in the background while people are thinking of questions they may want to ask. All right, so I showed you the state.
We can have some questions while Thanassis is doing the demo.
So I'm going to choose a LightTPD server. Like this is a server that's running in several devices these days. You see this, I just chose a Docker image, auto-extracted the configuration out of it, and I just clicked start. And so I'm going to just let Mayhem go. I could have had this integration run from a CI pipeline or from GitOps or whatever your favorite deployment is. And so we see that the system is starting up. It's trying to find workers to allocate the analysis. It's computing some static properties of the target. We see, for instance, it has certain protection zones, some others it does not. And we see it's about to start finding test cases. And yeah, it's alive. I believe this particular version is vulnerable. So there we go. It did find an issue. It's not going to stop. It's going to keep finding issues until we tell it. And if you look at it, this is a little bit what it looks like. It shows you a quick struct trace of what's going on. You can look a little bit further. You can see, for instance, how to invoke it, how to reproduce the issue. You can look at the outputs, the backtrace, the disassembly where the issue is actually occurring, what's the register state, the signal number, memory maps. Anyway, all kinds of issues that could be interesting. And then we give you a way to categorize all these findings, integrate them with your bug finding system, and so on. And with this, yeah, any questions for me?
Thanassis, I have a question for Larissa here. So there is this increasing trend that many of the pieces of modern software are getting replaced with neural networks and complex decision-making mechanisms. Can you comment how these techniques extend to this new type of software development?
That is exactly so here's the thing. There are so many smart brains in this room, and this is exactly why I wanted to bring up this point, because I think there is an opportunity here. There is something that is missing. There is incredible work in coming. So think about it. Like for instance, even in the latest paper we just published at ICSC, I can tell you, we looked at a very specific subset of the problem. We looked, for instance, at C libraries, and then we took a look at why some of the common solutions do not work. And then we thought, we put our minds down and we thought really hard, and we're like, yeah, we should try that. And lo and behold, okay, cool, that worked. And this is better than the default. However, I feel very dissatisfied because I'm thinking, okay, I came up with a solution, but in the domain of solutions, who knows how many there are? And even the problem of me finding this solution is something that could benefit from something like you just mentioned, right? Like I have to say, I am not well versed in neural networks, machine learning, advanced machine learning. Like I know the basics, but it's one of those points where I feel the only thing that's missing is someone putting them together. That's the research part. But then there is also the social part, which is right now, let's say you're a software developer. What is your incentive to write high quality code? It is true that maybe it's part of your, let's say it's part of your bonus structure, or it's part of your compensation. But for every organization that has tried this, usually I have heard the following: the more bugs that you fix, the higher your bonus is going to be. Turns out if you do that, humans are going to start introducing bugs in their code just so that they can increase their bonus. So in other words, there are two. This is just the right question to ask. I think from a research perspective, there's definitely an opportunity to use machine learning to actually come up with better techniques for testing these programs. It's a little bit unclear how the integration would work and what the appropriate framework would be. Like, is it symbolic execution? Is it fuzzing? Is it something else? How should this be expressed? How do you allow the domain of solutions to remain open enough, but at the same time tractable? And then there is the other part, which is how do we enable more and more software developers to introduce such solutions in their life, and make it part of the I guess the SDLC that everyone thinks about. Did I answer your question?
Yes, this is great, and thank you. And as you mentioned, I do believe there are a lot of exciting opportunities in the intersection. So it's a great topic, especially for young researchers in the audience. I would encourage them to take a look.
We agree. Any other questions? Right. I think I'm also 3 minutes over.
Okay, so if we don't have any other questions, I see something in the chat. Dimitrios
Would like to be unmuted.
Yes.
Hello, nice presentation. I'm coming from the environment of network orchestration. So we're facing a similar situation where we'd like to, where bugs are not getting propagated from let's say orchestration stack. So it's something like we're facing a problem where you write your test, but we'd like to have tests that follow up an orchestration, let's call it like that, path. So we don't know how to tackle this kind of problems. Do you have any kind of views on this case?
When you say network orchestration, are you talking about the protocol layer, or are you talking about systems of systems?
System of systems. Like, I mean, you have the Kubernetes, which is orchestration of Dockers. So you're setting up your test cases for Dockers for, let's say, the for kernels of computation. But what you'd like to have is something which produces, let's say, the quality of systems, of software systems, not of, let's say, hardware systems.
Nope. completely makes sense. I can tell you, we've actually done research on this for the past 3 years. There is no easy solution. The thing that I can say does not work is take the VM approach and yeah, all these containers, run them in a VM, and then assume this is all, one unit and try to apply the same techniques. There are significant scalability issues. You will be able to run examples like the AW config example, but if you try to scale to more realistic problems, this becomes very, very hard to scale. As far as how do you propagate things between systems, what we have tried so far is componentization. So we don't look at the whole thing as one blob and then try. Well, actually, we've tried that as well. You typically have very limited triaging abilities, like you may hit an issue in the database or in the API that's listening to the database 3 layers deep. You're not going to know about it in most cases. I think 90% was the number we observed. So what we're trying right now is effectively instrumentation that's going to be monitoring each one of these services independently. And so when something goes out of the ordinary for each one of these, we have that visibility from the instrumentation layer, and we can communicate it to the outside. You can still get false positives because, for instance, some of them may be legitimate. Like, for instance, maybe this particular API is supposed to crash when, a very specific bad thing happens. So I don't know if that answers your question.
Somewhat. If I may, I have a couple of seconds more. So sometimes, in networks, you do some kind of rollback. So you see, because it's typical for humans to, if there's a mistake, to roll back to retrieve the previous situation, which is not normally the case with a software approach. I mean, normally in the systems you have exceptions. So you have exceptions, you have errors. So you communicate the error, but this is not the typical, let's say, behavior as it's in the humans' behavior. So we'd like to have something similar from the software perspective or the program's perspective.
I can tell you what you just mentioned also happens sometimes for software. Like they're known as renewal processes. And you may have them even as part of your system definition to you effectively define a snapshot of your software and periodically or on events reset them. This assumes that all state, of course, is outside of the software stack in a medium that you trust. Or for instance, you're running, let's say, AWS Lambdas, right, or something else that is stateless, serverless. Yes. The idea is literally, in some cases, we cannot manage the state that gets accumulated over time, and we feel the need to reset. So this problem does exist in software as well. It does complicate everything I just mentioned because, for instance, let's say I just found this input that if sent to your system of systems is crashing, service number 5. Well, now I try to reproduce it and it no longer happens. And the reason it was happening like that was because of all the sequence that was up to that time, and maybe even the interleaving of threads that happened between these services as they were running. So reproducibility becomes harder. If anything, having stateful services only complicates the problem. And by the way, this is a complex topic. There's no chance we're going to figure it out. But of course, feel free to email me if you're interested to chat more about it. All right.
Okay, so let's thank Thanassis once again. And χρόνια πολλά ξανά.
Thank you. Ευχαριστώ πολύ. Να είστε καλά όλοι και καλό απόγευμα.
Ευχαριστούμε επίσης, Θανάση, και χρόνια πολλά και πάλι. We thank both speakers of the session, Thanassis and Leonidas, and the chairs, Nikos Papaspyrou and Kostis Agonas. Yeah, thank you very much all, and the talks were really, really nice. I believe we all enjoyed very much. So now I guess if if our next speakers are not in a rush, I would suggest to have a normal break of 15 minutes because I guess we are all a little tired, so we may need that time to make a coffee or whatever. So if you agree, let's say 18:25. Yeah, okay. I know some live with their coffee. Java. Okay. Good. So let's resume in 15 minutes, 18:25. So hi everyone. I think it's the right time, yeah. So we are heading for the last session with two more NTUA alumni that now have a great careers abroad. So it's Theo Rekatsinas first, and then it is Dimitrios Stamoulis, and Dimitris Tsoumakos will introduce Theo. Dimitri, please.
Thank you. Thank you, Ari. It is with great pleasure that we welcome Theo. So Theodore, as Ari said, graduated from the ACE department of NTUA in 2010 from DB Lab, right? And then he got his PhD in 2015 from the University of Maryland, Computer Science Department, under Lies Getur and Amolde Spande. On a side note, they were my own PhD defense, those two people in 2006. Wow. So after that, he spent 2 years as a postdoc at Stanford, right? Before becoming a professor at Wisconsin Madison. Right now, Theo is at Apple, where he's leading the knowledge platform and the graph machine learning team. And he's also a professor in the Department of Computer Science at ETH Zurich. Theo is doing a lot of stuff at the intersection of machine learning and data management. He's doing very interesting things. And Theo, the floor is yours. And thank you very much again.
Thank you, Dimitri, for the kind introduction. And before we start, I'd like to thank you all for the invitation. It's really an honor to be here amongst mentors, professors, and people that helped me establish my career. Hopefully, I'll be able to convey some of my journey and experiences to younger members of the NTUA community, and I'm really looking forward to the new blood, as one would say. So before we start, I'm obliged to say that, give a disclosure that whatever I am saying is not related to Apple. It is based on my research with my students at Wisconsin and also collaborators. So at no point of this talk I'm actually speaking for Apple. I'm just speaking for my own research. So today I will talk a little bit about the research I've been conducting over the last, I'd say, 7 years now, which is around data-centric debugging, data cleaning, if you will, specifically for in the realm of intelligent analytics and smart decision making. So before we start, I'd like to talk a little bit about my journey. Dimitri, you mentioned a little bit about it. I guess one of my goals was to travel in the US from coast to coast. I started from Maryland, went to the West Coast in California later, and then I ended up in the Midwest in Wisconsin. I deviated a little bit from my academic path to start a company based on my research called Inductive, which was later acquired by Apple. So that brings me now in Seattle. It's still very dark outside here. And the journey will lead me back to Europe this year, where I'll be starting and continuing my academic career at ETH in Zurich. So without further ado, let me start a little bit with the more technical journey of my life. So I had always been fascinated about data management and especially how it enables us to make smart decisions. So it is really data that encodes our domain knowledge about the world And it is data that catalyzes automated and intelligent decision-making. And not only this, but it is actually data that has been driving all the innovation behind modern AI that we're witnessing over the last decade. And this is a trend that it's not just recent. It has been going on for at least 100 years. People have been publishing data sets that are acting as benchmarks. These data sets drive innovation. These data sets enable us to design new solutions, new algorithms, and so on. So it's all about data fueling this interest and this what we're witnessing today with respect to how the new evolution of AI that we're living in. However, while this is kind of a very rosy picture and a very optimistic view of the world, data also corresponds to a major challenge in machine learning and AI deployments in the real world, in industry, in large-scale scientific experimentation, and so on. So there are recent surveys from market research companies like Refinitiv that basically indicate that 43% of the people say that poor data quality is actually the biggest barrier when it comes to deploying machine learning in production. Also, 38% mentions that they lack the data that they need to be able to perform smart decision-making using the latest and greatest AI tools. And not only that, but so ML requires heavy investment really in data preparation. But at the same time, one has to be extremely careful with low-quality data because it can lead to biased and unreliable models. For instance, here you see that it's a noisy picture of a speed limit sign for 80 kilometers an hour. The model believes it's a stop sign. Imagine what will happen if you're driving with that speed and you suddenly come to a stop. Most likely you'll create an accident. So data quality, it's kind of a notorious problem in all these deployments. And it has a lot of different dimensions. Many of the dimensions, and I'm using images here because it's easier to understand the problem. Many of these mistakes of data quality issues have to do with wrong labels. You see in this benchmark called Caltech 256 saying that this image contains grapes. I think there's just a few pixels on the table that correspond to grapes. You see cases where you may have, we'll see later, missing values. Definition disagreements are a big problem. For instance, in ImageNet, somebody was asking, what should we classify this image as? And people responded as paintbrush. However, you could argue that it could be a pot, it could be sage, it could be a number of things. So we need to find a common definition of the labels we're looking for. And similarly, you may have these issues come up in different types of data. For instance, in text, this is a review from Amazon that is labeled as neutral. People believe it's positive. Personally, I think it's closer to neutral, but that's up for debate, as you can see. So there are a lot of problems when it comes to data that we're feeding in modern machine learning pipelines. And in fact, data quality is a central piece of the modern machine learning lifecycle. Starting from model development, where you need to clean and understand your data, training, where you need to actually validate your feeds that you're giving to your model, make sure that they capture your distributional assumptions. And also you have different types of treatments. For instance, there's this data-centric treatment that I just talked about, where you need to clean and understand and fix mistakes of your data. But you may also have a model-centric treatment, where you want your model to be more robust and tolerate noise and make reliable predictions. So there's a lot of increasing interest in both the AI community and the database community. I encourage you to look into these two workshops, DEAN, which is part typically of Sigmund, which is data management problems for the end-to-end machine learning lifecycle. And more recently, Andrew started this initiative about data-centric AI that really puts forward a data management-centric view of AI. So this was at NeurIPS this year. So what are the differences between data-centric versus model-centric? I'll try to illustrate them quickly through these two examples. So data-centric approach is really seek to fix bugs in the data. For instance, here we have a data set that shows really different addresses and the tax rate. And imagine you're an insurance company that you want to use this information to design better models. This data set may have a lot of errors, invalid tuples, erroneous values, missing information, and you typically want to perform what we refer to as data repairs, where you may fix and replace some of the values. You may want to impute missing values, or you may want to perform data filtering, where you remove certain examples. Typically, these approaches they're very well understood, especially in the data management community, with data cleaning being a very old problem. You do have guarantees on the quality of the data, and you are able to actually use this data for different downstream models. And in many cases, these approaches can be intelligible and interpretable by humans, so they can understand actually what were the errors with the data they were using. There is the other extreme, and this is coming from the statistics community and the ML community, where people put forward a model-centric approach, where you actually want to make your machine learning robust, immune, if you will, to noise. So in these cases, you have a lot of great results that rely on robust statistics that will start performing perturbations, typically worst-case perturbations, and add worst-case kind of noise, known as adversarial noise, to your inputs, in an effort to try and obtain a model that will focus really on the features of the data that matter and are not so susceptible to this kind of attacks. And what you obtain back is a specific version of your model where that model can actually tolerate a lot of noise inputs with worst-case guarantees. So you have these nice guarantees for worst-case attacks. However, the outcome is very specific to a trained model. And it is really studied mostly for continuous domains like images, more recently with respect to text and so on. Putting on my more practical hat, industrial hat, I would say that there is a lot of room for improvement in terms of scalability and efficiency for these solutions to be deployed in real life. So my work focuses really on the data-centric types of approaches. And the goal of my research has been to streamline data quality management. Data quality management being how we can solve all the problems that I mentioned before on error detection, data validation, imputation, and so on. And really the question that has been driving the research that I've been conducting with my collaborators and students is how can we automate data debugging? Our focus is on the problems I mentioned, data validation tasks. And really the opportunity that we have identified is that instead of using business logic or rules for performing this debugging, one can actually use machine learning, unsupervised machine learning, to serve data cleaning. And you have kind of a chicken and egg situation where you're using a specific type of machine learning to clean your data that you're going to use for downstream machine learning models. However, there's a key distinction here that there's a very nice connection, if you will, to information theory and error correcting codes, which basically says that data in the real world comes with redundancy and structure. Attributes can be dependent, they have strong correlations, I have repetition of examples. So I can exploit this redundancy and structure to actually learn an error correcting model using machine learning that I can apply to solve all these data validation tasks. So let me give you an example just to be a little bit more concrete as to what do I mean by redundancy, what do I mean by structure, and how it can help. So we'll start with the simplest analytical model that is very common in a bunch of cases. I want to compute the mean value from the following of a vector from the following samples. And the problem that you see here is that I have empty non-values. So I have missing values for certain samples. So what would practitioners do? Practitioners would say, fine, I will assume that all the attributes are independent and I can compute the coordinate-wise mean. That will give me the following vector. A little bit, a data scientist, if you will, that is a little bit more careful would say, fine, I don't know if they're really independent or if this violates my assumption. So I'm going to remove all the fields or all the samples that have missing values. And I'm going to take the mean after filtering. That will give me yet another different vector. But I claim that actually we can get a much better estimate that outperforms both of these when it comes to statistical guarantees and when it comes to being closer to the true mean that generated this data. And this is my improved estimate after fixing some of these missing values errors. So the reason why I can do this is if you look into the data more carefully, you will notice actually that the data has redundancy and exhibits structure. In fact, if you look more carefully, you will see, if you were to ignore these missing values, you will see that attribute x1 is just the sum of x2 and x3, and then x4 and x5 are independent. So by exploiting this structure, I have the opportunity to fix some of these missing values and thus obtain a better estimate. So this is kind of learning really what is my error correcting, if you will, model by exploiting this kind of redundancies in my data. So this is a very kind of trivial example to demonstrate why these kind of redundancies are extremely helpful. And this type of structure did form the basis of a lot of the results that I'm going to discuss next. However, let me tell you that this problem of robust mean estimation is itself extremely interesting. And in fact, we recently published this result that says performing this two-step algorithm for robust mean estimation, first recovering missing values and fixing errors in your data using these dependencies, and then estimating the mean using either your favorite robust mean estimation method or standard statistical estimation methods. It is actually information theoretically optimal. It is better than robust mean estimation methods that were proposed before, that they assume that the entire sample is corrupted. And it gives you guarantees for worst case attacks where the attacker is allowed to actually go and perturb or introduce errors arbitrarily to any column, even your entire data set. All the samples could be corrupted, some of their coordinates, but if you have structure and if the corruptions don't destroy the structure, the row space of your data, you can get really strong guarantees and information theoretically guarantees by using this approach, this meta algorithm. However, in real world, structure is not as simple. Like the linear dependencies that I just showed you, structure is a little bit more complex. In many cases, especially for business intelligence data, you have domain constraints. You have what we refer to in databases as integrity constraints, so functional dependencies, for instance, saying that the zip code of a location should determine the state. Or you may have domain constraints telling you that my state, I expect it to be just 2 characters, and the zip code should only be numeric values, 5 digits. You may have external information, external knowledge, so typically catalogs or knowledge bases that include information about the real world that you want to encode in these error correcting models. And finally, you have a lot of statistics that you can leverage from your data set. For instance, redundancy here allows you to recover statistical dependencies. For instance, this conditional dependency here that indeed the zip code, this zip code indicates that we should be in Wisconsin. So using this structure, the overall approach and the overall theme of the systems that we have been introducing is the following. We have the structure. We want to learn a model to reconstruct the data and use that model to detect and remove errors. And once you learn this data reconstruction model, actually a lot of data quality tasks correspond to the same inference queries over the same model. So you can perform validation of tuples or specific values. You can perform repairs by asking the model to reconstruct certain values of your data set. And if confident, you can accept it as basically the value that you should be imputing. So this approach has led to a bunch of different works, both theoretical and practical systems. I will start with Holoclean, which was basically, it formed the basis of inductive, and it formed the basis of this entire journey. So the idea behind Holoclean is that we focus on tabular data. For instance, here you see a data set where we have logs for taxi trips across the different census tracts. And what we are trying to do is we will try to model this data set as really using probabilistic semantics. So we have a lot of information that we can encode. The first one is that we will represent its cell as a random variable, and we will be asking later on to predict back what is the value of this random variable. We have a lot of dependencies that we can capture as co-occurrences. And we also have these domain constraints that introduce dependencies across tuples, across different samples. So in our first take, when we started this work in 2017, we focused really on a standard model, which is called the probabilistic graphical models. These are models that really capture local features and domain constraints very well, and also allow you to encode sparsity. So here, basically, each cell would correspond to one of these circles, the random variable. The factors, the rectangles that you see here, capture the dependencies across the different values that these cells should take. And if you learn the parameters of this model, of this machine learning model, you are able to start running inferences over the model and be able to reconstruct, predict back, if you will, what are the most probable assignments to these random variables, given values, fixed values for other variables in this network. So in basically what these questions boil down to is, imagine this blue cell there that was missing. We would ask the model, hey, given the information that you have from other tuples in the data, and given the information that you have from this tuple, can you predict back that value? Of course, there were a lot of limitations, and we had to perform a lot of tricks to scale inference over these networks. Inference over these networks, in the worst case, is SRP hard. It's an extremely, it's a computationally challenging problem. So we had to perform a lot of tricks, for instance, start relaxing some of the constraints and rewriting these networks to look a little bit more like logistic regression. We also had to specify kind of filtering constraints that will allow us to really solve the problem similar to classification over an extreme number of labels. In many cases, the domains would control linearly with the size of the data that we had. So it was actually quite hard to use. At the same time, one of the most interesting questions we got from users is, okay, you rely a lot on domain constraints to be able to capture knowledge. However, explicit specification of these constraints might not be feasible. As a user, I may not know these constraints, or I may not have full coverage of these constraints. And in many cases, all I really want to do is just give you the data set, and then you decide what's wrong. You decide what you can fix and what you cannot. I don't want to deal with any more knowledge. And also the approach was limited to categorical data. So these were the main limitations of take one. To address these limitations, we started looking into more advanced machine learning models and basically modern approaches to neural networks. And in 2020, we introduced this simple approach that relies on a very famous mechanism in neural networks referred to as the attention mechanism that really captures dependencies and relationships across different entries in your dataset. The main difference between what we did and the mechanism that typically is used in transformers, which is the model that powers now, Google Translate, a bunch of different models in NLP, and it's deployed widely in production, is that instead of focusing on dependencies at the value level, we focused on dependencies between attributes, so schema level relationships. And we asked the question, can we have a very simple neural network that will represent our values as vectors, represent the attributes themselves as vectors, and try to reason about the correlations between the attributes using this attention mechanism, and finally be able to utilize these dependencies and information to actually predict back and reconstruct our data set using this simple network. And just to give you an idea of what the schema level attention would do, really it's given a target attribute that I want to reconstruct and predict, it will find which of the other attributes are more important and use that to predict its value. So in this case, for instance, if I want to output the county, given information about the city, zip code, and age of a person, I will take the embeddings of the gold strings that you see here. So I will take the vector representation of city, of the term city, of the term zip code, of the term age, identify which of those are closer to the vector representation of county. That gives me kind of the schema level dependencies that I need to be paying attention to. And then you take the embedding of the actual value out of these important attributes, and you really find kind of a nonlinear combination, basically, of these vectors to represent and reconstruct the vector that you have. And why this mechanism? Well, this mechanism, we used it because it can actually capture sparse structure dependencies, and there's a lot of great work that connects it to graphical models. And here you see one of the matrices that was learned by this approach in Holoclean. When, as imagine, one recovers very dependencies that confirm logical constraints that users would use in their data. For instance, here you see that I want to predict back the drop-off census tract. All I need to pay attention to and focus on is what was the latent log for the drop-off centroid. The pickup doesn't really matter, and you see this in the heat map that you see. The pickup does matter for the pickup census tract. So this sparsity and these very strong dependencies at the schema level, they're actually interpretable, and now even allow the users to identify business kind of logic and business rules for their own data that maybe they were not aware about. So does this work? We conducted several experiments. Here I'll just highlight one of those. And this is a benchmark data set that Google was using for their data validation toolkit called TFX. This is part of TensorFlow, their main platform for machine learning. The goal there is you have exactly this taxi data set that I mentioned, this information about pickup and drop-off. And you have naturally occurring missing values. So they are not random, they're systematic errors. So what you see here, for example, is I'm missing the information about the census tract. However, I have similar latent log with these other two entries. So can I actually use it to predict back and fix these mistakes by assigning this specific census tract? Hopefully you can see the pointer over the slides. So using this very simple technique referred to as AIMNet, we actually get significant improvements against a variety of solutions, starting from our original solution with quantization, because we wanted to be able to convert numerical values to categorical, but also very important solutions that have appeared in the ML community, like XGBoost, which is kind of the state-of-the-art for gradient-boosted trees, state-of-the-art autoencoders and generative adversarial networks, but also simpler solutions like random forest and linear regression. And you see that compared to all these approaches, we actually get a significant improvement just by leveraging the structure of the data and these higher level dependencies. We get 40, close to 40 F1 points. This is absolute F1 points improvement compared to the next best method. And not only this, but we're also significantly faster because our network is very, very cheap. You just learn your vectors, the vectors of the values, the vectors of your attributes, and off you go. So beyond these use cases, this approach was part of the open source product of Holoclean, and as part of Inductive, we applied it in a variety of use cases in industry. to solve different problems, if you will. So I'll talk a little bit about one of the problems here, which is that of data categorization. So in market research, people have a lot of they're missing canonical IDs for the purchased items they have. And this was in collaboration with a company that before they were applying manual annotation, and it would take them months, tens of months actually, to be able to clean the data before they can use it to perform market research. So using our approach, we were able to clean the data that they wanted to use for their decision-making pipelines in less than 15 hours. The accuracy that we got compared to the manual labels was 97%. And the interesting thing is that for the remaining 3% that we didn't get an agreement with the manually curated labels, we found that for 70% of that, the ground truth was actually incorrect. So what humans were agreeing that it is the right SKU was actually incorrect. The prediction of the automated model was much more accurate. So we have solutions where we actually exceed the performance of humans exactly because we didn't have this problem of disagreements that I mentioned at the very beginning of the talk. So HoloClean overall would lead to significant improvements in these pipelines and streamline many of the processes that that company at the time was using. Other use cases that are very similar in terms of the definition of the problem, but very different when it comes to the practical applications, had to do with error detection in demographic data, and this was used for policy decision-making in insurance, key performance indicator tracking, where you want to identify outliers, and of course, imputation of numerical data for industrial machinery monitoring. These were all applications of HoloClean back in 2018 and 2019. So the question after HoloClean is, I would like to move on to the next kind of phase for this line of work, was that of Pickett, which is, can we apply similar approaches specifically to data sets that will be used to train models, and not only to the training data, but potentially can we use this the idea of reconstruction at deployment time and be able to detect inputs, queries to a model that will lead to wrong predictions. So more recently, we introduced Pickett. So Pickett follows a similar approach that uses these transformer-based models for data validation, but our focus is really on machine learning pipelines. And we wanted to design Pickett as a plugin that can serve different machine learning models. So it is still a data-centric approach in the sense that we don't obtain one instance of a specific model that is robust to the noise that we have. But it is more of a plugin solution that will allow you to either detect outliers in your training data, but it can also allow you to detect what we refer to as victim samples, queries that they are so noisy that will really make the model that you have trained downstream misfire and predict something erroneous. So let me dive a little bit deeper into what the treatment of Pickett looks like. So during training, as I mentioned, we want to guard against corruption in tabular data. So at training time, you have a data set, for instance, like the one shown here on the left, where you have tuples that they're actually wrong. So you want to be able to remove these, filter out these corrupted samples in an effort to learn a much better model that basically focuses on the in distribution, if you will, samples. And during deployment, what you want is to be able to say, hey, are there samples that are so perturbed that actually will cross the boundary of the machine learning model that I have trained? This is separate than Pickett. And in this case, I will obtain a wrong prediction. So can I flag these samples during deployment time so that I surface them or I reject basically the prediction of my model, or I surface it to a human for verification? Notice that in many cases, noise may actually not lead to a wrong prediction. So in these cases, this will not be a victim sample. So the flow of Pickett and the whole idea behind it is basically, again, to use this idea of reconstruction. So given a noisy training data set, what we will do is we will start training this reconstruction model that uses similar attention mechanisms. I will go over them in a second. But what we will try to do is try to predict back every single input, every single value of this data set, and we would actually track the loss that this network would incur. So as you can see here, I start from a tabular data set. It goes and gets encoded through a network that I'm learning. We refer to it as PicketNet. What you get back is reconstruction losses for every single value, and then you use these reconstruction losses to identify if an entire sample is actually corrupted and should be removed or not. And we have a couple of, we have two thresholds here. It doesn't matter if the reconstruction loss could either be too high or it could be too low. In many cases, when the reconstruction loss is too low, and basically it becomes kind of a left side outlier for this kind of normal distribution, it typically corresponds to adversarial attacks that you have in your training data set. And the reason is because adversarial attacks would like to have a lot of replication when it comes to training examples that are off distribution in order to try and confuse the model. So this technique of having two thresholds over the reconstruction losses allowed us to capture both cases of naturally occurring noise, including systematic noise, but also adversarial worst case noise. And the network here is very similar. It's a little bit more complex, but very similar to that of AIMNet in the sense that, again, it tries to capture both high-level dependencies at the schema level, but at the same time, we extended it to capture dependencies at the value level to be able to handle more heterogeneous data sets. So the internal cell, if you will, of this network is a multi-stream attention mechanism. So you have two streams, one focusing on the higher order dependencies, where basically here we just say how relevant is the query that we are asking, the value that we want to impute with respect to attributes. And at on the other side of this other attention mechanism allows us to capture dependencies with respect to values. And really, the benefits is kind of a trade-off. The value stream allowed us to have sufficient flexibility to capture heterogeneous distributions. If you have a tabular data set, it doesn't mean that all the points were actually generated from the same distribution. They might just follow the same schema, but very different distributions. And the schema stream acts really as regularization that tries to capture these higher level constraints as the business rules that we saw before. A couple of experimental highlights for this. Here, the experiment that we conducted was to introduce actually poisoning attacks. This is worst case noise. And what you see is different mitigation strategies of removing and fixing these errors. And then after having removed the errors, we trained different downstream models. So we tried it on neural networks, support vector machines, logistic regression. Every time, really, what happens is you take this downstream model and you train it on the output data set from each of these mechanisms. So we tried isolation forests, 1+ SPMs, outlier detection methods that are kind of traditional. We tried the state-of-the-art robust autoencoder that tries to perform similar reconstruction, apply similar reconstruction ideas to the problem, Pickett. And then we also compared against really training with a clean version of the dataset, CL, that you see here, and training with a version of the dataset where we didn't apply any cleaning at all. So the interesting thing, what you see here, is that actually Pickett will, if you take Pickett, filter the dataset with Pickett, and then train your downstream machine learning model, you see that the accuracy that you get is actually very similar to that of having the clean version of your data. And it outperforms many of the baselines. And interestingly, the baselines actually are much closer to not performing any cleaning at all. So in this case, if you perform, again, we empirically validate our theoretical analysis from the very beginning. Indeed, if you perform very precise cleaning of the errors that you have in your dataset, you are able to learn much more reliable, much better models. And this is generic enough that can be applied actually to a bunch of different models. It's not specific to the neural network architecture you want to use downstream, or if you want to use an SVM or logistic regression mechanism. Similarly, at prediction time, the results here are not as strong. However, we find that basically the same reconstruction can be used as a feature for building, basically for designing kind of a model, a simple model like a logistic regression that will accept or reject the prediction of the final trained model that you have. And we find that compared to a bunch of state-of-the-art victim sample detection models that have been proposed in the literature, actually Pickett performs across different use cases much better. So this is kind of the extension. Pickett really was this extension of the same reconstruction approaches to data validation in machine learning pipelines. So before I open up for questions, I'd like to touch base a little bit on what is next and some of the problems that we have been focusing on recently, and then we believe that will have a lot of impact in making these systems even more practical. A big challenge in AI is how to encode already knowledge that we already know, and there is kind of agreement that in the community that knowledge graphs, so this kind of heterogeneous graph structured resources that capture information about real world entities and their interactions are the way to encode and kind of inform machine learning models, modern machine learning models about our knowledge of the world. However, these graphs are noisy. And of course, we want to be able to remove mistakes that are either introduced by humans or automated extraction mechanisms that construct these graphs. So we want to be able to extend these ideas behind Holoclean and Pickett to heterogeneous graph structured datasets. The problem, though, is that in real world, these datasets, when you want to embed really and represent these nodes as vectors over hundreds of millions of entities and tens of billions of facts, you immediately end up with representations that are in the scale of close to terabytes. Hence, you cannot put this data into accelerators, into GPUs, to be able to perform scalable machine learning over these graphs. So more recently in my lab, we started looking into this problem of how can we optimize large-scale machine learning over graphs, basically deep learning, for how we can optimize it with respect to resource utilization. And we started focusing on this problem first for embedding graphs and representing their nodes and relationships as vectors. And here, this project is called Marius. More recently, we published our first results on OSDI. We have extended it since then to much more complex networks. And just to give you a comparison, a highlight with respect to industrial systems like PyTorch Big Geometric from Facebook, the Deep Graph Learning Library that is supported heavily by Amazon, you will see that actually these systems severely underutilize GPUs when performing these machine learning over graphs. However, with our system, which really uses novel data replacement policy that is specific to the workload that is incurred by these machine learning models, we are able to reach utilization of GPUs that exceeds 60%. So we are actually able to perform graph learning over billion edge graphs actually in a single machine with a single GPU. And we are still faster than these systems when using 8 GPUs and also when they are using distributed settings. So this is something very exciting. And it's something that we are investing a lot of time in my lab, this Marius project. So selfless plug, if you're interested in these problems, feel free to reach out. We're hiring both at EDH and Apple, and we're expanding, so happy to discuss different opportunities with people that might be interested. And with that, I'd like to conclude my talk and leave you with this overview of learning these models for reconstructing these error-correcting models, really, of data and using them to automate data quality management. Thank you.
Thank you, Thodoris. Very interesting. Thank you very much. So, any questions to Theodore? If not, I have one. So, yeah, the initial question was if you are trying, and you answered that in the end, that you are already trying to apply this to graphs. How about text?
Text is actually, in my opinion, harder than, than graphs. And the reason is that you really need to be able to identify and align these kind of dependencies, especially if you want to start blending text with other types of data. So so in Picket, for instance, we do capture text attributes, but the text has to be kind of short spans and strings. So think of it as very brief descriptions potentially of the entries that you have. And we can detect if it is wrong. We cannot fix it. So there are different stages. We can identify if a text description is actually erroneous, or if there is information in the text description to potentially identify that the categorical attribute of your input is erroneous, but we have not focused on fixing things. It touches a little bit more on generative models, Dimitri, specifically if you want to fix text. Some of the low-hanging fruits would be to try and fix mistakes that have to do with categorical attributes by extracting information from these sort of text descriptions. Putting it all together, though, from a systems point of view, it's extremely challenging. And again, the main challenge there is data movement. You have to be able to move data very fast from disk to CPU and to your GPU memory. So that is really a big challenge. Really an unsolved problem for combining text and these models properly.
Yeah, I was thinking maybe shorter text, you know, some very constrained applications like pairs of, you know, single sentence that have been somehow matched by an application like translators, something like that. But I was wondering, because you gave an example which was interesting with you know, predicting what is the label, the barcode or whatever of you know, some garments or some products, and you said that you were predicting it even better than some humans, which obviously we have all experienced if you go out shopping. My question is the following: what happens if you put it on some data, on some let's say weird in a sense data, to predict things like maybe there's a hashtag that this user wanted to use, but he didn't in a tweet and stuff like that. I mean, maybe you wouldn't want to say what the results would be, but I think that you could have some very, very interesting, you know, side effects or use cases, so to speak, from that.
This is true, and if I have time to answer the first part of your question. So why can we actually go from short text to categorical predictions, like the SKUs in that case? This type of architecture here, if you can represent text using dense embeddings. You can actually use a pre-trained model and obtain a vector representation of your sentence. That's not the hard part. And using these representations, if you know that certain attributes should be informed by that text because of this attention mechanism, you can actually use this network as is to predict back what should be the information of that, the value for that categorical variable, which is exactly the use case of the SKUs. The SKUs, I go from text, I go from continuous information back to categoricals. The other direction is actually much harder, for instance, which encapsulates actually the hashtag or fixing the text that the user put in through this information, through additional information. We are not there yet. We don't have a good solution. We have a good solution to identify and flag it potentially as erroneous, just because of incompatibility, if you will, of the representation of that value with what it is that we were expecting from the other attributes. but being able to fix it, that's actually that's a big challenge that we are actually focusing on now. I still don't have a good answer. Yeah. This comes a lot up in scientific use cases of the models that we're developing. Think of Earth systems where people want to analyze the literature to be able to extract new information also and identify if it is correct and clean it. That is a little bit, that's where exactly the problem that you're describing is coming in.
Great. So is there another question for Theodoris? Theodori, again, we thank you very much for the talk. Very interesting stuff. Thank you for waking up early.
Oh, my pleasure. My pleasure.
Forward to more from you.
Thank you very much for the invitation.
Thanks also from my side, Theodoris, and for the excellent talk. And so let's move to last, but of course not least, talk of the event. And I would ask Dimitrios Sundris to introduce our next speaker.
Okay, thanks, Aris. Thanks all. Okay. Okay, I think it's up to, okay, we'll stay in Seattle because Nikos, Theodoris and Dimitris are in Seattle now. So good morning, Kalimera Dimitrios. So the next speaker is Dimitrios Stamoulis. Okay. A few words about Dimitrios. Okay, Dimitrios graduated from National Technical University of Athens by 2013. His diploma thesis was about reliability of integrated circuits. Okay, then after his graduation, he moved to Canada. Okay, to McGill University. He still continues to work with EDA stuff about IC variability and hardware, and then he moved, let's say, a southern direction to Carnegie Mellon, where he spent 5 years working a topic about hardware AutoML stuff. Okay. For efficient deep learning application. His advisor was the famous Diana Marculescu. Diana now he's the president of Texas University in Austin. And after Pittsburgh, he moved, let's say, from East Coast to, let's say, West Coast, if you can say. And now he's senior manager in Microsoft AI. So Dimitrios, it's a pleasure. It's an honor. Okay. Thanks for waking up quite early for us. Okay. And yeah, thank you. Thank you so much.
Thank you. Thank you so much. Thanks for the intro. Thanks for the intro. It's a pleasure to be here. As you guys, let me get a mic check. I want to make sure you can hear me and also you can see my slides. Share first. So can you see my slides?
It's fine. Okay, please go ahead. Okay.
All right, that's perfect. Okay. So thanks once again, Professor Sundris, for the intro. Thank you so much for the invitation. It's great to be here. As Theo mentioned, it's always good to be back where the magic started, where everything started pretty much. Thanks for the kind words in the intro. As Professor Sundris mentioned, the topic would be related to pretty much what I was covering during my PhD research. And that is automated neural network design under hardware constraints. Similar disclaimer, this is research, these are things already published. This is not something disclosed as part of the work at Microsoft.
And that has been throughout my PhD and during my internship with Microsoft in the past. So as the title suggests, here's a really interesting question we would like to answer. So, and the question is, can we automatically design deep neural networks, right? So you don't need me to motivate why. You can see deep neural networks being in several deep learning applications. So as a cartoon here, you would want to take a convolutional neural network, which is shown in the drawing, where you have the different layers, and you want to properly train that in order to deploy for different in different systems. So if we go from left to right in these different examples here, you can imagine having key point detection, face recognition for mobile applications. You can have segmentation on an automotive system, and that means you also have to think about safety critical, response time critical implications. You have a smart home. It doesn't have to be a video. It could be audio, a smart assistant, where you have also personal data, security implications. And then what's recently gaining a lot of attention, it's a VR, AR. And again, you have computing system implications there with a headset, having runtime constraints, thermal constraints, power consumption constraints, and so on. So at the core of everything is how you train, how you select the deep neural networks that you want to deploy, right? So for everyone in the audience, let's consider a simple case that you have, you're starting your undergrad thesis, and then the advisor says, here's the application of interest. We're going to do video detection, and let's start with a family of networks. So the typical way you're going to start putting together your first week for the thesis, it would be pick the state of the art, the best model out there for the application, try on your data set, and then the advisor would come back and say, well, that's not as good, maybe we can improve things and so on. So in this case, the go-to step would be manual design. You will go back, try to increase the network, add more layers. You would try to do extra operations, such as normalization layers, squeeze excitation layers. So all these manual steps take time, right? Not only to decide what to choose, also compare from. It would take time to utilize the GPUs to train everything. So you can imagine what the underlying motivation here is. So back to the question, the title for this slide, can we automate the entire process? So ideally, what we like to have is algorithm, a set of tools called Neural Architecture Search, or NAS, which is a push-button solution, right? That would solve many of the problems for the thesis. You go back to the advisor and say, here's my model, here's the application, here's the system, push the button, boom, you get a design, and it trains. And this is not just wishful thinking, right? There's a lot of research coming into this space. You can imagine the implications. There's a lot of things. Imagine having that as a service to many researchers to provide. So it's out there. There are efforts. There are many startups working on AutoML, automated machine learning, neural architecture search, NAS, and so on. And there's of course challenges, as is with pretty much every problem. At a high level, we can identify two key challenges. Challenge number one, you can imagine already, the search space, the design space is huge. And going back to the same drawing, the simple cartoon of a neural network, let's consider in this case mobile nets. So even if they're supposed to be efficient and small networks, and you only have to tune 22 layers, if you zoom in, it's one of the blocks here. There are many choices that you have to start thinking about. There's many degrees of freedom to choose from, right? You can do convolutions would be 1 by 1, 3 by 3, 5 by 5. You can going back to revisit the number of layers. Do I want to prune? Do I want, and then other decisions such as quantization and so on. And then you design your model. You said I'm going to use mobile nets A, mobile nets B. You still have to tune more things. What's the learning rate, right? What's the number of epochs for how long I'm going to train? So even for such a small model, we have millions of different candidates of network deep neural network designs. As a proof of concept and motivating the underlying research, early work from Google It would experiment to trying to traverse that space in a somewhat efficient fashion, and it was a rudimentary solution. Either it was genetic algorithms, reinforcement learning, and it would be thousands of GPU hours, right? And also you can imagine the cost associated. In fact, in that ICML workshop, there was this discussion that the carbon footprint just to do a search for an application and a design, it would be as much flying New York, San Francisco 5 times round trip. So challenge number one, cost. Of course, we want to make this process as efficient as possible, which is the case in general for optimization tasks. The second challenge, at the end of the day, we like to deploy, take that auto-generated DNN and deploy in a system, right? So this would mean we have to consider many constraints, implications for this the system. Now, don't get me wrong, this has been a focus as long as deep neural networks and evolution have been around, right? Early work pruning, early work in quantization, which a note here, side note here, you can view those as a special case, as a subset of the solution space of architecture research. One caveat is that early methods focus on optimizing floating point operations, optimizing multiply accumulate operations, which work to an extent. If you look back at simple models, machine learning models, CIFAR data sets, but it has been shown that optimizing for one does not necessarily going to get good latency. That doesn't mean you're going to get the optimal memory performance. And that's an interesting scatter plot. That was a workshop Google AI a couple of years back at CVPR, and they were profiling on their devices, and they would show x-axis being, as we mentioned, flops count, multiply, accumulate, y-axis being latency in milliseconds. So if I were to take an off-the-shelf fairly old pruning method, and I just set it to give me something at 50 million operations, the set of candidates you possibly return, their latency could vary up to 2 times, right? So you're gonna get something, but it might not be the optimal thing to deploy. And then at the top there, you can see the other circle showing that for a given latency, floating point operations could vary a lot. So even if let's say you pick the low latency one, you might end up having to move a lot of things from memory, so that translates to energy consumption, bottlenecks, and so on. So that's as a second challenge and motivation. So with this in mind, the key underlying goal, key motivation for my research and the research in the space that I will be reviewing is to develop architecture search methodologies that are both hardware aware and search cost efficient, right? And again, we stress hardware here. We come from Microlab. That's an important set of constraints to consider always. So outline for this presentation. First, architecture search. Different people mean different things when you say AutoML, when they say architecture search. So first, I treat that as the lecture part of the talk, which is formulate the problem, abstract things out that will let us reach the problem definition and how we go about it. Once we put things together, we can start filling the gaps and consider an actual case study, right? Consider runtime aware optimization on a hardware platform and see how existing methods would solve the problem. And the third sub-bullet there is that would allow us to also go and study the evolution of the methodologies. Which kind of takes us to now, which is a great segue for the final part. I would like to use the opportunity to stimulate discussion for people picking up undergrad thesis, master thesis, searching for grad school. There's some really interesting directions there for future work, which would be good to briefly touch upon. And again, disclaimer, everything you're going to hear is personal views and things were already published. Okay, so neural architecture search. What are the key components, right? So let's formulate the problem. Let's go back to the example with your advisor saying, here's your thesis topic, here's here's what we want to do. So what you have to think about is the following components. Number one, the deep learning application, right? Based on the topic, based on the project, based on the ground, it would be object detection, key point detection, video captioning, you name it. The reason it's important is number one, data set, right? They already motivated the friction of the different issues that can come from issues with labels and the data set. But in the context of our training, what that dictates is the objective, right? If you're doing classification, you want to optimize for accuracy. If you're doing detection, you want to optimize for precision and recall and so on. So the block number one, the objective, and if you were to plot that in an axis, you want to go as high as possible. The second part, you go back to the advisor and say, I want to try REST nets. I want to try mobile nets. And going back to the example with mobile nets, why that matters? That matters because that would dictate your search space, right? We already motivated different configurations. It could be kernel size, number of layers, and so on. So the second component is let's denote the search space with possible solutions, possible designs for neural networks to use, which is alpha, capital search space. And how that ties back to the first block, right? If we were to rank them, and you see the yellow dots there, ideally you want to pick the one that gives you the best performance with respect to your objective. That's always the case. But then interesting things come into the picture. Hardware platform. The project specifies run on a mobile device, run on an NVIDIA Jetson. It could be a cloud cluster, a neural engine. So that is important because, as we mentioned, that would give you the constraints in terms of runtime, energy consumption, and so on. So in general, let's denote the set of those constraints with C capital. So things are getting interesting all of a sudden, because if on the x-axis, if you consider the hardware cost, previously you had a greedy ranking. You knew what was the best that you wanted to reach that point. But right now, what was the best might not be the optimal in terms of constraints, right? So you can see how the yellow dots all of a sudden spread the search space differently. So which brings to the fourth component, how we traverse the search space, right? As a hyperparameter solution. So let's consider an intuitive way. Let's consider genetic algorithms. And then what you would do as a solver is you're gonna randomly sample and point your slug with a set of mutations of population. And if you can follow the red dot there, is you would keep mutating until you want to reach a combination of optimal performance subject to that constraint. So ideally, you want to converge here. So putting everything together in plain English, we formulate the design of neural networks as the following problem statement. We want to find the architecture that has the optimal deep learning performance under hardware constraints, right? And same thing, we want to maximize over the solution space alpha. We want to maximize, pick the architecture alpha that maximizes our objective, such that the hardware cost of that solution satisfies the hardware constraints. See, so, and I promise to keep the math involved in the notations to a bare minimum. So pretty much what you will need for the rest of the presentation. So we put everything together, and as we mentioned, let's put actual definitions in. Let's consider an actual case study, an actual objective, and see how hyperparameter solvers would perform in this issue. So let's consider the case of runtime aware architecture search, right? So filling in the building blocks. Number one, application. The objective is image classification on ImageNet, open source data set, and we want to have high accuracy. We will consider as a search space the mobile nets, and you'll see in a bit why, because we want to, as the name suggests, we want to execute on a mobile platform. To simplify things, the purposes for the presentation, let's only consider the case that you want to select the type of convolution for each layer. That's the decision you're trying to make. So either choose from 3x3, 5x5, 7x7 convolution, right? And then what you end up with, you want to have the optimal classification performance while running on a Google a mobile phone under 80 milliseconds, okay? So plugging the definitions in, we want to minimize the validation error, flip of maximizing accuracy, subject to that runtime constraint. Now, an alternative formulation which helps out with optimization aspect is moving the constraint up to the objective. So an alternative formulation would be treat that as a multi-objective, where you want to again find the solution over space alpha, which minimizes the error and simultaneously minimizes the runtime. And then you have a trade-off parameter lambda. The higher you set the value of lambda, the more you focus on runtime and you trade off validation error. So the missing part here is how are we going to solve this problem? What's the NAS algorithm to use? So we'll start from the early days, what I would call V0, which is the standalone NAS, right? So the idea here is the following. You have the search space and you have a sampler, you have a sampling strategy. Again, let's consider the intuitive case of a genetic algorithm. So you would sample the search space, you would pick, let's say, 5x5 or 3x3, and you want to evaluate this point, right? By evaluate, I mean train it for a few epochs, get an accuracy, and then go back to your mobile and profile that. And that gives you a signal, right? You use that signal to update your sampler. Either you go back and you update the population with the mutations. In the case of reinforcement learning, you update the reward and so on. So you keep sampling. You go through that loop many times. So it would be then the next 5x5, 7x7, and so on. The point to make here is that you traverse the space point-to-point evaluations, right? So every time you have a standalone DNN based on the candidate, you train that, you profile the hardware. So as you can imagine, this is expensive, right? We mentioned that the entire space has millions of models. Genetic algorithms have been good enough to traverse that space, but even if you limit your search in 8,000 models, this is still years, the equivalent of about 3/4 of a GPU year executing 64 GPUs for 5 days. So the underlying motivation here from going from V0 to V1 was to tackle this issue with the search space. So the main question is, can we avoid doing that point-to-point evaluation? So this is where the multi-path differentiable architecture search came into the picture, right? So again, do we really have to evaluate one by one? So the main intuition of this line of work was, well, let's put everything, let's train one thing and have different candidates as different paths, right? And what you call into a supernet as you saw here. So for each layer, you have one branch with a 3x3, you have another branch with a 5x5, another with a 7x7. So right now that becomes a path selection problem, right? And you can see that you can gate the decisions based on some trainable parameters here, the A's parameters, right? So that allows you to have a differentiable expression of your architecture choices. So that would mean writing the weight of the layer I. It is based on the gating function, either a 3x3, 5x5, 7x7. So let's say I flip the gate such that I pick that path, the 5x5, plugging the number in, it would mean using a 5x5 kernel for that layer. That is an architectural decision, right? Now, of course, there are different ways to go about it, linear programming, softmax, leaky softmax, but at the high level, the key point to keep here is that right now you have the decisions as a function of both the weights and this architectural decisions. So that allows us to flow gradients back, as you would do with the weights, right? How you train weights. You go on the data set, you do backpropagation, stochastic gradient descent, and you compute the weights. If you in this expression, if you now flow gradients back, you will take gradients with respect both the weights and the architectural decision, going back to this gating functions being differentiable architecture choices, right? So that worked. That was a breakthrough in the space. The literature went from thousands of hours down to hundreds of hours. So this was at the time when our research picked up. We're asking the question, can we do even better? The main problem was the following. Even though that was efficient, you had to be careful about how many things you consider, because you can imagine if I wanted to also consider one by one, I have to do another branch. If I had to do double channels, I have to create another branch. So after a point, the number of combinations to branch out, it was growing really fast. So our work, single path NAS, as the name suggests, the underlying intuition is the following. You don't need different paths to formulate different operations, right? As long as you do this main observation, that if you use a 3x3, it's keeping the core of a super kernel. And then if you want to use the 5x5, is also adding a slice off outside. And then keeping the 7x7, it's pretty much selecting the entire thing. So that simple trick allows to view NAS not as a path selection problem anymore, but as a kernel level selection. The hardware equivalent of thing is when you want to do quantization and you want to profile different things, you don't have a branch that is the int 8 and others floating 16 and so on, and then you linear program which one is the best. You start from the highest precision and then you work your way down to 8, 16 and so on. So in this case, start from the super kernel and prune if you want to slice out the outer part that would correspond to having a 5x5. And that allows pretty much the supernet is as costly, as large as the largest candidate operation. So back to the formulation, plugging numbers in, you can see, for example, if my gating decision is select the 5x5, that would be flipping this value to 1. So right now you have the weight for this layer corresponds to using a 3x3 and the outer slice that is also what it would take you to 5x5. That also has clean properties on representing the runtime, right? So the as you can see here, the runtime for this layer is also a function of that decision because it's the runtime of using the 3x3, and then if you flip the switch to use the 5x5, it's the increase you're gonna pay to also move up to 5x5. And again, plugging into the formulation, the architecture decision alpha is a function, a differentiable function for both gating A's and the weights. So we can go back, select the lambda, and then minimize for both the error and the runtime, right? You can extend this formulation for channels. This is pretty much a superset of any pruning decision you can imagine. You can refer to the set of papers for details. And I would skip in the interest of time, but here's putting everything together. So x-axis here is the search cost with respect to epochs, log scale, and then you have on the y-axis is the accuracy for the application of interest. Now, all these methodologies here try to optimize for around 80 milliseconds, right? So we went from standalone NAS, thousands of epochs down to hundreds of epochs, and this is where single path would take we complete the picture, right? So this is achieving state-of-the-art performance at the time at 80 milliseconds, and then this is only in a couple of GPU hours. So we went from all the way from standalone the equivalent of GPU years down to a couple of GPU hours, and that's orders of magnitude reduction. Now, if you ask how that, if the search space is somewhat similar, if the methodology is focusing on the cost, where you get the extra lift from, the extra 0.5%, this is exactly because the methodology is efficient. It allows us to consider more branches, more candidates that you wouldn't be able to do otherwise for, let's say, the multipath approach. So we're excited to see that the adaptation of the underlying formulation. There are different papers at the space bearing the same name, single path, and we're gonna review some things later on. We're happy to see Fast AI having single path as part of the model library. It's out there fully trained for reproducible. As a segue towards future work, it would be good to consider, can we do better, right? Single path, can we do better? So key limitations. Number one caveat here is once you train, you do the backpropagation, and you select, let's say in this case, you flip the gate decision and use 5x5, right? You still train for a few epochs, which means that while the decisions are trained, the weights themselves are suboptimal. So you have to discard them and train from scratch the full number of epochs you normally do all the fancy data augmentations to get the performance on Imagine. So in that regard, it's single path, but it's still multiple stages, right? The second limitation is, well, you have to repeat every time pretty much, because in this trade-off plot, x-axis being the runtime, the target runtime, the constraint, y-axis is accuracy. And if you follow the circles here, the dots, we optimize for 80 milliseconds. But if I wanted to have one for 60, one for 40, one for 20, it would be repeating the process for a different trade-off parameter. So the actual cost, if you want to use that in production, it's n times the number of constraints you want to optimize for. So this is where in the last few months, the last year, state of the art has taken off. And so, disclaimer: this is not our work. This is follow-up works from Microsoft Research, Google Research, Facebook Research. But the underlying idea is, since you're searching anyway, as you're learning the decisions, the gating parameters, also fully train your weights, right? For any combination you can imagine in the network. So have a fully trained 7x7 if you were to use it on its own, have a fully trained 5x5 if you were to use it on its own, and so on. The key word here is if you were to use it on its own, which means that allows you, however you slice the network, you get a model running at 20, which uses 3x3s. You can get another model running at 40, 5x5s, and so on. Which means that's single path, single stage. And of course, you can imagine how the training cost is being lowered further. So putting everything together, it has been an incredible space. In the span of a few years, it's going from thousands of hours down to training once, a couple of hours, get a model. So you would start with multi-state standalone genetic algorithms, try one, discard it, try another, discard it, and then going to multipath with a differentiable formulation. And then it would be our work with revisiting the single path, and then the latest efforts building on top of formulations such as single path, going to a single stage methodology. And you can follow the cost, keep dropping and dropping all the way to now. So the even more interesting thing, we covered this block here as we abstracted out things, we discussed solvers, but we also identify other critical components, right? We discussed the cost, the model architecture, and the application. So each one of these block here has great opportunities for future work. There's some really interesting things happening in literature, and it's a few things that are weeks old. So from a NAS point of view, from an ultimate point of view, I can really see interesting directions in this space. So for the remainder of the presentation, allow me a few slides touching upon each one of those. Again, personal views, it's not disclosing specifics. And then the first component, hardware. This is really interesting. This is, and based on the audience, I mean, expertise, Microlab, CS Lab, state-of-the-art models for FPGA platforms, for computing platforms. There's many degrees of freedom here that you can incorporate into a NAS problem and have some novel exploration. So let me highlight a few directions. Number one, full stack optimization. What I mean by full stack. If you noticed previously, all I assumed was that you have the candidate, you profile that on your device. The hardware is what it is. Then you have another candidate profile, the hardware stays the same, right? So more and more people starting asking the question, can I jointly optimize, design my DNN and the underlying hardware? And it could be all the way up to the OS scheduling layer. So there are startups working on this thing. For example, AutoTVM, and that would co-optimize both kernel choices, but also how you're going to map it to run on a GPU. So tiling decisions in the CUDA, hyperparameters, and so on. Scheduling a number of threads, you can imagine different parameters you can consider here. Another interesting trend, taking what we just said to a step further, co-design, fully expose the hardware design. So this would play nicely into FPGA fabrics, configurable fabrics, neural engines, and so on. And you can abstract things up and plug that into a NAS solver. Remember, previously we said minimize over solution space of DNNs. That would be multi-variable optimization, which also includes over the solution space of the hardware decisions, such that you minimize both the error and the cost, right? So, and simple example, the hardware decision here is, let's say you have a state-of-the-art model for energy consumption for FPGAs. And one of the tunable parameters is precision, right? So hardware vector here corresponds to using int8, int16, which is a binary decision. So flipping that switch, it would, of course, lower the hardware cost, but at the same time, reducing arithmetic precision would affect the error. So jointly solving for both, it's an interesting space to explore. And then last trend, I would like to have a special note on modeling because my advisor Diana, it's pretty much the premise for the research group that is you cannot optimize, but you cannot model. So it doesn't have to be all the way tunable hardware. A direction that optimizes, and you say, for example, we have a model for place and routing algorithm, which is state of the art, and you can use that to model the number of gate you would get for the FPGA. You can use that, plug that into an existing NAS architecture, instead of runtime optimize for the metric of your interest. Just highlighting this trade-off, if nobody has done it before, it is a novel extension. It's a great project in the context of a past semester project, thesis, and so on. So this is with respect to the hardware. Another building block, architecture, search space, and we said this has to do with a model, set of candidates we consider. And there's also many interesting things in this space, right? Theo briefly touched upon attention. He had a screenshot with transformers, and this is gaining steam. State-of-the-art methodologies. I have the citations here. Once we share the slides, go back and check. A few months old papers. The idea is leverage the modeling capacity from transformers and whatever the performance gains have been on language, and try to port that over to vision applications, right? If you do that and you replace convolutions, right now you have to go back and also revisit the AutoML algorithm, because all of a sudden we're not only optimizing for kernel sizes, you reformulate the problem to decide how many encoders to use, how many stages of decoders, how many tokens to use on self-attention, and so on. So there's already work on this one. The dynamic transformer, NAS vision transformer, autoformer, you name it, which exactly trying to reformulate this space. Personal prediction would be once a set of more mature work come into play formulation-wise, the next step would be people considering multi-objective. So have the equivalent of GPU memory optimal autoformer, power optimal, power efficient, dynamic VIT, and so on. So there's a room there for explorations. Speaking of which, another set of along those lines, revisit some of the aspects of VIT, which is string transformers. If you haven't considered, it was best paper a few months back on ICCV. I encourage everybody to check. It's state of the art currently, to my knowledge, on several application tasks. And again, that redefines the search space. There would be interesting explorations there. Based on the tiling the string transformer uses, that would have different implications on memory, power consumption, and so on. And then the last thing is hybrid. This is weeks old explorations. And the key point here is trade-off, right? So in the past, the trade-off you had over your control is go from ResNet 50 to ResNet 101, and you stack up more layers, and that's how you traverse the front of accuracy versus flops.
it has been shown right now that instead of stacking more convolutions, keep the underlying structure of convolution-based, but augment that with attention. And that gives impressive accuracy versus flops trade-offs. So that's a really interesting front there to explore how hardware-aware AutoML algorithm would perform. So again, you wouldn't be reinventing the wheel and coming up with a new NAS. It would be taking existing building blocks as formulations and then pretty much being the first to map out this exploration space. And then the last part, it has to do with applications, right? And same underlying motivation, work with off-the-shelf, state-of-the-art methodologies, and revisit the objective. Why is it important? The reason it's important is the main counter-argument people usually raise with respect to these methodologies is that they're fairly finicky, that you heavily optimize for ImageNet, you heavily optimize for simple tasks, but then you try to go downstream for custom data, for deployment, object detection, they tend to be suboptimal. And in fact, there's recent work, ICML, a few months back, showcasing that the optimal pruning on one task is not the optimal on if you were to use that on the object detector. So from the NAS point of view, that's an interesting challenge to explore because right now, if you were directly to optimize for video detection, that means a larger model, a larger search space. So as we motivated for ready making the search more efficient, I would imagine this being even more challenge of a challenge in the following years. Another interesting thing is new trends, and by no means new here doesn't refer to being there. Multitask has been around, multimodal has been around. By multimodal, I mean train a DNN with different modalities, so it outputs language, it outputs audio, it outputs image. This has been around. What I mean by new is in the context of architecture search. So there's already work there that is a multimodal NAS, multi-tenant NAS, and so on. The second sub-bullet in terms of multi-tenant, that is really interesting with respect to good context for the research group here on the hardware side of things. This is single GPU have different models, not multimodal, different models. Have one model for language, one model for vision, how you schedule those in the underlying hardware. So view that as a hyperparameter problem, and instead of heuristics, that plays well into expertise that people have. And there's already papers in this one with HPCA, ISACAD exploring this from an auto optimization side of things. And then the last part is tools, right? Support and need for the community. It will keep growing, and there's some interesting efforts there. Open source tools, Microsoft has one that provides pruning architecture search, and a few weeks old that just released Razor that gives options for state-of-the-art NAS as well. I think that would be a great building block for explorations for people who want to check something, pitch that as a project for their semester, and so on. And I hope that worked as a foundation for some interesting questions or follow-up things if you want to take it offline. So before we move into questions, I would like to thank collaborators from Microsoft and Carnegie Mellon. But even more, thank you so much for the invitation, Professor Soudris, and thanks the organizer for helping with everything and for the initiative for the great event. That is, so we can open the floor for questions.
Okay, thank you, Dimitrios, for a very interesting talk. Okay, I think you share with us many results from your, let's say, PhD period, more or less. Okay, and some new ideas. I mean, really, like, let's say, the last slides about future directions, etc. With, let's say, with papers from 21, okay, and I saw some papers 2022, really amazing. So, and, yeah, yeah. So before, okay, I think it's time to proceed with questions. Okay. Okay, please, questions to Dimitris. Okay. You have no constraints from the general chair. Okay. Because it was the last talk. Okay. So please, any question from the audience? Okay, maybe some are tired. So, Dimitri, I'll ask some, maybe I have some questions from my side. Okay, okay. So, first one, okay, since I'm working with hardware, maybe it's not related with, with your talk, but it's okay, but of course related with ML and stuff like that. Do you know if Microsoft would like to invest, to develop new hardware? You have the platform, like, for example, like TPU, for like Google, or Microsoft will continue, to use hardware platforms from other suppliers.
Yeah, that's an interesting question. There's always a discussion whether you go your own silicon or not. I cannot speak for the company, but that's cloud would be a different word.
I understood. Okay.
But there's already the let me put it this way, from a research side of things, one of the friction factors to just jump into a different paradigm, right? If that's hardware, if that's modeling, it tends to be that you want to see that it's proved out, that it works well. So same goes with and across different companies. That's only for Microsoft. The recent discussion for transformers. Leveraging transformer vision, that would also require reflecting those changes in the hardware. So it would make sense for us as universities, companies would invest on exploring this research side of things. If it ends up being state of the art and lives up to the promise, then I can see the community following SIFT, right? So how was the case for CUDA, like following up all the ecosystem towards the convolution side of things?
Okay. I think, yeah. I think just maybe I don't know if it is simple or an if question. Okay. You actually spent you present, let's say, a design space exploration strategy or method. This method is completely platform agnostic, hardware platform agnostic. So just
yeah, that is a great point. So that is the hardware side of things is being treated as a black box, right? And in fact, many would just rely on a simulator to just expose some hardware metrics like a power consumption model. But what could be viewed as a limitation in this case? It's exactly opportunity space for novelty on an orthogonal. So discussions with Yannis, simple things. It would be coming up with a new model, like have an emulator, it could be FPGA, and see if you plug that into a search space, can you traverse a new set of solutions that nobody has reached previously. So to echo your point is, if indeed you open up the hardware design space underlying, that the Pareto front, it would yield better solutions. And Facebook AI was working on that, Reality Labs. Georgia Tech, some interesting explorations there, and the focus is the emulator itself, the hardware itself. AutoML is just the tool of making the case that how that can be used.
Okay, and so maybe there's no technical question, but I would like to share. Okay, since many many students are still in this let's say digital this digital workshop, let's say. I don't know if it is if you can share with them and with us, some lesson learned from your career up to now. It's not technical; it's rather philosophical. Okay, and again, have to thank you very, very much, really. Okay, So
that's a good question. That is a really good question. Again, thank you for the invitation. Lessons learned. We could in fact next year have a slide deck just for that, or a microlab. Number one, we've discussed that heavily. Early collaborations during my undergrad is bird eye view, the high level idea, abstract things out. There are different buzzwords to say that. What I mean by that is Diana has been my advisor in that front, helping a lot. Is try to get involved with the bigger picture. Just don't limit on the project at hand, what you have, what your thesis topic is. Ask your advisor to see what you will be applying next, for example, for a grant. Just going through that phase of having to think in a bigger picture, having to convince someone else other than your advisor is always good to understand the implications behind the underlying problem. So high level idea and thinking in that sense, I think it's really good place to start with.
We can't hear you.
Yeah, I think you're
Sorry, Dimitri.
Okay, so Dimitri, I have to thank you very much again. Okay, I have to thank all the speakers, the organizers. Okay, and yeah, I'm really happy that that many colleagues, okay, including our dean, is still here. It's around 8 o'clock local time, so really appreciate this. So I have to thank you, and now so I think it's Aris. I mean, let's say we'll say the last few words. I don't know. Okay. Thank you, Dimitri. Thank you, really. Yeah.
Thanks also to both speakers of this session. Very early, we woke up, sleepless in Seattle, we would say, and now sleepless in Athens, and we are all until late here. Thank you all for being here. It was a very nice event. We had excellent talks. Thanks to speakers, thanks to chairs, thanks to colleagues that invited speakers, and a big thanks to Dimitrios Fotakis for putting all this together. And I don't have anything else to say. Maybe if someone wants to say something, to add something to this, maybe our dean to close the event. Ari? We can't. Your mic.
Can you hear me now?
Yes.
Yeah, I have nothing else to add. I think that it was a worldwide event. We had people from all around the world, especially from US or Europe. Let's hope that next year we will have an event in our auditorium full of people. I guess we can expect that by next year we will meet all together and we'll have the opportunity to be all together. So thanks very much for the organization, Aris, Dimitris, all the colleagues in the Division of Computer Science. I think that all the attendees enjoyed it. It was really nice, and we had a very high, top-notch talks from very, very esteemed colleagues and alumni of the school. Thank you very much.
Thank you. Thank you all.
Thank you very, very much. And see you next year.
Yeah.
Thank you.
Next
year.
Bye-bye.
Bye-bye.
Thank you.
Bye-bye.
Γεια σας. Καλό βράδυ.
Καλή νύχτα σε όλους. Γεια σας.